आपने गो लाइव किया ना? ठीक है, आई थिंक थोड़ा लैग है इसमें। हो गया ना? Yeah, I think it's fine now. Hello? Yeah, okay, good, fine. So welcome back, students. Session got delayed actually. There was some small technical issue, and Amit Mayasa system has little issue. Okay, so no issue. Fine. I'll take this session alone. Okay, so are you all fine with this? So please type in the chat box. Yeah, we have started the class finally. So yeah, we have started the class. Okay, so please type in the chat box. So is my audio and video clear to all of you? So shall we go ahead with this session of fluid mechanics and turbo machines? Perfectly fine. Okay, so yeah, this is one very good session. Basically, this initiative of Super 36 on different subjects is really one of the very good moves in front of GATE examination. With GATE almost being within 15 to 20 days, this is a very good session which revises all the concepts in a particular subject and also gives you enough idea on each particular subject actually. Okay, because if you can solve these questions, then definitely you'll be able to solve all the questions that comes in the near time, okay, in GATE 2023. Because one thing I'll assure you, you may not have the same models, but definitely the knowledge what you get by solving all these questions, that would be definitely enough for taking this questions in this fluid in any subject that's done by our team actually. Okay, yeah, good evening Sukumar, Nikhil, Dayanand, Prashant, I'm not late. Okay, yeah, good. And I'm Roshan, all of you guys. Okay, yeah, hello. So basically if you see the schedule that we have came up with, so on 14th January we have started this sessions basically. So on 14th it started with basic and applied thermodynamics with Negi sir and Vinod Dasulia sir actually. Okay, so it's a very good session. We have some nice questions on entropy, applications of thermodynamics, again Baton cycle, VCIS, psychometry, all these things. So then on 15th, the next day, we have this class of engineering mechanics and theory of machines with Apoop sir and Vishwajit sir again. Okay, we had some long session with a lot of good questions again. And on 16th we have strength of metals plus machine design with Ramanand sir plus Apoop sir. And of course on 17th we got one very nice session on material science and manufacturing technology by Swadesh sir and Aditya Paul sir, correct? So Aditya Paul sir basically dealt with the production part 2, generally the metal cutting theories and all, and Swadesh sir dealt with the material science and all the basic fundamental casting or generally manufacturing processes. Okay, and today we are going up with fluid mechanics and turbo machines, and myself and Amit Mojasa is supposed to take this session, but I'm taking this session alone right now. Okay, so I hope I won't bore you much actually. We'll talk some really nice examples on the way and we will enjoy the session. Okay, and tomorrow you have again this session at 9 a.m. in the morning by Amit Dikshit sir and Sandeep sir, of course, on industrial engineering, operations research, and of course heat transfer. Clear? So this is the schedule, and we are at the penultimate class today with fluid mechanics and turbo machines, and tomorrow is the last class of this particular subject. Okay, so this is our team, which we have a nice blend of industrial experience and also a very good academic experience team. So few of the people here has, for example, for this, if you take 23 years of experience, and many of the teammates of my teammates, which I am proud to work with this team, has some 10 to 15 years of work and obviously, yeah, we have me and myself, and some of the other team members has some good industrial expo. We have worked with the turbines in power plants, okay, and we worked with some pumps basically in our coming to myself, I have previously working with some oil industry. Okay, so I was dealing with pumps and all the turbo machines. So we had a very good idea on this particular fluid mechanics and turbo machines actually. Okay, so we'll talk about them. So let us start the session. So shall we start the session? So it's already delayed, right? So without any further delay, let us start the first question here. Okay, XC questions will be covered, right sir? Yes, definitely. I'll give you whenever you have doubt on any concept, please ask me in the chat box. I'll definitely respond to your comments. Okay, and I know there are a few areas where you people feel very difficulty, especially the Reynolds transport theorem when you're applying for the angular momentum. All these things we'll deal in this session. Okay, clear? So are you all ready? So let us start with this question. Okay, so हिंदी में भी कुछ बोलिए, मे बी नेक्स्ट टाइम, क्योंकि मेरा हिंदी उतना अच्छा नहीं है. ओके, सो इसलिए fine, let us start here. Under what conditions is the equation divergence of rho v bar is equal to 0 is valid? Okay, so basically they have given you certain types of flows actually here. Okay, so what are the conditions under which this particular this equation divergence of rho v bar is actually equal to 0? So let us try to identify this. Normally if you see the continuity equation in integral form or generally in the differential form here, so if you talk about the continuity equation, if you talk about the continuity equation, we have dou by dou t plus divergence of rho v bar is equal to 0. Correct? So this is what you have. So whenever you have this A, B, A and B, A and C, only A. Okay. What about other options? No one is interested in C and D. No one is interested about C and D actually. Let us see here. Okay. So first of all, if flow is steady, if flow is steady, then definitely things do not change with time. So this term is actually 0. Then we get divergence of rho v bar is actually equal to 0. Yes or no? Correct? First of all, will this happen? So please type in the chat box. Let us suppose if the flow is steady, then time rate of change of density will be definitely 0. Correct? Yes or no? So all of you, please type in the chat box. Come on, let's make it an interactive session. Okay, it's not like a one way. I keep on solving and you keep on typing the answers. Let's not do this. Okay, so let us interact. So please tell me, if the flow is steady, then will this time dependent term goes to 0? Correct? So now if the flow is steady, depending on whether it is compressible or incompressible, this term is always 0 and this is always the equation. Correct? So divergence of rho v bar is equal to 0. So first of all, out of these 4 options, we have option A, steady incompressible flow, and steady incompressible flow. This is steady incompressible flow and this is steady compressible flow is also valid. Correct? Now if you see one more thing carefully, this term, look, try to understand one thing. Let us suppose if flow is incompressible, for example. So see carefully, if flow is incompressible, for example, okay, if flow is incompressible, then can I say rho is constant? What is the meaning of rho is constant? Density do not change with respect to position and also it do not change with respect to time. Yes or no? Correct? If flow is incompressible, then definitely the fluid's density or the density at any point in the flow doesn't change with location and also with time. Correct? Can I say this? Yes or no? So please type in the chat box. Can I say this? Can I say if flow is incompressible, then your density is constant, which means density do not depend upon the location, space coordinates and also time. Correct? So that means normally in case of incompressible flows, we have divergence of v bar is equal to 0 actually here. Now whenever density is constant, can I multiply density on both sides here? Can I multiply density on both sides? Yes or no? Can I multiply density on both sides? So when I multiply density of both sides, since density is a constant, I can take density inside this operator. So divergence of rho v bar is still 0. Correct? Yes or no? Can this happen? So please type in the chat box. Can I say that whenever the flow is incompressible, since density is just a constant term, I can keep the density inside the differential operator? Yes or no? Correct? Can I do this? Because density is constant. So let us suppose if you have equation x is equal to 0, for example, I can write 5 times of x is also 0. Correct? I can multiply density on both sides of this equation, and since this is a constant term, I can take this constant inside this differential operator. Correct? So that's why if you see, this equation also holds good for incompressible flow. Okay, so this equation also holds good for incompressible flow. So if you see these options, unsteady incompressible flow. So if the flow is incompressible, this is valid. So unsteady compressible flow. So here this equation is not valid, because whenever the flow is unsteady, your things actually change with time. Okay, so therefore that dou by dou t term still remains here. Clear? So did you understand how A, B, C are the correct answers? Because many of you may comment A, B, or many of you may comment A and C, but actually A, B, C are correct answers, because in case of incompressible flow, whether the flow is steady or unsteady, it doesn't matter. That equation, divergence of rho v bar, is always 0. Okay, in analysis what we do is we take this density out because it's a constant, and we write the equation as divergence of v bar is equal to 0, which can also be written as divergence of rho v bar is 0, because density is actually a constant term in that. Clear? So did you all understand how A, B, C are the correct answers? Look, this is not a correct answer, okay? Because in case of compressible flows, you cannot take this divergence, you cannot take this density out of this differential operator, correct? Because in case of compressible flows, depending upon space, density of the fluid can change actually. Yes, got it? Is this clear to all of you? Did you all understand how D is the wrong option and A, B, C all are correct options here in this case? Yes or no? So please be careful with one thing. Normally, this equation divergence of V bar is equal to 0, or generally divergence of rho V bar is 0. This equation is valid for incompressible flows, both steady and unsteady, both steady and unsteady, both steady and unsteady. And here this thing, okay, so please speak slowly. Okay, my number of words per minute is high, I think. Okay, yeah, I'll go a bit slow. Okay, so and this equation is valid for incompressible flow, and steady compressible flow, and steady compressible flow. Okay, when I'm not writing any steady or unsteady here for any type of incompressible flow, it can be steady incompressible flow or it can be unsteady incompressible flow. As long as things are incompressible, things do not change with time. Okay, so that's what we have here. So are you all clear with this question? So did you all enjoy this question? Because all the comments I got, you have marked only 2 options, but actually 3 options are correct for this equation. Okay, so let's go for the next question. So let us see this question. Which one or more of the following statements is or are true for a stream function psi is equal to 5 times xy? Okay, so whenever you have psi is equal to 5 times of xy as your stream function, then what are the correct options out of this? So first thing, discharge between the points p1, 1 and q2, 2 is 15 units. Magnitude of velocity at point P is 5 root 2. Magnitude of velocity at Q is 10 meters per second. Acceleration of particle is 20 meters per second square at point P. Okay, so now let us verify the correct options. First of all, if you take 2 streamlines, for example, okay, so let us suppose you take 2 streamlines. If you take 2 streamlines, for example, point P, one streamline is passing through point P, another streamline is passing through point Q. Then for unit thickness of the streamlines, if you want to calculate what is the discharge that's flowing between the streamlines, actually there could be some discharge. So what could give you the discharge actually? Here the stream function value is psi1 equal to constant, or psi is equal to c1, for example, and here it is psi is equal to c2. So let us suppose if your stream along a streamline, stream function is constant, we know this. Okay, so let us suppose if you have 2 streamlines which are passing through 2 different points, then if you have a flow in between, then for 1 unit width of the streamlines, what could be the flow that's happening between them actually? Okay, so let us see. In this case, flow or discharge between the streamlines, per unit width is equal to the difference in the values of the stream functions actually. Okay, so along the streamline, this stream function is some constant, and along this streamline, this stream function is some different constant. So if you take the difference between these two, that difference is actually equal to the flow rate between the two. How many of you know this point? So please type in the chat box. How many of you know this point actually before? How many of you know this point, that the discharge between the 2 streamlines per unit width is equal to the difference between the 2 streamlines? Yes, psi2 minus psi1 by W. Okay. Okay. Me. Now, how many of you know how it happens? That's what I want to ask. How many of you know that how many of you know that how do you get the difference between stream functions as the discharge? How many of you know this point? Good. All of you knows. Okay. My concept was a bit weak here, but now in clear, sir. Okay, good. Okay, now try to understand this. If you take the flow in this direction, for example, if you take flow in this direction, you take some normal area to this. Okay, you take some normal area to this. This is the velocity of the flow, and this is the normal surface. So what you do is, to this normal surface, oh, just a minute. Yeah, to this normal surface, what we do is we project actually perpendicular faces. When you project perpendicular faces, when you have your velocity like this, okay, so let us suppose if you have some velocity of the flow, something like this, you divide this velocity into components. So you have u in this direction and the v, for example, in this direction. Okay, v in this direction. So here if you see, the outward normal to this surface will be outward, and to this surface it is in this direction. So if you want discharge, you get q into dy, where this height is dy, into unit width of the streamline, plus v into dx. But here this v and this dx, if you take this dx, this is in opposite direction actually here. Okay, and v actually, if you resolve, this could be in the positive direction, of course. Okay, so v normally, if you resolve this uv in the standard xy coordinate system, this n outward normal to this surface will be in the opposite direction. So v right minus dx. Okay, so that's how the discharge actually gives you the difference between stream functions. This u dy minus v dx will actually give you difference in the stream function. Okay, so normally if you know the concept of stream function, you can understand easily this equation u dy minus v dx gives you the differential equation for the streamline. So that's the small difference in the stream function. So now if you see, at p1 comma 1, what is the value of psi? Psi is equal to 5 times of xy. So 5 into this curve 5xy is passing to this point, so this 1 comma 1 should satisfy that. Okay, so this is 5 actually. Okay, so 5 units. And what about the point 2 comma 2? Here it is psi is equal to 5xy, which is equal to 5 times of 2 into 2, which is 20 units. Okay, so when you have 20 units, then magnitude of c1 minus c2. So along this streamline to 1 comma 1, psi is equal to 5 is constant, and along 2 comma 2, psi equal to 20 is constant. So if you do c1 minus c2 or psi1 minus psi2, sometimes if you write magnitude of 5 minus 20, which is 15 units. So 15 units is the discharge that flows between the two streamlines, which are at passing 2 points 1 comma 1 and 2 comma 2. Clear? For second income fluid flow, steady flow, sorry, I didn't get this. For 2D incompressible, I think, okay, incompressible fluid flow, steady flow, the difference in values of stream function gives the discharge permit across the lines joining 2 points. Yes, correct, of course. Okay, I think you have written this in a statement. Fine. So anyhow, the difference is the discharge between the two per unit width. Okay, so here if you see, this 15 units is actually correct answer. Next, come to the magnitude of velocity. Okay, so how do you calculate the magnitude of velocity here? Okay, so let us calculate this. How do you calculate magnitude of velocity? Let us see. Psi is given 5xy. Now if you see, this is a two-dimensional flow. If you have ui plus vj, for example, at any section you have ui plus vj, then how do you add the components u and v? So tell me, how do you add the components u and v? U is actually equal to dou psi by dou y, and v is equal to minus dou psi by dou x. Correct? Yes or no? So please type in the chat box. If you know complex numbers, you can add that easily, because we have Cauchy-Riemann equations, and from Cauchy-Riemann equations we can easily write the dependence of velocities on stream functions. Correct? Yes or no? Mavish, sir, please, I have a request. Please take some time out of your schedule and give us XCB PYQs before GATE 2023. Okay, I'll try to do that. Okay, surely. So tell me, is this equation correct? Yes or no? All of you, everyone should type in the chat box. So please type in the chat box, is this equation correct? Do you all remember this? Look, for any incompressible flow, if you see, look here, I would like to take one slide and would like to keep some points here for you. See here, for any irrotational flow in general, for any irrotational flow, there exists phi, which is velocity potential function, such that u is dou phi by dou x and v is dou phi by dou y. Correct? So if you see, normally in potential flows you talk this. Okay, so if you see, in case of potential flows, we define complex potential function, which is this velocity potential plus I times of stream function. Correct? And we take this f of z is analytic function. Okay, so I haven't taken any detailed course on fluid mechanics, but if I take, then definitely I'll spend some time there. Okay, so here if you see, this f of z is equal to phi plus I times of psi actually here. So whenever this is phi plus I times of psi, then they should satisfy Cauchy-Riemann equations, which is dou phi by dou x is dou psi by dou y and dou phi by dou y. This gives you minus dou psi by dou x. And here this phi is such a way that this velocity vector v bar is actually equal to gradient of phi actually. Okay, in vector calculus there is one very fundamental rule. Normally you might have seen some of my maths classes in English channel of this gate Wallah. So I'm telling you one thing, whenever in vector calculus, if you see, whenever if any vector point function is irrotational, okay, means if the curl of the vector point function is 0, then always there exists some scalar function such that this gradient of the scalar function, means the change of that scalar function, gives you the vector function actually. Okay, so that's why here this v bar is equal to gradient of phi. So you have u and v. Okay, and from Cauchy-Riemann equations from complex analysis, these two are equal. So u is equal to dou psi by dou x dou y and v is equal to minus dou psi by dou x. Clear? So that's how you have this u and v values. Okay, so now if you write this components, u is equal to, if you differentiate this 5xy, okay, so stream function value is given 5xy, so if you differentiate with respect to y, you have 5x and v is equal to minus 5y. Now if you want to calculate velocity at any point, your velocity vector is how much? Therefore velocity vector in this case is ui plus vj. So ui, which is 5x plus, here there is a minus, so minus I into minus 5y actually here. Okay, so if you want magnitude of velocity at any point, magnitude of velocity at any point is equal to 5 into square root of x square plus y square. Okay, so this since I think you are not familiar with complex numbers right now, I'll write in vector coordinates I bar j bar. Okay, so this is better for you. Okay, as of now this could be better. So can divergence has minimum value also? Yes, obviously we can see gradient, divergence, curl, they can have minimum values. Okay, when I teach vector calculus, they will come in a much detail about this. Okay, fine. So now if you see, this is the velocity. Therefore at p which is 1 comma 1, magnitude of velocity is equal to 5 times of square root of 1 square plus 1 square, which is 5 times of square root of 2 units. 5 times of square root of 2 units. So let us check the options. 5 root 2 meters per second. Okay, of course they have given in SI units, so 5 root 2 meters per second is the correct answer. Okay, so this is units is given in SI units, meters per second. So 5 root 2 is correct. Now what about q? At q, which is 2 comma 2, magnitude of velocity is equal to 5 times of square root of 2 square plus 2 square, which is 4 plus 4 is 8, and square root of 8 is 2 times of square root of 2, so 10 times of square root of 2 meters per second. Correct? Because this is 8, so 8 can be written as 2 root 2, so 2 root 2 into 5 gives you 10 root 2 meters per second. So if you check this, let us see, this is given 10, square root 2 is missing. Okay, so that's why this value is wrong, so this option is wrong. Now what about acceleration of particle at point p? Okay, so they want acceleration of the particle at point p. So how do we calculate acceleration at point p? This is a 2D flow, so let us see. Acceleration is equal to ax I bar plus ay j bar. Correct? Now how do I write the components ax and ay? Let us write ax is equal to dou u by dou t plus u into dou u by dou x plus v into dou u by dou y. Correct? And what about acceleration in y coordinates? Dou v by dou t plus u into dou v by dou x plus v into dou v by dou y. Okay, so you have this. Now if you see steady flow, now there is no involvement of time here because you see the velocity vector, there is no involvement of time. So this dou u by dou t and dou v by dou t terms are 0. Next, if you see this u, which is 5x, don't have any involvement with y, so dou u by dou y is 0. Similarly here there is no x, so dou v by dou x is 0 actually. Okay, so that's how we can make the maximum terms 0 in the acceleration components. So this is u into dou u by dou x and this is v into dou v by dou y. So this is equal to, what is u? 5x into dou u by dou x, which is 5, and this is v minus 5y into minus 5. So these are the components. Now at x is equal to 1 and y is equal to 1, because they are asking the acceleration at point 1 p, and p coordinates are 1 comma 1. Okay, so whenever p coordinates are 1 comma 1, magnitude of acceleration at 1 comma 1 is how much? X component of acceleration will be 25 and y component of acceleration will be 25 again. Okay, so 25 square plus 25 square actually, so 25 times of square root of 2. Yes or no? Correct? Can you all understand that this acceleration is 25 times of square root of 2? Correct? So please type in the chat box, because you can easily understand. Here if you put x equal to 1, this is 25 and this is 25, so square root of 25 square plus 25 square, so 25 times square root of 2. Correct? So Kenil, I think you total 50. Okay, there should be, you should do calculations little carefully. Clear? So 25 times of square root of 2. So what are the units? Okay, so 25 times of square root of 2, but here they have given you 20, but 25 root 2 is more than 20 actually. Correct? So that's why this 20 is a wrong option, so D is also wrong answer. Okay, so therefore this is 25 root 2 meters per second square, the components of acceleration. Clear? Guys, look, this calculation should be done very carefully. Okay, I'll tell you the main problem in exam. Okay, whenever you're trying to solve questions, many times it happens that, let us suppose myself in one exam I have done this mistake when I was writing gate. Okay, normally this calculator will be very small in exam. Okay, so whenever you are trying to click the points, instead of clicking 5 you may click sometimes 8. Okay, or instead of clicking 5 sometimes you may click 2. These things will happen. Okay, so you should be little careful. Myself, when I got this 40 all India rank, I have committed 8.6 marks mistakes in calculation. Okay, so 8.66 marks I lost because of calculation. Okay, because in gate examination when you answer some questions which has options as a wrong answer, you will get some bonus of negative marks. Okay, so that which is not required. Okay, so please be careful when you are doing those calculations. Clear? Now let us go for the next question. So let us see, a nozzle has inlet and outlet diameters of 10 centimeter and 5 centimeters respectively. If it discharges air at a steady rate of 0.1 cubic meters. Okay, so cubic meters per second. Okay, cubic means cubic meters per second. Okay, now into the atmosphere, the gauge pressure at the nozzle inlet will be, of course, static pressure. They are asking about static pressure. It's a simple question, 1 mark question. It can be asked as a 1 mark question. So please try to solve this question. So all of you, please try to solve this question. Let us check. You take a nozzle. Okay, so you take a nozzle. This is nozzle inlet and this is nozzle outlet. Okay, now what's happening here? There is some flow of air in this. Okay, there is some flow of air. They have given you the discharge of air. Then the gauge pressure at the nozzle inlet will be dash. Okay, so let us suppose there are no losses. So how to enter log base 10? Please show. Yeah, I'll show you. Okay, so let us complete this question, then I'll show you definitely. Okay, Vijay. So see here, we have air here. Inlet diameter is 10.1, so D1 is 10 centimeters, and outlet diameter is how much? D2 is 5 centimeters. Okay, so this is 5 centimeters respectively. It discharges at a steady rate of 0.1 meter cube per second. So the discharge to this is how much? 0.1 meter cube per second. Okay, so this is 0.1 meter cube per second, and this is giving into the atmosphere. So what is P2? P2 is nothing but the atmospheric pressure, local atmospheric pressure, let us say. Okay, so at some location. Now what they are asking, the gauge pressure at the nozzle inlet will be dash. So what is P1? This is what they want, but they want this value in gauge value. Okay, so we'll calculate this in gauge value. Okay, so now let us see this. Q is 0.1 meter cube per second discharge. Now if you apply Bernoulli's equation, because this is a steady flow, so applying Bernoulli's equation, so let us apply steady Bernoulli's equation. Applying Bernoulli's equation for steady state, of course. Okay, so when you apply Bernoulli's equation, we know that P1 by rho z plus V1 square by 2z is equal to P2 square by rho z plus V2 square by 2z. Of course, because here this nozzle, they didn't talk about any elevation or the potential differences. That's why we are taking the net potential difference in the flow is 0 at the inlet and the outlet sections. Okay, so whenever they are zeros, now we know, let us try to identify certain values. This P2 is nothing but P atmospheric conditions. Okay, so G can be cancelled from all the terms. So when you cancel G, P1 minus P ATM, P1 minus P ATM local by rho is equal to V2 square minus V1 square by 2. Correct? V2 square minus V1 square by 2 actually here. Okay, so this is 2. Now if you see, they are asking this answer in kilopascals. Okay, so static pressure, of course, this is static terms and these are the dynamic terms when you multiply density. Answer A is correct answer. Meter cube per second. Yeah, meter cube per second, right? What did I write? Meter cube per second. Correct? Any issue? Prakash, any issue here? I think it's fine, right? Even I have written meter cube per second. When you write QMECS, cubic meters per second. Okay? Clear? So let us see this. So if you try to solve this, we need this value P1 minus P ATM local. Okay? So this value V2 square minus V1 square multiplied with the density by 2. You will get this answer in pascals if you put velocities as usual. Okay, so let us put this. What about V1 and V2? We can write V1 is 4 times of Q by pi D1 square and V2 is equal to 4Q by pi D2 square. Okay, now you know you need not calculate both individually. You can apply the continuity equation. So applying continuity equation, we have A1 into V1 is equal to A2 into V2. If you take this section as section 1,1 and this as section 2,2. So here you have certain velocity here and here you have certain velocity. Okay, so when you take this, then this implies A1. So A1 is nothing but pi by 4 D1 square V1 is equal to pi by 4 D2 square V2. So pi by 4 gets cancelled on both the terms, and you know one thing, this D2 and D1 relation is given. D1 is 10 and D2 is 5 centimeters. So D1 by D2 is 2 actually here. Okay, so whenever D1 by D2 is 2, we know this term can cancels out, means D1 is 2 times of D2, so this gives you 4. So V2 is 4 times of V1. Correct? So this is from the continuity equation. Okay, so this is from the continuity equation. So his name is Uddhav Prakash. Is his father? His name is Uddhav Prakash. Oh, I didn't get this. Okay, fine. I hope you don't feel. Okay, I'll call you politely. No issues. Fine. So see here, if you put V2 is equal to this, then density by 2 into 4 times of V1 square minus V1 square. This is 15 V1 square. Okay, so normally I have shown you this relation. Normally whenever you talk about venturi meters or orifice meters generally, or in pipes, whenever they are converging, whenever the ratio of D1 to D2 is 2, then this constant turns out to be 15 by 2. If you can remember this, you can remember, or else if you don't remember, then you know, you can just go with the continuity equation. Okay, so this implies rho or 15 by 2 rho V1 square. So what about V1 square? So square of this quantity, 15 by 2 into density. So what about density of air? They haven't given you anything, correct? So let us take the standard value 1.25 into, then because they haven't given, so let us assume this. Assume rho air at this conditions is, for example, 1.25. okay, so 1.25 is what you can take here. Okay, so when you take 1.25 or 1.20 for sometimes you can take. Okay, so second decimal doesn't give you much impact. So this multiplied with V1 square. So what is V1 square? Square of this quantity. So 16 q square. So q is 10 power minus 1. So 10 power minus 2 is q square divided by pi times of d1 square. Okay. So d1, this is pi square and d1 power 4. Correct. So what is d1? 10 centimeters. So 10 power minus 1 meters. So this is 10 to the power minus 4. So this many pascals. Okay. So this answer is going to be in pascals. And since they are asking in kilopascals, we can write in kilopascals here. Okay. So let us do this calculation. So when you do this calculation, then or generally let us take the standard. Anyhow, this is fine. So let us take this density of A is 1.25. Generally we write the value as 1.2. Okay, because air don't have a constant density with respect to temperature and all, it changes. Okay, so but normal values we'll take is 5/4. Okay, now if you simplify this, 2 cancels out this 8 times. Okay, and this 10 power minus 2 will give you a 10 square here. Okay, so this value, let us multiply this value. 15 into 1.25 into 800. Okay, this is 800 by pi square. So let us do this calculation. I'll show you the calculations along with me. Okay, so all of you please practice the calculations along with me. I'll work out. Okay, now if you see 15 into 1.25, 15 into 1.25 into 8 into 100. So into 100. So this value divided by pi square. So pi and square here. Okay, so pi square gives you 1519.8. 1519.8 pascals. Okay, so if you reduce to kilopascals, we can write 1.52 kilopascals actually. Okay, I took the density of water by mistake. Yes, here they have given you the fluid is air. Okay, you shouldn't take density of water. Clear, Chandan? Now see here, this is 1.52 kilopascals. Okay, so something close to 1.5, 1.46 is what you can take. Okay, because when you take density of A is not a constant. Since nothing is given here, we have assumed some standard value. But normally if in GATE examination they can give you exact values that take density of air is equal to some value 1.20, 1.22 such values. Okay, so it would be somewhere around 1.25. Okay, in general. So that's why I have taken you. So 1.52 is what we got. So generally we can take something close to 1.5, which is 1.46 kilopascals. Clear? Okay, a simple question from Bernoulli's equation. That's it. Here they have asked you gauge pressure. So that's why I have shown you P1 minus PATM is nothing but P1 gauge actually. Okay, so they are asking you about P1 gauge pressure. So 1.52 kilopascals can be taken. Clear? So please type in the chat box. Is this clear to all of you? Okay, this is in kilopascals. Many of you might have substituted density as 1000 because you might have assumed that fluid is water. Okay, because this is one common misconception that students do. That's why we have kept this question. Okay, it's a very easy question, a simple question from continuity and Bernoulli's equations. That's it. Okay, log base 10. Yes. Now, first of all, I'll ask you one thing. Tell me, what do you think is the answer of log 10 to the base 10? All of you, please answer this. Log 10 to the base 10. I think you're asking this log 10 to the base 10 because in machine design, when you're drawing the SN curves, you generally do the log calculations. Okay, so that's why I think, if I'm not wrong. Okay, so anyhow, if you see this value, what is this value? So please type in the chat box. What is this value? 1, correct? Which is known to us. 1. Now it is 1 actually. Okay, so now if you see in examination, you have two lns here. One ln is not, this ln button is for this value, means ln natural logarithm, and log, this button is to the base 10. Okay, now when you want to calculate log 10 to the base e, calculate 10, then again apply log. So this gives you 1. Okay, when you apply log, this is to the base 10. Okay, and if you want log to the base e, for example, okay, so for example, you know 10 ln, if you see 2.302, which is log 10 to the base e actually at that time. Okay, sometimes you may encounter a situation where you have different values. Okay, means for example log 5 to the base 2, log 5 to the base 3, these kind of things. Okay, so if you want to calculate log 5 to the base 2, then in that case 5, this button log x to the base y. So when you click this log x to the base y, now enter base. Okay, so this is the value of log 5 to the base 2. Okay, so that's how you calculate logarithm values using virtual calculator. Clear? So is this clear to all of you? Now I hope now no more issues. So please also tell about anti-log of base 10. Exponential. Okay, If you want antilog, you write exponential, then you can calculate exponential functions. For example, if you want e power 4, okay, then click 4 and click e power x. Then this is value of e power 4, antilog of 4. Okay. 10 raised to power 5 into 10 power 5. Okay. The main difference between Casio and virtual calculator is, in Casio, you will generally type the function first and then you click the value. For example, if you want to calculate e power 5, you click e power x function and then you click 5. Now, here what you write is, in virtual calculator, first you type the value, then you should type the function. Then you will get the correct answer. Okay. Got it? Fine. So basically here, this is how we take the logarithm values and all using this calculator. Normally in machine design and all, when you're taking about the SN curves and all, you generally you find the uses of this log 10 calculations, then you can use these things. Fine. So let's go for the next question. So let us solve this. A rectangular tank 3 meters long, 2 meters wide and 2.5 meters deep contains water to a depth of 1.5 meters. It is accelerated horizontally at 3 meters per second square in the direction of its length. Then which one or more of the following statements is or are true? So this is from the rigid body motion. Okay, so let us see. There is one tank, water tank. So let us see. There is one water tank actually. There is one water tank like this. Okay, so there is one water tank. Now this water tank has water filled up to certain level. Okay, so this got water filled up to certain level, 1.5 meters deep, for example, let us say. Okay, so this got filled to certain level actually. So there is some water level up to which it is filled. Just a minute. I think I have to shorten this a bit. Fine. Okay. Fine. Okay. So there is water up to this level. Now what are the dimensions? We have this tank dimension as 3 meters. So this is 3 meters. Okay. So this is 3 meters length. Now what about the depth of the tank? 2.5 meters depth. Okay, so then this height or this depth, basically here you can say this is 2.5 meters. And width is how much? This dimension is 2 meters. Okay. Now in this, water is filled up to a height of 1.5 meters. Okay, so this total height is 2.5 meters, but this is 1.5 meters. Okay, so you have water filled up to this depth of 1.5 meters. Okay, so this is 1.5 meters. Now they are asking you if this tank is accelerating with some acceleration. So let us suppose this tank is being accelerated. So whenever this tank is being accelerated, then what they are asking you certain things here. Okay, slope of free surface. So tell me one thing first of all, whenever this tank is accelerating in this direction, will this horizontal level stay horizontal? Will this horizontal level stay horizontal? Will this horizontal level stay horizontal? Yes or no? The tank is actually undergoing some acceleration. Then whenever the tank is undergoing some acceleration, then will this level be horizontal? That's my question. No, correct? This level won't be horizontal. Generally, many times you might have experienced this. You generally know water tankers, correct? Whenever you see water tankers, there are two openings here, correct? One opening at the front and one opening at the back. For example, this is the engine part, so cabin. So here there is a front opening and here there is a back opening for filling the water. So many times you might have seen, whenever you are moving at the back, what happens if this tank is accelerating? Look, if this tank is accelerating, this is rear end and this is front. So let us suppose if this tank is accelerating, whenever you go here, definitely there is some chance that water may spill on you. You might have seen this normally. Okay, whenever it's going on a flat earth, This is because of our fluid mechanics explanations. If you do some mathematical analysis for this pressure variation, you will experience that whenever tank is accelerating, I'm sketching it 2D. If you see, whenever a tank is accelerating, the free surface which is supposed to be horizontal, this will take some inclination actually. Okay, the free surface will take an inclination. This inclination will be in such a way that if you take this rotation as theta, then tan theta is given by minus acceleration in the x direction by g plus az is what you have here. Fundamental equation. Normally you can derive that very simple by taking the Euler's equation. You can derive without taking the convective terms of the acceleration and steady terms. You can take just acceleration in the x direction as ax, then you will get this equation that tan theta, line of constant pressure, tan theta will be given by minus ax by acceleration in the x direction divided by g plus acceleration in the z direction. Normally your convention is x is this direction and z is vertically upward direction. Okay, and the width is y direction. Okay, so whenever you take these things x, y and z, then definitely if you can do little mathematical analysis. I'm not doing this in a detailed course, I'll do, but since this is some problem solving session, I'm just using the results. Okay, so tan theta is equal to minus ax by g plus az. Look guys, based on this rigid body motion, there is one very famous interview question they'll ask you. Okay, normally we know one thing. Let us suppose if there is some fluid in a container. So let us suppose if there is some fluid in a container, we know, since if this is incompressible fluid, we know the pressure actually varies in a linear motion, correct? There is some linear increase of pressure at any section. If you take, for example, the pressure increases linearly. Now, can you tell me one situation? They'll ask you this question. Can you tell me one situation where if I take pressure at 2 points like this on the same vertical line, okay? So if I take pressure at 2 points on the same vertical line, the pressure at these 2 points is equal. Can you tell me any such situation? They'll ask you this question. Can you understand from this equation what I have given you? Can you tell me any situation where the pressure at these 2 points on the same vertical line be equal? Can you tell me this? Can you tell me the pressure at both the points, at these 2 points on the same vertical line to be equal? Can you find any situation like that? Can you find any situation like that? So type in the chat box. Can you find any situation like that? Did you all understand the question what I've asked you? Can there be any situation where whenever you have some fluid, the 2 points which are on the same vertical line should actually lie, means the pressure at these 2 points which are on the same vertical line is same? Yes, very good. In the case of where body is rotating, rotation, no. Of course, in case of a rotating body, yes, at the same radius you have same pressure generally, okay? But at the same location, if you see, these two are, even though at the same radius, but these two are at different heights, so pressure won't be same, okay? So the only case is in case of wizard, you told it correct, in case of freely falling bodies, okay? Whenever if I fill a container and if I allow it to fall, then in that case we have a uniform pressure or a constant pressure along a vertical line, because you can see if this az is minus g, okay, z if you take in the z direction, then acceleration in the z direction is equal to minus g, means if the body is freely falling, in that case this denominator will be 0, so theta will tend to pi by 2, okay? So if theta is tending to pi by 2, the water surface will be in such a way that the, means basically this free surface which is here will turn out to be something like this, so it has the pressure uniform at all the directions, okay? So line of constant pressure will be vertical in that case. Clear? And this tan theta is nothing but dp by dz. Slope of constant pressure line is what is nothing but this tan theta, and that tan theta will be equal to minus ax by g plus az, okay? Clear? This is a simple analysis you can do. I'm not doing it now. You have to take a cubical element, then apply force balance on all the 3 directions. You will get this equation, okay? Right now I'm not doing it, but that's how you will get the equation actually, okay? You will actually get this terms. x bar minus del p by rho. This is equal to dv by dt. Okay, so where this is the body force vector per unit mass in my detailed courses I have told, but right now I cannot do this. It takes some 20 to 25 minutes. Okay, so I'm not doing this. This is the constitutive equation. Okay, complete fluid mechanics till viscous flows can be told in one single equation, and that equation is you add the viscous term here plus this property. Kinematic viscosity is very important property. Okay, this is dv by dt. So complete fluid mechanics till external flows can be talked in that one single equation. Okay, if you make the flow is if you make the flow is inviscid, then this viscous term won't be there. Then this is Euler's equation. If you keep the flow steady, okay, means if you keep the flow what do you say, in static condition, then there won't be any acceleration. Then this is the hydrostatic equation. Okay, you will get those equations. Dou p by dou x equal to 0, dou p by dou y equal to 0, dou p by dou z is minus rho g. You will get all these equations here. Okay, now let us see. So anyhow, so if you do that equations, you will get this. Okay, now come back to this question. The tank is accelerating horizontally at 3 meters per second square. So tank moves on the road, of course. So Az is 0. So what about tan theta? First part, tan theta is how much? Tan theta is equal to magnitude of, because they have given acute angle. So sometimes what happened, this angle will be given. Okay, so if you take this as your theta, then you can keep a modulus, because tan theta is nothing but minus of tan 180 minus theta. That's why from little trigonometry you can say, if you want to talk this angle as theta, then just keep as a modulus. Okay, now since here the angle is given something less than 90, so let us take modulus minus 3 ax. Acceleration in the x direction is 3 meters per second square divided by g plus tank actually moves on the road, so that's why this Az will be 0 actually in that case. Okay, so if you see this Az, g plus Az actually, so this Az will be 0. Why I have taken Az is 0? Because tank moves on a road, so whenever it is moving horizontally, there is no z direction transversion for the tank actually. Okay, so that's why we get tan theta is equal to 3 by g. So what about theta? Tan inverse 3 by g. So let us calculate this. 3 divided by 9.81. Okay, so apply tan inverse. Guys, look carefully here. Whenever you are applying tan inverse, you should take care one thing very importantly. The answer is given in degrees. Okay, so the answer is given in degrees. So you should make sure that out of these two buttons, this blue dot is in degrees. Okay, if this blue dot is in radians, you will get some different answer. Okay, so since you want in degrees, keep this in degrees and click tan inverse, then 17.00. So 17 degrees is the correct answer in this case. Okay, so this is 17 degrees. Fine, so 17 degrees is what you have. So slope of free surface is 17 degrees. So first option is correct. Total force on the front side is dash. Okay, so let us see here. Now tell me one thing, if you take this, see carefully here, you have a container like this. For example, let us suppose the container is something like this. Okay, now the free surface, let us suppose, I think some spilling is also there. So let us see here. If you calculate this, for example, from the midpoint, this length of the tank is 3 meters. So if you take a mid plane, for example, at the middle of the tank, if you take a mid plane, then you know this distance is going to be 1.5 meters. Yes or no? Because the tank total length is 3 meters. So if tank total length is 3 meters, then half length of the tank is going to be 1.5 meters. Correct? Yes or no? So please type in the chat box. It is 1.5 meters. Correct? Because what happens? Your surface will take, instead of this shape, your surface will take some different shape like this. Okay, so your surface will take some different shape. It is inclined now. Okay, so this is inclined. It is inclined. Okay, so this surface becomes inclined surface now. Okay, so that's why it got inclined. Free surface got inclined. Okay, so this is 1.5 meters, and try to understand carefully here. So this angle is 17 degrees, which is known to you. So initially, this is 2.5 meters height. Correct? So water is filled up to 1.5 meters. Okay, so water is filled up to 1.5 meters. So water is filled up to 1.5 meters. So this height is 1.5 meters. now this angle is theta, okay, so which is 17 degrees, and this height is 1.5 meters, okay, so this distance is 1.5 again. So can I calculate this distance, yes or no, from simple trigonometry? So from simple trigonometry, this distance is equal to 1.5 times sine theta, correct? Sorry, this is 1.58. So if you take this angle as theta, for example, then second case, let us see, tan theta is equal to, if I take this dimension as x, or let me take one new slide so that diagram will be much clear to you. Fine. Okay, so let us see, I'm drawing some nice big diagram here so that you can see the things clearly. Okay, so fine, this is how there is some fluid level. Okay, initially the fluid level would be something like this, it would have been something like this. Okay, so it would have been something like this. So this height is 1.5 meters. This height is 1.5 meters. The fluid is filled up to 1.5 meters. And this distance, half length of the tank, this half length of the tank is also 1.5 meters, okay, because it's a 3 meters long. So this length is 1.5 meters. So that means this angle is 17 degrees. So if you call this distance x, for example, if you call this distance x, then we have from this triangle, if I call this A, B, C, for example, okay, so if I call this ABC, then from triangle ABC, you can understand one thing, from triangle ABC, tan theta or tan 17 degrees, let us write directly. So tan 17 degrees is x by 1.5. So what about x? 1.5 times of tan 17 degrees. Okay. So what is x actually here in this case? So x, the depression in the case is 1.5 into 17 tan. Okay, so this is in degrees. So 0.45, 0.46 if you take, or 0.458 meters. So this means, now try to understand carefully here, on the right face, okay, so they have asked the force on the front side is dash. Okay, so obviously whenever tank is accelerating, this is the front side and this is the back side. Okay, so if you see the force, hydrostatic force acting on the front side. Now this is a question of hydrostatic forces from here. So if you see, this is the surface, so there is fluid which is acting on this level. Okay, so here if you see, there is some fluid which is touching these points. So what is the area? If you see the side view, then you have something like this. Okay, so if you see the side view of that, you have something like this. This height up to which the fluid is in contact is how much? This is a rectangle, actually it's a rectangular tank, so the fluid is touching a rectangular face on the front side. So height is how much? 1.5 minus this value. So 1.5 minus 0.458, 0.458 meters. Now this side dimension is nothing but width of the tank, correct? So width of the tank is nothing but this dimension, which is 2 meters. They have given you width of the tank is 2 meters. Now what is the expression for hydrostatic force calculation? Hydrostatic force acting on this is equal to, acting on front side is equal to, this is water, correct? They have given you water is filled, correct? It is filled, depth contains water. Okay, so this is water, so density of water into G into area of solid fluid contact. So what is the area of solid fluid contact? 1.5 minus 0.458 into 2. So this is the area of solid fluid contact into, if this is open to atmosphere, then this point is also at atmospheric pressure. So the depth, if this is at free surface, if you treat this as free surface, this is a rectangle. So half of this length is the depth of centroid, which is h bar in this case. Okay, so h bar value is 1.5 minus 0.458 by 2. So let us calculate this value. First of all, they are asking the answer in kilonewtons. Okay, so if you want answer in kilonewtons, you can do this density of water. Okay, so density of water is how much here? 1000. If you take this as 10 cube, then 10 kilonewtons. So what is kilonewtons? This value 1.5 minus 2 gets cancelled actually. Okay, so 2 gets cancelled. So square of this value into G. So 1.5 minus 0.458. 0.458. Okay, so this value, square of this value multiplied with 9.81. So this 9.81 is here. So 9.81. This gives you 10.651. Correct? So did you all get 10.651? So in fins tan HML equal to 1, we can write it. Okay, we'll see what about fins. So are you all getting 10.65 around 10.6? Are you all getting this? Are you all getting 10 point this value 10.6 kilonewtons? So type in the chat box 10.66 kilonewtons, correct? So 10.65 around. I have taken some more decimal, so the second decimal place is changing. So 10.65 kilonewtons. So let us see here 10.65, 10.63. Okay, fine. So because this second decimal will change because of some decimals, so option B is also correct answer. Good. A, B both are correct. Now let us calculate about C. First of all, before calculating about C, tell me one thing. Spill out volume. Look, try to understand here. Whenever this surface is moving parallelly, it is inclined. So if this is 0.45, can you please tell me what is this value? This value, because these two triangles are congruent triangles, correct? They have one angle in common and same side. So these two triangles are congruent, which means this height is also how much? 0.458. Okay, so whenever this is 0.458, tank height, look, tank height is 2.5 meters. So water is filled only up to 1.5 meters. Okay, so whenever water is filled only up to 1.5 meters, you have still 1 meter height empty, correct? So that means by raise of 0.458 meters, will there be any spilling from the tank? So please type in the chat box. Will there be any spill out from the tank actually? Whenever this raise in the fluid is giving you only 0.458 meters, then will there be any spilling out of the tank? No, there won't be any spill out, correct? Spill out will happen if the raise is more than 1 meter, then only there is some spill out. But here if you see, the value is less than 1 meter, so that's why there won't be any spill out from the tank. So first thing is this option D is actually wrong answer. Okay, there won't be any spill out. Let us calculate total force on the backside. Obviously, tell me one thing. The force on the backside, forget about magnitudes. The force on the backside, will it be more than the front side or less than the front side? The force acting on the backside, will it be more than this force acting on front side, or will it be more on the backside? So please tell me, will the hydrostatic force be more on backside, or will it be less than the front side? It will be more, correct? Because there is high amount of fluid solid contact. Okay, so let us see. In that case, hydrostatic force acting on backside is equal to rho W into G into, if you take the side view here, this is 1.5 actually here. Okay, so if this is 1.5, then area of contact is 1.5 plus 0.48, which is 1.958 into 2 into the depth of centroid of this surface will be how much? If you take a side view of this, you will get some larger or taller rectangle, and this is from the free surface. You have h bar at this location. Okay, so this is h bar, which is 1.958 by 2, correct? So this is what you have. Again, if you want in kilonewtons, this rho W you can take 10 cube. So the answer is in kilonewtons if you neglect this 10 cube. Okay, so 1.958 square into G, correct? So let us take that 1.958 square into 9.81. So this gives you 37.6 kilonewtons. 37.6 kilonewtons sound. Okay, so this force is going to be 36.4. 56.4 is coming. 37.6 is coming here, correct? So 37.6. Correct? I hope 37.6 is correct answer, right? We have done the calculation carefully, correct? 1.958 by 1.958 square into 9.81. Okay, so 37.6. Yes, 37.6 should be correct. One then, sir, if there is any spill out, how to calculate it? Yes, I'll tell you. Look, how to calculate the spill out? I think there is one question on spill out. I think I've kept one question on spill out. Yeah, the percentage of water spill over. Okay, we'll do that. Okay, so we'll see how to calculate the spillover in that question. Okay, so right now let us try to understand this. 37.6 kilonewtons is the correct answer. Okay, so let us check the options. This is how much they have given you, 15.6, only half of that is given. Okay, so this is wrong. Guys, please be careful with these values. Okay, sometimes when you miss 2, 3 in the denominators, these values will change. Okay, so C is wrong answer. So A and B are the correct answers in this case. Okay, so this is a very good question. It involves concepts of rigid body mechanics, I mean rigid body fluid motion, and also it involves concept of hydrostatic forces. Okay, fine. So one of our friend has one doubt. So in fins, tan HML is equal to 1. We can treat it as a long fin. How to get ML from calculator? Please show. I was getting error. Okay, so normally when you do this calculation, ML root HP by K into L. So you can get this calculation easily if you do carefully. Okay, clear? Whenever it's a long fin, generally yes, ML greater than 5 generally. Okay, so whenever ML is greater than 5, you can take it as a long fin. I think Sandeep Chandrakar sir will talk it better on the other day. Tomorrow we have some heat transfer questions. Then definitely you can experience some questions of fins. Okay. Okay. Fine. So let us see. Okay, this question we have solved. So A, B are correct answers. So this is one very good question. So let us try to solve this. Normally you might not have seen this question till now, unless you attended my full course. But normally you might not have seen this. A solid cone of angle 2 theta, base radius r0 and density rho c is rotating with initial angular velocity omega inside a conical seat. Okay, so there is a conical seat inside which a cone is rotating. The clearance h is filled with oil of viscosity mu. The mass of the cone is m. Neglecting air drag, the analytical expression for the cone's angular velocity if there is no applied torque. So they have given you certain expressions, 4 expressions they have given you. Okay, tan HML value. Okay, so I'll tell you tan HML value, how do you calculate, is by this expression. Okay, so tan HS function, you will write this function as this. Is how you get the tan hx function. Okay, so when x value is ml, you keep ml value in all these functions and calculate. Okay, for example, if ml is 2, okay, so let us suppose, then e power 2 minus e power minus 2. Okay, so that's how you get, plus e power 2 plus e power minus 2. Okay, so this is tan h2 value. Okay, so that's how you get the tan h function value in calculator. Clear? This is the function, tan hs function. Now let us solve this question. You might have seen torque acting on a cone, some formulas, pi mu omega d power 4 by 32c, whatever. Now here this question is, try to understand this. First of all, let us see. Okay, fine. If this is your cone, okay, now this cone has some axis. Okay, so this cone has got some axis here. So this is the axis of the cone. So initially this cone is revolving at some angular velocity omega naught. Okay, so this is rotating at some angular velocity omega naught, and this base radius is how much? This base radius is known to you. This base radius value is how much? This is r0. Okay, so the base radius is r0. Now this cone is in a conical seat. Okay, so this cone is in a conical seat like this. So there is some conical seat. So there is some conical seat. So in this conical seat, there is some viscous oil which is filled. There is some viscous oil which is filled. And there is some viscous oil which is filled in this cone. Okay, which is filled in this seat. There is some viscous oil which is filled in this conical seat. Okay. So whenever you have this conical seat, they have given you this thickness of this oil film is H. Okay. Now they are asking you, when this cone is rotating without any external torque, okay, initial angular velocity is omega, then what happens? Because of this viscous effect of the oil which is present, this cone will the angular velocity of the cone will slow down, correct? The cone will actually slow down. Okay, the angular velocity of the cone reduces. They are asking you, what is the variation of angular velocity with time? Clear? Did you all understand the question? What they are asking you? Initially the cone has some angular velocity of omega naught. Now whenever the cone is evolving at some angular velocity of omega naught, they are asking you what should be the variation of angular velocity with the time in this case. Clear? Did you get what they're asking you? Yeah, we can take a small step, of course. Okay, so let us see. First of all, I want to ask you one thing. Normally, if you take the angular momentum equation, this cone is a rigid body. So for rigid body, cone is a rigid body. So for a rigid body, we know net torque acting on this is equal to I times of alpha. Now, there is no external torque that's acting, but on this cone, there is torque due to one thing, correct? What is that? Because of the viscous effect of the fluid, correct? Yes or no? Now, whenever the cone is at any moment, let us say at any instant, let us say at a instant, let omega be angular velocity of cone. Okay, so let omega be angular velocity of cone, for example. Okay, now if this is angular velocity of cone, then whenever the cone is evolving at angular velocity, let us suppose if this oil has dynamic viscosity of mu and this cone has a base radius of r naught and this total cone angle is 2 theta. So this half semicone angle is theta, correct? Because they told cone angle of 2 theta. So that means this semicone angle is theta. So whenever the semicone angle is theta, so please tell me, what is the torque acting on this cone? What is the torque that is acting on that cone? Any idea? How do we get that? You might have seen, correct? Conical shaft or shaft evolving in a sleeve. Then conical shaft evolving in a sleeve. Have you seen these questions? How many of you have seen these questions? Look, I'll try to explain you. So if you want to calculate torque acting on the cone due to viscous effects of the fluid, torque acting on cone, is equal to, okay, so torque acting on the cone is equal to, first of all, T. Let us suppose if this is T, then this T, if you see the points of solid fluid contact, okay, so these are the points of solid fluid contact. So these are the points of solid fluid contact. Now, these points of solid fluid contact are not at a constant distance from the axis of rotation, correct? Normally, if you take, for example, a pipe, and if the pipe is rotating, then all the points on the surface of the pipe where the fluid is getting in contact, all these points are at some uniform radius from axis of rotation. But in case of cone or any tapered shafts, these points of contact are not at same location, are not at same radius. Okay, for example, the radius at this location will be something different, the radius at this location will be something different. Then how do you do that? Okay, so see, for example, if you take small elemental strip, okay, so if you take small elemental strip, for example, then in that case, let us see, in that case, so let us say this distance is r, and this excess distance here is dr, for example. Okay, so there is some small increase of dr, you take some small section. Okay, sorry, 2 pi mu omega r power 4 by sin theta. Okay, there is some formula, we'll see. Okay, what is that formula? So now if you see, this is dr. Now whenever this is dr, let us say this length, slant length is dl, for example. Okay, so this slant length is dl, small slant length. Now if you see, the small elemental torque acting on that small part is small elemental force into radius. Okay, so small elemental force into radius, because force into radius gives you torque. Okay, so what about small elemental force? Shear stress acting at that point into small elemental area into smaller. So this is tau into, now what is the area of solid fluid contact actually? This is like some small part of the first term. So if you want to calculate the area of contact which is in contact all over the 360 degrees, if you want to calculate the area which is contact with fluid, then this area is 2 pi r multiplied with dl, correct? So 2 pi r multiplied with dl gives you r. Now what is the relation between this dr and dl? So let us see, dr is something like this and dl is this. Now if you observe carefully, this angle is theta. So what about sin theta? Sin theta is dr by dl actually here. Okay, so sin theta is dr divided by dl. Okay, so opposite side by hypotenuse. So dl can be written as d small r by sin theta. Okay, so whenever you have this d small r by sin theta, then if you replace here tau into 2 pi r into d small r by sin theta into small r. Okay, so if you see, what about tau? Tau can be written as, from Newton's law of viscosity, mu into velocity gradient. Okay, so what are the velocity of these points which are in contact here? The velocity of the points which are in contact at this location is nothing but this radius is r and cone is revolving at angular velocity of omega. So velocity is r times of omega by the clearance. Okay, so the clearance at any section is h. Okay, so we have seen the clearance is h actually. Okay, so r omega by h. So whenever this is r omega by h into, so this is shear stress from Newton's law of viscosity, tau is mu into velocity gradient. So r omega by h into 2 pi smaller into dr by sin theta into smaller actually. Okay, so here the only variable we have converted is in terms of smaller. Okay, so let us take one slide again. So let us see here. So when you see this dt, the small elemental torque acting on the cone is equal to how much? The small elemental torque is equal to mu omega 2 pi h sin theta. These are constants, correct? So 2 pi mu omega h by sin theta, 2 pi mu omega by h sin theta. These are constants anyhow, into, now 1, 2, 3, we have 3 small r's here. So 3 times of small r, which is r cube d r actually. Okay, so therefore complete torque acting on the cone is r is equal to 0 to capital R, this constant which is here 2 pi mu omega by h sin theta into small r cube dr. So what about torque here? T is equal to, then in this case what about capital T here? If you integrate this, this is a constant 2 pi mu omega by h sin theta into this integration of r cube is capital R power 4 by 4. Okay, within the limits 0 to capital R. So if you solve this expression, we get this 2 cancels out 2 times. So T can be written as pi mu omega. Here it is r naught because the outer radius, base radius is r naught at the final stage. So small r naught. So pi mu omega r naught power 4 by 2h sin theta. Okay, if you convert to diameters, you will get 32 here, correct? Because d naught by 2 gives you 2 power 4 in the excess, and that gives you 32. So this is the net torque acting on the cone at any given speed, okay, at any given instant. Okay, now, so did you all clear? Are you all clear with this equation? Did you all understand? Whenever there is some conical shaft rotating in a sleeve, then the torque acting on the cone is given by this expression, pi mu omega r power 4 by 2h sin theta. H is clearance. Okay, yes or no? So please type in the chat box. Is this clear to you? Everyone should type in the chat box, all of you. So pi mu omega r naught power 4 by 32 h into sine theta. Clear? I mean, here if it's radius, then it is 2. If it is diameter, then it is 32. Yes? So is this clear to all of you? Now, normally from your rigid body mechanics, you know, so tau is equal to I alpha. Okay? So tau is equal to I alpha. Tau is equal to I alpha. So whenever cone is rotating, there is this torque from the fluid acting on the solid, correct? So because of this torque, what's happening? The cone is actually getting slowed down. Okay, so if I write this expression, pi mu omega r naught power 4 by 2h sine theta is equal to I, moment of inertia. So what is the moment of inertia of the cone about its axis? So moment of inertia of the cone about its axis is 3 by 10 mass of the cone into r naught square. Okay, the base radius square. This is the moment of inertia of the cone. You can derive it actually, but I'm taking the value for now standardly. Okay, in engineering mechanics course you might have derived this. Okay, when you calculate moment of inertia of solids, you can easily get that equation by simple integration. Okay, so 3 by 10 into mr square into alpha is d omega by dt. Now in this equation I have to correct only one quantity. What is that quantity? So please tell me, type in the chat box. In this equation I have to correct one thing. Yes, very good. This is resistive torque, correct? Very good. So we have to keep a minus sign here, correct? There comes a minus sign because this is resistive torque. Okay, because the cone is trying to rotate, but this torque is actually trying to oppose the motion. That's why it is resistive torque. You have to keep a minus sign here. Clear? So 3 by 10 m r naught square. So here we get a differential equation. So if you see, minus pi mu, okay, this is 5 actually. Okay, so we have 5. So minus pi mu omega, omega is not constant, it's a variable. So r naught power 4 into 5. So we have 5 here. So minus 5 pi minus 5 pi mu r naught power 4 by 3 h or m h sine theta, 3 mh sine theta is equal to into r naught square. Okay, so divided by r naught square. This is what you have here. Okay, so is equal to into omega is equal to d omega by dt. So here in this case, if you see, r naught square will cancel this r naught square. So if you see, if you solve this differential equation, it can be separated to variable separables. So minus 5 pi mu r naught square by 3 m h sine theta into dt is equal to 1 by omega d omega. Okay, so you want this relation. The retarding angular acceleration will not be constant as omega is decreasing, which leads to decrease in torque, correct? Okay, so which leads to decrease in torque. That's why it's a differential equation. We never took omega is constant, correct? Yes, that's why if you see, if you integrate this expression and you have this is a constant, mu is constant, r naught square is constant, mass of the cone is constant, clearance is constant, cone angle is constant. So if you integrate this, when time t equal to 0, initially this omega is equal to omega naught. Okay, at time t equal to some time t, this angular velocity is omega of t. So from this you can write omega of t is equal to omega naught into e power, which is exponential of this quantity, which is minus 5 pi mu r naught square by 3 mh sine theta. Okay, this is the equation. So this is how the angular velocity of the cone changes. Okay, and this is a negative exponential function. So that's why as time increases, angular velocity of the cone comes down and finally it comes to rest. Okay, so that's how we have this equation. Clear? So this is the expression for the, and t is also there. Okay, so e power t is also there because integration gives you t here. So t is also there. So as time increases, this velocity of the angular velocity of the cone keeps on decreasing and finally it comes to rest very soon. Okay, so let us check where is this option. Omega is equal to, so let us see, omega is equal to omega naught. Okay, we have x power. So let us shortlist some quantities. We have r naught square. Okay, so let us see here. We have r naught cube, which is wrong here. We have r naught square and r naught square. Okay, good. Then we have sine theta, but here we have tan theta. So tan theta is wrong. So out of these two options, 3mh sine theta, 5 pi. Pi is there, correct? So we got a pi. Okay, so pi should be there. So here there is no pi. So that's why it is wrong option. So A is correct answer in this case. Okay. Clear? So we have, didn't saw the sign in the question. Sign should be there, right? It should be negative sign. Okay, because as time increases, angular velocity should come down because the torque is resisting torque. Okay, that's why. Clear? So are you all thorough with this question? So please type in the chat box fluid and its properties, first chapter, hopefully. Okay. Yeah, good question. Correct. Because normally, if you encounter questions with fluid mechanics, you experience these questions up to this point. Okay, they are interested to show you how the torque calculation comes out. Okay, but this torque, so this is two concept, basically some combination of two things. Like one is your engineering mechanics, rigid body mechanics, angular momentum principle, and one is fluid mechanics where you have calculated torque. Clear? So how many of you have liked this question? So please type in the chat box. How many of you felt this is a good question? Because normally you might have experienced it till this point. Okay, this is something further. So type in the chat box. Is this clear to all of you? Yes or no? Okay, fine. I hope it's clear. Now let's go for the next question. So let us see. Yeah, some of you is asking about turbo machines you will teach. Yeah, I haven't taken a detailed course, but very soon maybe I'll start some questions. Okay. So see, an open rectangular tank, 6 meters, 4 meters by 3 meters, meter cube deep, 3 meter cube. Okay, so this is 3 meters deep, contains water up to 2 meters depth. The tank is subjected to a horizontal acceleration of 3.9 meters per second square along the longer side. Of course, along the length. The percentage of water spill over. So previously some of you asked how to calculate spillover. So that's we'll see. Okay. So you will do turbomachinery questions. Yes, we have some basic type of turbomachinery questions here. Okay. So we'll try to solve them, which are very familiarly asked in GATE examination. Okay. I'll give you some intro of turbo machines. Okay. No issue. Because this is a long session anyhow, so we'll spend some time on each and everything, each and every doubt of you. Okay, so let us see this. First of all, there is one tank again. So there is one tank. There is one tank actually. Okay, now initially the water level could be something like this. Initially the water level could be something like this. Now if you see, since the answers are more than 0, because of acceleration of the tank, they have got some water level in this direction. Okay, so let us suppose they've got some, if this is midpoint for example, then somewhere it is touching here, and let us say for example this is going like this. Okay, fine. So some part of the water is spilling out. Then in that case, if this angle is theta, so first of all, how do you calculate theta? First of all, let us write the dimensions. So this value is how much? The length of the tank is how much here? Length of the tank is 6 meters. So this is 6 meters. Length of the tank is 6 meters, and this height of the tank is 3 meters. Okay, so height of the tank is 3 meters initially. So this height is 3 meters. So this initial depth of water is 2 meters. Okay, so initial depth of water is 2 meters in the tank. Now the tank is subjected to a horizontal acceleration of 3.9 meters per second square. So in this longer side we have acceleration which is 3.9 meters per second square. Okay, so this is 3.9 meters per second square. Clear? So I hope it is clear. So 3.9 meters per second square. So whenever this is 3.9 meters per second square, let us see. Let us try to solve this. So tan theta, we know tan theta is magnitude of minus ax by g plus az is what we have here. Since this is a tank moving horizontally, so az is 0, no acceleration in the z direction. This is x direction. Okay. So tan theta is equal to, how much is this? Magnitude of minus acceleration in x direction 3.9 divided by 9.81. Okay. So theta is almost, how much is this? 3.9 by 9.81. 3.9 by 9.81. Okay. So we got this value 11.4. So take a tan inverse of that. Tan inverse 21.7 degrees almost. 21.68. Okay. So 21. Okay. Tan increases very fastly. So let us take 68 degrees. Better. So if this is 21.68 degrees, now what is the depression in the water level? Let us take. So what is the depression in the water level? This depression x, for example, if this is 3 meters, okay. So if this is 3 meters and if this is x, then let us say 21.68%. Okay. 21.68. Okay. So almost 20%. Okay. So let us see. First of all, okay, this theta value you are telling. Okay. Theta is 21.68. Correct. Yes. Theta is 21.68. Okay. So now what about x? X is equal to tan theta into 3. Correct. So x is equal to, let us write here, x is equal to tan theta into 3 meters. Okay. So we have 3 meters here. So from this simple triangle, x value you can calculate. So x is equal to, so this is angle. So tan of this angle 0.39 into 3. So 1.1926. 1.1926 meters. 1.1926 meters. Now, whenever x is 1.1926 meters, definitely the rise on this side will also be 1.1926 meters, correct? But the tank is available only up to 1 meter height because this is only 3 meters. So if fluid rises beyond 3 meters, then definitely there will be some spillover. So in this question, we know one thing, definitely there is some spillover of fluid, but we don't know what is the amount. Okay, we'll see. Now, let us see. Yeah, I don't know. I have to solve Midun. Okay, so let's wait for some time. We will know the answer. So now observe carefully. There is a tank like this of some height. There is a tank like this of some height. Now in this tank, your fluid level is trying to come out something like this. Okay, but your tank is only up to this portion. Okay, so tank is only up to this. Tank is only up to this portion. And here initially the midline of the flow or the fluid, the free surface of the fluid is something like this. Okay, so the free surface of the fluid is something like this. Initially it is at 2 meters or something. Okay, so initially if it is at 2 meters, then there is some spillage. Okay, so this is the volume of fluid which is spilled over. This is the volume of the fluid which is spilled over. Now how do you calculate this volume actually? Okay, so how do you calculate this volume? Look, this angle theta is known to us and this height is also known to us. The only thing that you should know to calculate is this length. Okay, so if you know this length, then you can calculate this very easily. Yes or no? So please type in the chat box. If you know this length which I have marked here, if you know that length, then you know the area of that triangle of the fluid which is going out, which is getting spilled over. If you multiply that with width of the tank, then you can easily understand. Yes, did you understand how to calculate the volume which is spilled over? This fluid, whatever I have shaded, this will definitely spill over the tank, right? Because tank already got filled at that location. Yes or no? Correct? So please type in the chat box. Can I say this? All of you. So please type in the chat box. Can I say this? Yes or no? Just no need of big equations and all. Just focus on simple things. You will easily get that. Okay. Here, if you see, we know this distance, which is 0. Because the elevation, total elevation is how much? This total elevation is 1.192 meters. Okay. So this is this length, which is here, is this is 0.192 meters. Okay, so this is 0.192 meters. But theta is constant actually. If this angle is theta, this angle will also be theta. Correct? So this small angle here will also be theta again. Okay, so if that's theta, then we know at this midpoint, this distance or this length is how much here? Half length of the tank, 3 meters. Okay, so half length of the tank is 3 meters, and this is 0.192, and this total value is how much actually? So see carefully here, what is this total value here? What is this total value? This is 1 meter and this is 0.192 meters. Okay, so we know from similar triangles or from trigonometry, anything you can write. From similar triangles, we know if this value, if I take it as y, then y by 3 is equal to 0.192 divided by 1.192. Okay, so we will get y value here in meters. So we will get y value in meters actually here. Okay, so y value will get in meters. So if you get y value in meters, then 3 times of, so let us store this value for example. So 3 into this recollect minus 1. Okay, so 0.192 something divided by recollect. So 0.4846. 0.4846 meters. Okay, so therefore percentage of volume spilled is equal to this volume which is spilled, half times of 0.192 into this y we have calculated 0.4846 into width of the tank w, let us say for example. Okay, so width of the tank is w divided by what is the actual volume in the tank? Actual volume in the tank is, initially it is of 6 meters and 2 meters height into width of the tank. So this is the fraction multiplied with 100. So this gives you the correct answer in this case. Okay, so if you do this calculation, then width and width gets cancelled. Then okay, then let us take a calculator. You will get the answer in percentage. Okay, so this is the percentage of water which is spilled over. So if you perform this calculation, 0.4846, yeah, this value multiplied with 0.192 into 100 into 100, this divided with 2 into 2, 2 to 4, 4 6 is 24 actually. Okay, so divided with 24, 0.38. I think I have messed somewhere, so please check this calculation once. That y by 3 is equal to this, y by 3 is equal to 0.192 by 1.192. So y value is correct. All of you type in the chat box, is y value correct here? Yes or no? Y value is correct here, yes? Did you all get 0.4846? So please help me with the calculation here. 0.4846, correct? Yes or no? So please type in the chat box. Percentage of volume which is spilled is, you are getting around 9.89%. So please check this calculation. Y is correct. Yes. Okay, y is correct. So if y is correct, then volume spilled is how much? Half into this value which is 0.192 is the amount of this triangle height, and base is 0.4846 into width, whatever is the width of the tank that is available, divided by y value is correct, right? So divided by total volume initially is, this is a 6 meter tank and 6 into, there is 2 meters depth actually here. So 2. So this is 2. So 2 into width into 100. So is this calculation clear? Yes or no? So please type in the chat box, is this calculation clear to all of you? Into 100, correct? So y value is correct. So percentage of volume which is spilled. So this amount of fluid which is here will get spilled over the tank actually. So half times of this triangle, 0.192 into 0.4846 into width divided by 6 into 2. Initially the fluid is filled up to a depth of 2 meters. So 6 into width into 2 into 100. Yes. 0.4844, correct? Yes, all of us are getting 0.4844, right? Chandan, how did you get 9.89? Any issue with the calculation? So please check. Because whenever the pressure, whenever the line actually shifts like this, then this is the amount of fluid which gets spilled over the tank. correct? So 0.4832. The leftmost part of the water should have height of 3 meters. 0.38. Leftmost part of water should have height of 3 meters. Yeah, this is of height 3 meters. Okay, fine. Correct. This is 2 meters and this is 1 meter. So we are not calculating this part of the fluid. Okay, we are calculating only the shaded part of the fluid. We are calculating only shaded part. Correct? Point 192 meters means almost some 19 centimeters of the fluid is actually at that point. Okay. So 0.38 is correct answer, correct? So let us confirm this. So when you do this calculation, 0.38. Okay, where is this calculation? So this is anyhow 2 6 are 12, 12 6 4 6 are 24. So 0.192 into 0.4846, 0.4846. Okay, so this value by 24 into 100. So 0.38% is what you're getting. So 0.38% of the fluid is getting spilled over the tank. Spilled percentage. The change in final to initial to final of water gives the spill percentage. Here they have asked the percentage of water spill over is dash. Okay, so the percentage of water which is spilled is basically this, right? How do you calculate percentage? Normally something which is lost by total which is available into 100. Look, this part of the water will stay in the tank. Okay, this part whichever is not shaded but in between is will lie within the tank actually. Correct? Because theta after coming to that particular location it will stay constant. Okay, so fraction is 0.38%. Correct? If they ask you whatever is the portion that is remaining and all, then things will change, okay, relatively. But here they've asked just what is the portion, what is the fraction, or what is the percentage of water that is spilled out. That is nothing but this calculation. Okay, so 0.38%, because obviously you can see clearly this is a large tank of 6 meters. 6 meters is certainly large, but this height is only 10 centimeters or hardly 20 centimeters. Okay, so 20 centimeters when you compare with 3 meters is very small in that case. The spilled height is 0.1926. Yes, of course, this is 0.1926. So percentage of volume spilled. Look, whatever you're telling is relative value, okay, but this value is actual value, actual volume of water which got spilled. Okay, whatever you're telling, total volume minus spilled volume gives you the fraction or the percentage of water which is inside the container. Okay, but this value what I'm writing is the volume or the percentage which is spilled over. Correct? This value, look, whatever the value you're writing, 6 into 2 into width minus half into this 0.192 into 0.464846 by 6 into 2 into W. This gives you the percentage of water which is lying in the container. Okay, but whatever is spilled is this percentage. Correct? This is because whatever is left in the container after after spilling out, whatever is the percentage that is left inside the container is this value. But they are asking you what is the percentage of water which is spilled over. Okay, so spilled will be obviously, so the left part you're taking is horizontal. Yes, of course, the left part is horizontal, correct? Because up to this, whatever this rise is there, this is still in the fluid, still in the tank. Okay, tank is up to this yellow line limit. Okay, so whenever tank is up to this yellow line limit, only this is the shaded part which is going out. Okay, this fluid is rising above the free surface level, but still it lies inside the tank. Correct? Did you understand what is this calculation giving you? This calculation gives you the percentage which is left in the tank after spilling over. Okay, because this is the spilled out volume into width, of course. Okay, so when you multiply into width, then this is the spilled out volume. Then this portion is which is left inside the tank actually. Okay. So percentage which is spilled out is less than 1%, which is 0.38% in this case. Clear? Fine. So 0.38% is the correct answer in this case. Fine. So let's go for the next question. So let us solve this question. The water level in a tank is 20 meters above the ground. Okay. So there is a water level which is 20 meters above the ground. A hose is connected to the bottom of the tank as shown in the figure. The tank cover is airtight and the air pressure above the water surface is 2 atmosphere gauge. Okay, so this is 2 atmosphere gauge pressure. So here the free surface of the water, maybe because of some compressed air or something, the pressure at this location is 2 atmosphere gauge. Now the system is at sea level. Of course the system is at sea level. So that means here the pressure, its opening pressure is PATM local. Then the maximum height to which the water stream could rise is dash. So because of this tank, then whenever there is some outlet to this tank, actually fluid is coming out and it reaches to the maximum height, correct? So they are asking you what could be the maximum height of the fluid that could be reached by this because of this particular configuration. Okay, so how do we calculate this? Look, try to understand. If there is no loss, for example, then in such case whatever is the total energy available for the fluid here, same should be the total energy at this location, correct? Yes or no? Because this is open to atmosphere, so this point is also open to atmosphere. So here also the pressure is PATM local. So whenever this is PATM local, whatever is the total energy per unit weight of the fluid that's present at this point, same should be the total energy available per unit weight at this point. Yes? Yes or no? So type in the chat box. Is this clear? I'm telling you, whatever is the total amount of energy at this point, the same energy should also be available here if there is no loss. Yes. So if I take this point 1 and if I take this point 2, then let us apply Bernoulli's equation between the 2 points. Applying Bernoulli's equation, between points 1 and 2 actually here. Okay, so between points 1 and 2, this implies, of course, steady state and fluid is water, for example, incompressible fluid. So if you take this P1 by rho z plus V1 square by 2z plus Z1 elevation is equal to P2 by rho z plus V2 square by 2z plus Z2, correct? Now let us take, for example, this as the datum. Okay, so if you take this as datum, for example, at this point, okay, so if you take this as your datum, now at this location pressure is 2 atm gauge. What is the meaning of this? It is 2 atm more than the atmospheric pressure. Okay, so therefore we can see this P1 value is 3 times of atmospheric pressure. So 3 times of PATM local by rho z plus V1 square by 2z. So please tell me one thing. Whenever this is a large tank, for the discharge happening here, can I say the level of the fluid fall will be very small? Yes or no? It's a large tank. So whenever this is a large tank, for the fluid which is coming out like this, then this level will actually come down with very low velocity, correct? So whenever this level is coming down with very low velocity, I can take the velocity of the particles at this section. The velocity of the particles at this section is 0. So plus Z1. So what is the elevation? It is at 20 meters elevation. So 20 is equal to P2. So at this location, the pressure is again atmospheric pressure. So PATM local by rho z plus V2 square. So tell me, at the maximum height of the projectile, or it's not projectile, sorry, at the maximum height of the projection, what could be the velocity of the fluid here? Here the fluid has kinetic energy. So complete kinetic energy got converted to potential head. So at that highest point in the vertical motion, what could be the velocity of the fluid? So please tell me. one thing is very clear, the velocity keeps on reducing, correct? Because the kinetic energy available with the fluid gets converted to potential energy. So whenever things gets converted to potential energy at the maximum location or at the peak height, what is the velocity of the particles? What is the velocity of the fluid at that condition? So type in the chat box, what is the velocity at this location? 0, correct? It is 0. Very good. So V2 is 0. So V2 is 0 plus Z2. So what is this Z2? H. Okay, so elevation is H. What is the H value? So the maximum height. Okay, so we have to calculate H. Get. So H is this value. So what about H? H is equal to 20 plus 2 times of PATM local by density of fluid, which is water here in this case, water into gravity. Okay, so let us compute this value. H is equal to 20 plus 2 times of atmospheric pressure is 76 centimeters of Hg, or if you take 101.325 kilopascals, 101.325 into 10 cube pascals by density of water. Did they give any quantity? No, they haven't mentioned anything. So let us take 10 cube by default into 9.81. Okay, so this value is 9.81 here. Okay, so if you make this calculation, 10 gets cancelled. So height up to which this can rise is in meters. If you take this, so H is equal to some meters. So 2 into 101.325, 2 into 101.325 divided by 9.81 divided by 9.81. Okay, so 20.657 plus 20, which is 40.657, 40.657, so 66 meters. Okay, so 40.66 meters is what you can directly get here. So 40.66 meters, so 40.7 close. If you round off to single decimal, then 40.7 meters is the level up to which the fluid rises, which is coming out of a nozzle. Okay, so simple question. Look, whenever you are applying Bernoulli's equation, first thing that you should take into consideration is the datum. If you take your datum correctly, then majority of your calculation gets eliminated. So why did you take 3 in this PATM in this equation? Because they have told me that the tank cover is airtight. Means if you see, there is some air which is tightly packed here. Okay, the air pressure above the water surface is 2 atm gauge pressure. Okay, so what is the meaning of gauge? It is 2 atm more than the atmospheric pressure. Okay, so if you take atmospheric pressure as PATM, then the pressure at that location is 2 atmosphere pressures more than a atmospheric pressure. So total 3 atm is the pressure at that location. Okay, Anims, is it correct? So, I mean, sorry, did you understand this? Is this clear to you? Did you understand how the answer is actually, how the pressure at this location is 3 times of atmospheric pressure, because it is 2 times of gauge. Okay. In hydrostatics, you might have seen gauge pressure. Whenever some gauge pressure is given to you, if you want to calculate absolute pressure, add the local atmospheric pressure to that. Okay. So that's what from simple hydrostatics equation. So let us solve this question. Water is to be delivered from a reservoir to a pipe to a lower level. Okay, discharged into air. So it is discharged to atmosphere as shown in the figure. If the head loss in the entire system is 11.58 meters. Okay, so total head loss is 11.58 meters. Then the vertical distance between the point of discharge and the water surface in the reservoir. Okay, so if you see, they're asking you about these points. This is one point, for example, and this, for example, is another point, or generally this is some other point, for example. Then the vertical separation between these two. Okay, they're asking the vertical separation between these two. So they're asking you a vertical separation between these two, H, for example. Okay, so vertical separation between these two, H. Okay, now let us see how to calculate this. So see how to calculate this. Water is being delivered, okay, between the points. So they want this H. So again, let us apply the Bernoulli's equation, but this time there are losses actually. Okay, so let us see point 1, and for example, let us take point 2, and datum. Let us choose one datum such that one of the elevation becomes 0. Okay, so this is, for example, your datum. Okay, So whenever this is your datum, then fine. Okay, so this is your datum. So if this is your datum, then Z2 is 0. Okay, here I have intentionally choose that datum because my Z2 becomes 0. I might have taken some other place also, but Z2, I want to make one of my maximum possible terms of the Bernoulli's 0. So I have taken one datum there. Okay, now if you see, apply Bernoulli's equation, apply Bernoulli's equation, Bernoulli's equation between points 1 and 2. Points 1 and 2. So P1 by OZ plus V1 square by 2Z plus Z1. So this is total energy available at the fluid with the fluid per unit weight. Okay, so this is equal to, now here this is the total energy available. Similarly at this point, P2 by OZ plus V2 square by 2Z plus Z2 plus, now try to understand one more thing. Here there is some head loss that's already given. Okay, so whatever is the energy available with the fluid, that energy is equal to energy available at this point plus the losses which are at this path. So HL, head loss. Okay, now let us, when to consider exit loss. There was ambiguity in GATE 2021 XC paper also. Look, whenever they ask you to consider minor losses, you have to consider. If nothing is mentioned, you need not consider. Okay, let us suppose if they mention statements like consider all the losses, things like that, then you have to consider. If nothing is mentioned, you need not consider. And also you need not what do you say, you need not consider if they ask you to say, if they say you that minor losses can be neglected. Okay, in these both cases you need not do that. Okay, so if you see, let us try to identify some things. First of all, at this location it is a free surface open to atmosphere. Here also it is given, it is discharged into air, means free surface. Okay, so it is discharged into atmosphere. So please tell me, can I say P1, P2, both these values are equal? Yes or no? P1 and P2 values are same and both are equal to atmospheric pressures. Can I say this? Yes or no? So please type in the chat box. Can I say that P1 and P2 are same and both are equal to atmospheric pressures? Because here the fluid is open to atmosphere and here also the fluid is being discharged to atmosphere. Correct? So can I say this? Yes or no? Type in the chat box. Come on. The reason is, here it is open to atmosphere. There is some air acting here, and here the discharge is also into the atmosphere. So that's why P1 and P2 are same here. Okay, so that's why P1 is same as P2, which is P atmosphere, because the discharge is open to atmosphere. Okay, so these two terms gets cancelled on both the sides. Next, here it's a tank. So for the small discharge that's happening to a 50 mm diameter, so almost some 5 cm diameter pipe. So if you take this tank as a large tank, then for the discharge which is coming out, this velocity of the fluid level which is coming down will be very small. Correct? So whenever the velocity of the fluid level coming down is very small, what is the value of V1? So please tell me, what is the value of V1 here? What is the value of V1? The tank is large, so the fluid level is coming down very slowly. So whenever the fluid level is coming down very slowly, the particles at the interface has very slow velocity. Yes or no? So what can I take for the value of V1 here? Type in the chat box. 0, correct? So if I take V1 0, then this term is 0. Then Z2, I have taken this as the datum. So when I take this as my datum, then this Z2 is also 0 basically here. Okay, so Z1 is nothing but this elevation, and that's what exactly we want. Okay, so this H is equal to Z1 and this Z1 is H, and we want the value of H from this equation. So let us do this. H is equal to V2 square by 2Z plus head loss. V2 square by 2Z plus head loss. Okay, so what is this H value? V2 square. So V2 square is nothing but the velocity through this pipe. Okay, so the velocity through this pipe, this velocity through the pipe can be written as discharge by area. So let us see. This V2 square can be written as V2 is 4Q by pi d, because it is flowing through some small pipe. So V2 square is 16 Q square by pi square into, there is a square here, so d power 4 by 2z. So you have 2z multiplication plus head loss. Now You know the head loss they have given you. Total head loss in the system is how much? They have given you some value 11.58 meters. Diameter of the pipe is known to you. Discharge is also known to you. So let us calculate the value. So if you calculate this, H is equal to 16 Q square. What about Q? 0.00631. So 631 or 6.31 into 10 power minus 3. So 6.31 into 10 power minus 3 whole square. This is discharge square by pi square into d power 4. So what is diameter? 50 mm. So 50 into 10 power minus 3, which is 5 into 10 power minus 2. Okay, 5 centimeters. So 50 into 10 power minus 2 meters. So 5 into 10 power minus 2 power 4 by 2 into G 9.81. Okay, so all the units are in SI units, correct? Let us check meter cube per second, meters per second square plus head loss. So what about this head loss? 11.58 meters. So this is 11.58 meters. So if you calculate this, this is 10 power minus 8, this is 10 power minus 6. So we can do one thing. This 10 power minus 6 and 10 power minus 8 gets cancelled, and we can write a 10 square here. Okay, so 2 cancels out this 50 times. Then 5 power 4 is there. Okay, so let us take a calculator and let us get this value, meters. So this is in meters. So let us calculate this value. 16 into 6.31 square. 16 into 6.31 square. Okay, so 16 into 6.31 square into 50 into 50 into 50. Okay, into 50 divided by pi square into 5 power 4. So what is 5 power 4 value? 5 power 4 is 625, correct? 25 square. So 625 into pi square. First of all, oh, I think I have eliminated that. 16 into 6.31 square. Okay, so 16 into 6.31 square into 50 into 50. Okay, so this value divided with this 5 power 4 is 625 into 9.81. 625 into 9.81 into pi square Okay, so this value gives 0.526 plus 11.58 plus 11.58. So 12.106. 12.106 meters, correct? So did you all get 12.106 meters? Yes, 12.106 meters, correct. Okay, so 12.106 meters. Normally when you're doing this pi square, okay, taking these powers into consideration or typing zeros in this calculator, you should be a little careful. Okay, because generally those are the moments where you commit some mistakes actually. Okay, fine. So please type in the chat box. Is this clear to all of you? Because you know, these discharges and all, they'll be very small. When you're typing them, you should be careful. When you type 0.001, all these things, it'll be, you know, you should be a little careful. Okay, fine. Any doubts till this point? Any doubts till this point? Fine. It's almost some 2 hours since we have started. So if you have any doubts, you can ask me. Not only this, regarding fluid mechanics, regarding gate examination, anything. Okay, we'll speak some general thing for 5 minutes. Then again, we'll get back to track. Okay, so type in the chat box, because it's been already 2 hours. How many of you didn't realize that it's already 2 hours? Tell honestly. How many of you felt that the time went very fast? We have solved some nice questions, right? Cone rotating. Okay, then after some calculation of accelerations. First few questions I've kept conceptual, then mathematical, then slowly we, you know, kept on to the subject. Okay. Anyways, you felt time went very fast for 2 hours. How many of you felt this? How many of you didn't realize that it's already 2 hours that since we have started? Am I boring you too much? No, right? Okay, good. So if you have any doubts regarding the gate examination, regarding how to attempt the exam, anything, you can ask me. Okay. Look, I'll tell you one thing actually. Take question on compressible flow. Yeah, I'll take normally that compressible flow we'll leave to thermodynamics, but again, yes, if you have some doubts, I'll discuss here. No issue. How much rank should I get into IITM thermal department, sir? Forget about rank, because rank varies every year depending on paper complexity. But gate score, if it's above say 800, I mean category, it again depends on category. But normally, if you see, gate score around 800 could give you a very good admission in disciplines that you want. Okay, if you want design, if for general category is what I am telling, and generally design and all, if you see, it will be very less. I'll show you one thing. Normally, since I also spent some time at IITM, I have to show you IITM MTech. If you see this website, maybe last year website could be available. Yes, 2022 admissions. So here on the right side corner, left corner, sorry, you have these cutoffs. Okay, so MTech 2022 cutoff, MTech 2021 cutoff, 2020. Normally for 3 years they keep. For example, if you click this 2022 cutoff, then these are the scores. Okay, last admitted scores, non-PWD candidate. So for example, if you are from mechanical, okay, if you write exam in mechanical, then ME1 is for thermal. Yes, ME1. Okay, so ME1 is for thermal. So last time cutoff score is 755 for general category. Okay, so in general for mechanical 1, okay, Y. So mechanical 1Y, this is 755 score is the final cutoff. Because last year what happened is, I'll tell you, PSUs last year there happened one thing actually in 2022 exclusively. Okay, so normally in 2022 what happened is, till 2021, 2020 and 2021, these 2 years are very like nightmare years for gate aspirants, because of COVID first and second waves. There is no much PSUs giving equipments and all. Okay, so because of this many students opted for MTech. But last year suddenly what happened, number of aspirants that would get writing gate examination came down. Okay, so in 2020 it's almost like 1.1 lakh odd in mechanical, but last year number of candidates who wrote the exam is around 89,000 something odd. Okay, so and also PSUs, because for 2 years they didn't put any equipment, so suddenly all these PSUs they gave equipments, and there's huge vacancies in when you combine all the vacancies, the number of posts were huge. So many students who got a job, obviously they opted for the job. Okay, so that's why if you see last year the cutoffs for MTech is also low. Normally this won't be the cutoffs. I'll show you for 2021. Okay, so you can see at that time whenever there is no jobs and all, everyone opted for MTech. At that time you can see mechanical 1, if I show you for example the same year, so you see mechanical 1 it is 813, but here if you see 2022 mechanical 1, how much is the cutoff? 755. It came down. Okay, the reason is there are two things. Number of students writing gate in mechanical came down last year almost by 30,000 or 40,000 students, and main thing, because of no equipment in 2020 and 2021 because of COVID, last year there was a very large number of vacancies. So people who got minimum marks, like for example I'll tell you, during our time when we get around 65 to 70 marks in between, rank used to be in 4,000 or 4,000 plus, near to 4,500. But last year what happened, when you got 65 marks, 68 marks, your rank came below 500. Okay, so that's the difference. And this year number of aspirants are much less. So if you focus correctly and if you utilize all these free sessions and if you try to practice some questions and all, it will be a very great advantage for you. Clear? Okay, did you understand the logic? You have to always understand the dynamics. Okay, it's not like the same cutoff works every year. Okay, this year also there is lot of vacancies from PSUs and all, but one major drawback is that what do you say, like for example, generally IIT MTech admissions results come first and then the PSU results come. Okay, so because of this some slight issue, what happens is, like, people they get admitted to MTech first, then when they get a job they leave the seat and go to job. Okay, so because of this few people again lose some seats. Okay, so I hope this won't happen this year, because all the PSUs already gave notices that they're going to recruit, so things will happen in a fine way if you want to do MTech. Okay, this year also more people will choose PSU. Yeah, obviously, because of the after pandemic people started focusing on money, so that's why majority of the people they take jobs. Correct. Even that's the reason for the fall in cutoff. Okay, so anyhow, Vijay, the main reason is why I have taken this point is, forget about rank, don't worry about your rank too much. Okay, but focus on the gate score. Okay, and your gate score depend upon the gate marks, number of marks you get. Okay, so just try to increase your marks. So as marks increases, score increases, then definitely your rank also increases. Okay, so this is my common point. Clear? Fine. Any other doubts? Any more doubts? If you have any doubts, you please try to ask me. I'll try to explain you at the best of my knowledge that I can give you. Okay. Maybe fluid mechanics, or you can ask me doubts from fluid, thermal, and mathematics, which I teach. Okay. Marks optimum, can you tell, sir? 75 to 8, 75 to 80. Okay. Or 70 to 75 could be ideal marks. That could be fine. Okay. In XC, if you are writing XC. In mechanical, 70 marks could be good enough. XCB PYQ cover dijiye na, please. Yeah, definitely, Prashant. I'll try to do that on same channel, hopefully within a week's time. Okay, before the exam, no issue. Okay, fine. So shall we go back to the questions? Okay, so let's get back to the questions. Then this MTech story is done. A calculator, fine. Okay, so let us go for this next question. So let us see. A solid cylinder of diameter 30 centimeters and height 15 centimeters floats with its axis vertical in seawater, and the relative density of seawater is 1.03. And if the relative density of the cylinder material is 0.9, then which statement should be correct? Okay, so what statement should be correct? Metacentric height, stable equilibrium, unstable equilibrium. Okay, so they are asking you what is the values actually. Okay, so since, look, one thing is very clear. If metacentric height is positive, then definitely the body should be in stable equilibrium, correct? It is an MSQ. So definitely what should happen? If one of these two is correct, then definitely this is also correct. Okay, so anyhow, let us check. So how can the ME paper will be this year? We'll talk. Okay, we'll talk after some 45 minutes. Again, we'll solve some questions, then we'll talk about some general things. Okay, Ismail? Fine. So let us get back here. So there is one surface of water, surface of some liquid, right? Seawater. Okay, so there is some seawater, and on this seawater there is a cylinder which is floating. There is a cylinder which is floating actually. Normally, yeah, something deeper inside. Okay, so here if you see, this is cylinder which is floating. Now, first of all, the weight of the cylinder, for the cylinder to float, weight of the cylinder, or weight of cylinder should be equal to buoyancy on cylinder. Correct? Weight of the cylinder should be equal to the buoyancy force acting on the cylinder. Only in such conditions the body can float. Otherwise, what happen? Body will sink. Okay, so that should not happen. So this implies, what is weight of the cylinder? Density of the cylinder into volume of the cylinder, which is pi by 4 d square into h. Okay, so pi by 4 d square into h. Actually, this diameter is d, for example. Okay, so this diameter is d, and this is h, for example. Let us say height of the cylinder is h, and let height of the submersion is small h, for example. Okay, then in that case, this is density into volume gives mass into gravity is equal to, then buoyancy acting. So buoyancy is nothing but volume of the fluid which is displaced. So density of seawater into volume which is submerged inside this cylinder, inside this fluid, is pi by 4. Volume which is submerged inside this cylinder, inside this fluid, is pi by 4 d square times small h into g is what you have here. Okay, so from this we can calculate what is the value of small h. Okay, so let us calculate this. G gets cancelled, pi by 4 d square and pi by 4 d square gets cancelled, and so this implies density of this cylinder is equal to into h, into capital H, is equal to density of seawater into small h. Now let us do one thing. Since they are talking about relative densities, let us take density of water on both sides. Then small h value is capital H times of relative density of the cylinder, which is 1.03 is, no, this relative density of the cylinder is 0.9. Okay, so this is 0.9 divided by this relative density of this seawater is 1.03. So this is 1.03. So we'll get small h value. Okay, and what about capital H? They have given some value of capital H, 15 centimeters. Okay, so 0.15 meters, 0.15 meters into 0.9 by 1.03. Okay, so this is small h value. Okay, so small h is in some meters, because this we have kept in meters. So let us punch these values. 0.15 into 0.9 divided by 1.03, correct? 0.15 times 0.9 by 1.03, this gives you 0.131 meters. So 0.131 meters. So the height of the cylinder which is submerged in the fluid, in the sea water, is 0.131 meters. Now we need to calculate the metacentric height. How do you calculate the metacentric height? Gm is equal to Gm, which is metacentric height, is metacentric radius minus Bg, and metacentric radius is moment of inertia about this perpendicular plane by submerged volume minus Bg. Now try to understand this. Tell me, what is the plane about which you have to take moment of inertia? If you project this, for example, now see here, what is the plane that you have to take? This plane which is here. Okay, so at the interface, whatever is the top view that's available. Okay, so at the interface, if you see, now tell me, this is a cylinder. So at this interface, if you cut this and if you see the top view at this interface, what is the figure that you will get? So please tell me, at the interface, if you cut the surface, at this interface, if you cut the solid, and if you see the top view, what is the shape that you will get here? So type in the chat box. It's a cylinder. So please tell me. It's a cylinder. So please tell me what is. It's a cylinder. So please tell me what is the shape that you will get. If you cut the interface and if you see the top view, if you cut this solid at this part and if you see the top view at this surface, what is the solid? I mean, what's the shape actually? It's a circle, correct? So which moment of inertia is to be considered if rectangular object? Yeah, in case of rectangular object, normally when you have the axis of floating, if you cut at the free surface level, whatever the top view, if you take that top view is what you have here. Okay, so here in this case it's a circle. So let us suppose if it's a circular cross section, then what is the axis? Now about what axis you have to take the moment of inertia? If you see, this perpendicular axis passing through the centroid is the axis about which you have to take the moment of inertia. Means if you have a cross section like this, then to that cross section, this perpendicular axis, which means here in this case, this axis is the axis about which you have to take the moment of inertia. So this axis is xx. Okay, so look guys, in case of cone and all, many people commit this mistake. Normally in case of cone, what happens? The cone has larger radius here and the radius comes down as you go to the bottom. Okay, many people take moment of inertia of this base surface. Okay, you should not take that. You should always take moment of inertia of that surface which is at the interface, at the water line. Okay, so this point has to be noted very carefully. Clear? Normally in case of rectangular and this cylindrical things, you don't face any issue. But whenever they give you some cone and all, people make this mistake that they take the moment of inertia about the base, but you should always take the moment of inertia of the cross section which is at the water line. Okay, so means at this part, at this, if you cut the solid and if you see the top view, about this figure you have to take the moment of inertia. Clear? Now if you see, pi d power 4 by 64 is the moment of inertia. So pi d power 4 by 64 divided by submerged volume. So what is submerged volume? Pi d square by 4 into small h. Okay, so small h value we already know anyhow, minus Bg. So what about Bg? Now center of buoyancy and center of gravity. So center of gravity will be somewhere here and center of buoyancy will be somewhere here. Okay, so therefore what is this G? Half of this total height. Okay, so center of this total value is h by 2 minus center of buoyancy of solid which is submerged is small h by 2. So this is h by 2. So the difference between B and G is this value, correct? Yes or no? Because here if you see, this is B and this is G. So this difference is capital H minus small h divided by 2. Yes or no? Correct? So if you add this, capital H minus small h by 2. So this is the metacentric height. Now if this value is positive, then this is in stable equilibrium. If this value is negative, then the body is in unstable equilibrium. Okay, so let us check that. So let us see this. First of all, let us perform some calculation. Pi d square, this is d square, then this is 16 So d square by 16h. Okay. So what is d square by 16h? Let us say d square 0.3 meters. So 0.3 square by 16 times of h, which is 0.131, minus capital H minus small h by 2. So capital H is 15 and small h is around 13. Okay, so fine. 0.15 minus 0.131 by 2. Okay, so this is the metacentric height which is acting. Okay, so at this location, so metacentric height of this flotation is how much? Gm is equal to this value. Let us calculate this. 0.15 minus 0.131 by 2. Okay, so 0.0095. So subtract this from this value. So subtract this from 0.3 square by 16, 0.3 square by, oh, I think it got multiplied 2 times. Let us do this calculation again. 0.15 minus 0.131. Okay, so by 2, this value. So subtract this from 0.3 square, 0.09, 0.09 divided by 0.09 divided by 16 times of 0.131. 16 times of 0.131. Okay, so this value gives 0.334. 0.0334 meters. Now what are the options they have given you? They have given you in centimeters. Okay, so this is 3.34 centimeters. Correct? So this is the metacentric height at this location. So Gm is 3.34. So this is wrong. Since Gm is positive, this is in stable equilibrium, but this is not in unstable equilibrium. So A and C are the correct options in this case. Clear? Okay. Yes, Gm is metacentric height is 3.34 centimeters in this case. Okay. So is this clear to all of you? Metacentric height is 3.34 centimeters and this body is in stable equilibrium. Clear? Fine. Yes, A and C are the correct answers in this case. Okay, so one concept of metacentric height I thought of discussing here. This concept of metacentric height, if you see, for example, from design point of view, Gm should be more for stable, but from comfort point of view, this is actually wrong. Okay, I'll tell you one thing. Normally, this is one very famous question in L&T interviews. Okay, Larsen and Toubro, if you see, they'll ask you this question. Let us suppose if I'm designing a ship, then will Gm is more important or less important? Okay, means of course we know stability of the ship depends upon Gm. Normally, stability of any floating body, if you see, time period of oscillation. If you see, for example, we know if high, I'll tell you one concept here. If Gm is high, stability is high. Okay, obviously because stable equilibrium keeps on increasing, so stability is high. We know this, but there is one very important question in this ship design companies exclusively. They'll ask you that if I am designing a ship, how much importance should I give to Gm? Okay, means basically this metacentric height. The answer is to this question, if you see, there are two types of ships normally. One which, of course, in general purpose, if you classify, one is passenger ships which takes people, and one is cargo ships which takes goods, actually oil, these kind of things. Okay, so here if you see, time period of oscillation is actually inversely proportional to square root of Gm. Okay, I'm not doing the derivation for now, it's a simple derivation, but of course I'm just giving you this idea. T is inversely proportional to root Gm. Okay, now if you see, if you increase Gm, let us suppose if you increase your Gm actually, okay, so if you if you keep on increasing your Gm, metacentric height, then time period of oscillation will be low. Correct? Yes or no? Sorry, I think it is T is equal to, just a minute, theta double dot plus W by Gm theta is equal to 0. So omega is square root of this. So T is directly proportional to, yes, correct. So T is inversely proportional to square root of Gm. Okay, so T is inversely proportional to square root of Gm, correct, because simple harmonic motion is the oscillation of the ship generally. So now whenever you increase your Gm, if you try to increase the stability of your ship, if you try to increase your Gm, this time period will actually come down. Okay, So basically in this case, if GM value is increasing, your time period of the ship will come down, means time period of oscillation will come down. Now tell me, for warships GM should be high, okay, but for passenger ships yes, generally for cargo, generally whenever passengers are going, we make sure time period of oscillation is high, okay. The reason is, look, whenever ship is tight, okay, for example, let us suppose if ship, my hand is ship, okay, now whenever some disturbance, some wave or some wind come and hit the ship, now the ship actually goes by some disturbance and come back to the same mean position, okay. Now try to understand one thing, time period of oscillation is, for example, let us say only 1 second. Within 1 second ship goes like this and come fast, okay. So ship moves and get back very fast. So whenever ship oscillates, means if the time period of oscillation is very low, then will the passengers feel comfortable inside the ship? Means within 1 second you are just tilting and coming back, then will you feel comfortable there in the ship? Will you feel comfortable there in the ship? If time period of oscillation of the ship is very low, for example, then means the ship actually go to some disturbance and come back in very less time, okay, which means if you are physically inside the ship, you move down and come back very fast. So is that comfortable for the passengers? Is that comfortable for the passengers here? No, okay. So in that case, passengers don't feel very comfortable in the ship. So that's why in such cases there is some compromise between comfort and stability, okay. So in case of passenger ship, of course the design is made such that the ship meets stable equilibrium, but the increase in GM is restricted to save the comfort of the passengers, okay. But in case of cargo ships and all, where stability is of more importance and comfort doesn't have any much sense there, so that's why they will go for T, okay. Clear? So I hope you got the thing. So when your design is with respect to the passenger ships, you compromise certain value on GM, metacentric height, and you focus on the time period for the comfort of the passengers. But when you go for cargo ships or warships, generally stability is the main point of importance, and there you try to increase the GM as much as possible. Clear? So this point is one very good point. Normally you face this in all the ship design industries like L&T and all other companies, okay. Clear? Fine. So let's go for the next question. So let us see this. Air flows through a pipe at a rate of 120 liters per second. So there is some air flow which is happening here at 120 liters per second. Okay, so there is some 120 liters per second. The pipe consists of two sections of diameters 22 centimeters and 10 centimeters with a smooth reducing section that connects them. Okay, so there are two sections and there is some smooth reducing section. The pressure difference between the two pipe sections is measured by a water manometer. What is the meaning of this water manometer? The manometric fluid is water. Okay. Whenever they tell you mercury manometer, water manometer, things like that, the liquid with which they are telling this is actually the manometric fluid. Okay. Since you can use water as manometric fluid because the substance flowing in the pipe is air. Okay. So whenever this is air, you can use water, higher density fluids. Now I'll ask you one question. Try to answer this. Let us suppose if you use an inverted tube manometer, for example, okay, for the same configuration, air is flowing in the pipe. If you use inverted tube manometers gives better accuracy. Okay, I'll show you how. Okay, how many of you know this? Normally, inverted tube manometers gives better accuracy. How many of you know that inverted tube manometers gives better accuracy actually? Normally you have seen inverted tube manometers, correct? So inverted tube manometers gives generally better accuracy. Okay. So if you see why, how many of you know the answer for that? Why inverted tube manometers give better accuracy? Why inverted tube manometers gives better accuracy actually? Why inverted tube manometers give better accuracy? High resolution. I don't know. Yes. So any idea why? Okay, you know this point, good. But my question is why inverted tube manometers gives better accuracy? Because theoretically you might have mugged up at some location, but on some book or something. But physically, why? Why it gives you? Okay, we'll see that after some questions. We'll take some small break in the sense, not, you know, I'll go away from this place. We'll stay here, talk some general points again regarding gate and all, and then we'll again get back we'll discuss this question. Okay, so we'll keep some questions to discuss in that free time, okay, in between. So for example, now my question is, when you keep this inclined tube manometer here, then definitely what happens, if this is a inverted tube manometer, actually it's, if this manometer is a inverted tube manometer, then you cannot use water, okay, because whenever you keep this inverted tube manometer, water having higher density will come and settle in this pipeline, okay, so then there's no more a manometer, it just acts as a bypass for the air, that's it, okay. So that's why in case of inverted tube manometers, always the density of the manometric fluid should be less than the working fluid, which is basically the fluid flowing in the pipe, okay. So now here if you see, anyhow, if the frictional effects are neglected, then the differential height of water between the two pipes section is dash centimeters, okay. So this is 22, this is 10, discharge is given. So let us see, they are asking you what is this difference h, what is this difference h, okay, what is this difference in the heights h. This is h, okay. Now how do you calculate h? So first of all, let us take this section. So if you take this section 1 and this is section 2, okay, so this is section 2, for example, 1 and 2, for example, okay. So if this is section 1 and 2, then if you apply Bernoulli's equation between sections 1 and 2, applying Bernoulli's equation between 1 and 2, okay. So let us take for example 2 points, first point and second point here, okay. So first point and second point, guys, try to, okay, manometric fluid, high resolution due to high reading of same pressure due to low density, yes, okay, correct, I'll explain you that. Now here if you see, I'll ask you one more question here. First thing, normally if you take a flow through pipe, for example, okay, if you take a flow through pipe, whenever you have a pipe cross section, for example, whenever you have a pipe cross section, okay, a circular cross section, for example, then in that case, if you take the radial direction, normally this dou P by dou R, radial pressure variation will be 0. Normally you might have seen in viscous flows. If you apply Navier-Stokes equation in cylindrical coordinates, you will easily understand that, okay. So we'll see how is the deflection, dou P by dou R is 0, so that's why whatever is the pressure here, same will be the pressure here. Now I'll ask you one more question here. Normally let us suppose there is some flow, can I apply Bernoulli's equation at any 2 points in the flow? In all conditions, in all cases, can I apply Bernoulli's equation at any 2 points in the flow? Can I apply this? Let us suppose you have some flow that's happening. Can you apply Bernoulli's equation at any 2 points in the flow? At any 2 points in the flow, can you apply this Bernoulli's equation? Okay, we'll see the answer. Okay, we'll solve this question slowly, no issue. But tell me the answer. Can you apply Bernoulli's equation between any 2 points in the flow? No. Why? What is the limitation? Why you cannot apply? I'll say that I'll apply. See, for example, I'm applying here 1 point and here 1 point. What is the restriction? No, we cannot apply. Why? See, I am applying here in all the cases. I am applying. See, for example, here. Okay, so here you see at 1 point and second point, I applied at 2 different points. Okay, as my wish. Similarly, here in this case also, I applied at this point and this point, my wish. Okay, so what is the condition? Very good, Rishikesh. Along streamline if rotational, correct. Okay, so if flow is rotational, look, for example, if flow is rotational, then you have to apply Bernoulli's equation at 2 points on the same streamline. Okay, so please keep this point in mind. It's not in my comprehensive course, I have discussed this in derivation and all, but just I'm giving you this point, keep in mind. No, only incompressible study in viscous. No, not like that. If the flow is irrotational, then you can apply Bernoulli's equation at any 2 points in the flow, no matter whether the 2 points are on the same streamline or not, you can apply. Okay, I have shown it in my detailed course actually, but right now it's a bit lengthy derivation again using polar coordinates and all I have to discuss, so let us not Have that. Okay, I'm just giving you a result. If flow is irrotational, you can apply between any 2 points in the flow. If flow is rotational, then in that case you can apply at only on the same streamline. Okay, if flow is rotational, then you can apply Bernoulli's equation at 2 points on the same streamline actually. Okay, but if flow is irrotational, then you can apply at any 2 points. Clear? So rotationality is the picture that's very important for applying Bernoulli's equation. Clear? Yes, if flow is irrotational, then we can apply at any 2 points. Okay, but if flow is rotational, you can apply only at the same, only at the same, only on the 2 points on the same streamline. Clear? Okay, so this point is very important. Okay, fine. So let us solve this anyhow. So if you apply Bernoulli's equation, then P1 by OZ plus V1 square by 2Z plus Z1 is equal to, they've asked assume no losses, correct? They told if frictional effects are neglected, so no losses, P2 by OZ plus V2 square by 2Z plus Z2. Okay, so we have this Bernoulli's equation. Now since this is a horizontal pipe, then there is no elevation in the elevation difference. Then if Z's are cancelled, then you can cancel G all over. So P1 minus P2 by rho of air actually here. Okay, so this is density of air because air is the substance. V2 square minus V1 square by 2 is what you have. Okay, now this is 22 centimeters and this is 10 centimeters. Discharge is given 120 liters per second. Okay, so how do you calculate V1 and V2? V1 is 4q by pi d1 square and V2 is 4q by pi d2 square. Okay, so this is d2 square. So we'll calculate V1 and V2 values. Okay, so this gives you V2 square is 16q square by 2 pi square into 1 by d2 power 4 minus 1 by d1 power 4 actually here. Okay, now what about this P1 minus P2 difference? If you see, pressure here is P1, and if you neglect the air column as compared to the water column, because air, your communication is great. Okay, thank you. So see here, what I'm telling, yeah, here we have air here. Okay, so if you have air, for example, so compared to the water density, air density is very small because water has almost density of 1000, but air has only 1.25. So the pressure column created because of the air is very less actually. Okay, so that's why when you neglect this air column, if you take this manometer, for example, for the same expense of fluid, if you take this as datum in the manometer, because if you see, this is the interface that's maintaining the same liquid. Okay, so that's why pressure at this location, for example, if you take points A and B, okay, so if you take points A and B, then from manometry, PA should be same as PB. PA should be same as PB. So what is PA actually here? If you neglect this air column length and this air column length, then P1 is same as PA. Okay, because this height is not given, so we'll neglect the air columns, they are very small. So P1 plus, so PA is nothing but P1. And what about PB? PB is P2 plus this small water column which is of height h. So P2 plus rho water GH. Okay, so P1 minus P2 from this equation is rho water GH, correct? So this is the deflection that's available. So P1 minus P2 is rho water GH. If you replace here, rho water GH by density of air is equal to 16q square by 2 pi square times of 1 by d2 power 4 minus 1 by d1 power 4. So if you write expression for h directly, h is equal to 16q square density of air by 2 pi square into g into density of water, g into density of water into, okay, so we got all the quantities, O air, O W into g into 1 by d2 power 4 minus 1 by d1 power 4. Okay, so this is what we have. So if you substitute all the values, let us compute this value. H is equal to, what are the units they are asking? In centimeters. Okay, so first of all, let us calculate in meters, then we can take in centimeters. Okay, now 16 by 2, this can be cancelled 8 times anyhow. So 8 times of, then q square. What about discharge? 120 liters per second. So 1 liter is 10 power minus 3 meter cube per second. Okay, so 120 square, 120 square into 10 power minus 6. So these many meter cube per second into density of air. So what is density of air? 1.20 kg per meter cube. So 1.2 kg per meter cube divided by, okay, so this is 1.2 kg per meter cube divided by pi square into G 9.81 into density of water 1000. Let us take, or did they give something? They haven't mentioned anything, right? Okay, fine. Then let us take 1000 by default, 10 cube. Okay, so we have 10 cube, then into 1 by d2 power 4. So what is diameter at the second section? 10 centimeters. So 0.1 power 4 minus 1 by, that's 22 centimeters. So 0.22 power 4. Okay, so this total value, if you calculate, you will get it in meters. So you can write it in centimeters. Okay, so let us calculate this calculation little carefully. So here, let us take some white color. So let us see 10 cube. Okay, so okay, this is 10 cube is in the denominator. Fine. So this is 0 can cancel this 10 power minus 4 times anyhow. Okay, so let us see. Let us perform this calculation. First, let us start with this bracket. 1 by 0.1 whole power 4. 1 by 0.1 power 4 minus 1 by 0.22 power 4. 1 by 0.22 power 4. Okay, so this value. Fine. So this value is 9573 into some value into 1.2 into 1.2 into 10 to the power minus 4. So divided by 10 to the power 4, for example. Okay, so this value into 12 square, 144 into 144 into 8. Okay, so into 8. So this value 1323 point something divided by 1000. Okay, so divided by 1000 you have. So divided by 1000. This divided by pi square into 9.81. Okay, so 9.81 and this value divided by pi square. Okay, so 0.01366. 0.01366. Okay, so this is what you have, correct? So 0.01366. So that in centimeters is 1.37, for example, if you round off to 2 decimals. So 1.37 centimeters is such a small deflection, of course, because the fluid is air. So 1.37, yes, 1.37 centimeters is the deflection that is shown by the manometer. Clear? Hindi also, yeah, definitely, you know, I'm trying to speak, but very soon, hopefully in some 3 to 4 months, I'll try to take some sessions in Hindi. Okay, actually, I know my Hindi is very bad as of now. Okay, if I speak Hindi, you feel like you know, Shah Rukh Khan speaking Tamil in Chennai Express movie. So that's why we'll you know, take Hindi sessions a bit later. Fine. I'll ask you one thing here. Try to tell me honestly. Yes, of course, I do respect Hindi, and you know, obviously there are very good things. But let us suppose if you get, you know, an MTech admission in IIT or IISc Bangalore, anywhere. Okay, here there is a provision to teach in Hindi, so that's why you are asking. But trust me, nowhere in India, in IITs or in IISc Bangalore, anywhere, people teach you in Hindi. Okay, they teach you 100% in English. And let us suppose if you are planning for some foreign admission or something, again they don't teach you in Hindi, they'll ask you to learn in English. Okay, so try to make it a habit to learn in Hindi, okay, to learn in English. Okay, initially, yes, I do agree, because to understand few things we need to, you know, understand it in the own language, in the native language, but make sure that you will actually get the things better in English, so that it will help you in near 2-3 years, upcoming years. Okay, fine. Clear? But yeah, definitely very soon I'll try to start you know, sessions in Hindi. Okay, but for now, please adjust. Let's go with English. Okay, yeah. So this is, सर थोड़ा सा हिंदी बोलो, अरे मुझे हिंदी उतना अच्छा नहीं आते है, so इसलिए I'm speaking in English. Okay, fine. So let's continue. So something is given here. What is given? A body weighs 20 newtons and 10 newtons when weighed under submerged conditions in liquid of relative densities 0.8 and 1.2 respectively. Then which one or more of the following statements is or are true? Okay, so let us see. There is one body which is weighing 20 newtons in some fluid with relative density of 0.8 and 10 newtons with another relative density of 1.2 respectively. Then which one of the following or more statements are correct? Okay, weight in air is 50 newtons, volume of body is 2.53 liters, weight in air. So basically point of focus or point of interest is what is the weight of body in air and what is the volume of the body. Okay, so these two things are of importance. Okay, so let us calculate. First of all, case 1 solution. Case 1, the body, first of all, if you see, let us suppose the body has some shape. Okay, so the body has some shape, for example. Now this body is inside some fluid. So this body is inside some fluid. This is relative density of S, for example. Okay, so let us say, look guys, I'll tell you one thing. So strategy क्या होना चाहिए गेट 2025 के लिए? Okay, I'll tell you. Vishwajit, yeah, definitely I'll answer this. Okay, but after some 2-3 questions, again we'll take some break and then I'll answer you this. Okay, now I'll tell you one thing. Actually, many times people use these terms and synonymously, like relative density and specific gravity. But actually, there is some difference between these two. Okay, relative density is ratio of any two fluids. Okay, means basically density is ratio of any two fluids. For example, if I take kerosene and some other vegetable oil, for example, then I can say the ratio of these two quantities as relative density of oil. For example, I can say relative density of oil is density of oil divided by density of this kerosene. But if you take specific gravity, then you standardize the comparating fluid. Okay, means basically if I say density of one particular fluid by the second fluid, you standardize the fluid about which you are comparing. Okay, so specific gravity means in case of liquids and solids, we take generally with respect to water, and in case of gases, we take with respect to air at STP conditions. Okay, standard temperature and pressure conditions. Okay, so that's the main difference between relative density and specific gravity. Okay, so in case of specific gravity, we standardize the fluid with respect to which we are comparing the things. Okay, but in case of relative density, it can be a ratio of any two things basically. Okay, but here since nothing is mentioned, I am taking my relative density is same as specific gravity. Okay, but if things are mentioned, you should be a little careful. Okay, now let us continue. So normally in this case, what happens if you take the free body diagram, weight acts downwards and buoyancy acts upwards. Okay, so the difference between these two is taken as the weight, correct? Because the actual weight of the body cannot be measured, correct? Because if you keep the body on any basically any weighing machine, what happens is some part of the weight of the actual weight of this body is being overcome by the buoyancy force. Okay, so that's why you cannot get the actual weight. Okay, so that's why there is some small change in the value. Fine. Okay, so that's what. Shavish, so please अपने टीम से एप्टीट्यूड और मैथमेटिक्स के भी PYQ वाला वीडियो के लिए बोल दीजिए. Yeah, definitely. Do you know Telugu, sir? Yeah, Telugu is my mother tongue. I know Telugu well. Okay, Telugu baga వచ్చు నాకు. So anyhow, let us see here. So if the volume is V, if the volume of the body is V, then in case 1, the body is weighing 20 newtons. So 20 newtons, whatever you are weighing, is nothing but density of the body or weight of the body, actual weight of the body, minus this buoyancy force which is acting. So density in case 1, which is S1 into rho water into G into volume of the body. Okay, so this is the actual weight that you are measuring in this case. Okay, so whenever you keep the body in fluid, then weight of the body, some part of the weight of the body is actually balanced by the buoyancy force. So that's why this 20, whatever you have measured, that is actual weight of the body minus this buoyancy force which is acting. So buoyancy force is equal to G into volume of the body into fluid density. Okay, so relative density in the first case, let us suppose if it is S1, then S1 rho W into GV is what you have here. Similarly, in case 2, in case 2, we know that 10 is equal to weight of the body minus specific gravity of relative density in the second case into density of water into G into volume actually here. Okay, so this is G into volume. Now you need two things. First thing, weight in air, and second thing, volume of the body. So first of all, let us calculate volume of the body. So for example, if I call this first equation and if I call this second equation, then from first and second, from 1 and 2, so let us say from 1 and 2, this weight of the body is nothing but 20 plus this quantity. So 20 plus S1 into density of water into G into volume is equal to, in second case, 10 plus that value. So 10 plus relative density or specific gravity in this case into density of water into G into volume of the body. Okay, so from this expression, 20 minus 10 is equal to S2 minus S1 into density of water into G into volume. Okay, so what about volume here? Volume is 10 newtons divided by S2 minus S1, the difference in the specific gravity. So basically here the relative density is 1.2 minus 0.8, which is 0.4 into density of water 1000 into 9.81. So this is in meter cube. Okay, so if you want to convert meter cube to liters, then 1 meter cube is equal to 1000 liters. So that's why if you take volume is equal to 10 into 10 cube by 0.4 times of 9.81 liters. Okay, so this is in liters. So you can cancel out this 10 cube. This one more 10 cube is also there. Okay, this 10 cube should be there as it is. So volume is equal to 10 by 0.4 into 9.81. Okay, so 0.4 into 9.81. So 0.4 into 9.81. See, when I'm typing the previous calculation, instead of 4, I clicked on 5. So these kind of mistakes will happen in exam. Okay, so please be careful. So now reciprocate this and multiply 10. Okay, so multiply 10. So if you multiply 10, 2.548 liters. 2.548. So 55 liters. So 2.55 liters is the volume of the body. So 2.53. Okay, so maybe some second decimal could be changing. So 2.53 liters is correct. So the volume of the body is not 3.64. Now what is the body weight in air? Okay, so if you keep the body in air, what could be the weight of the body? So let us check this. Weight of body in air. Weight of body in air is equal to actual weight of the body. Actual weight of the body. Actual weight we can write W actual minus buoyancy force of air. So density of air into G into volume of the body. Okay, but now who tells you what is the actual weight of the body? From any of these equations, from one of these two equations, you can write 20 plus S1 OWGV. Okay, so or 10 plus this quantity from out of these two equations. In any case, you can take. Let us take first case 20 plus density S1 into density of water into G into volume minus density of air into G into volume. Okay, so this is equal to 20 plus S1 into density minus density of air. So S1 is 0.8. So 0.8 into 1000 is 800 minus this is 1.2 for example. Okay, so 1.2 into G 9.81 into volume in meter cube. So volume in meter cube is 2.55 by 1000. Okay, so 2.55 by 1000. Then this answer will be in newtons. Okay, so this will be in newtons. So what are the units they are asking? They are also asking in newtons. Okay, and these are also in newtons. Okay, fine. So let us compute this value. So if you compute this value, let us see 800 minus 1.2, or this is volume better. Keep this 2.48 something divided by 1000 into 9.81 into 9.81 into 800 minus 1.2. 800 minus 1.2. Okay, so this value 19.97 plus 20. Okay, so 39.97, almost 40 newtons. Okay, so 39.97 997. So if you round off, very close to 40 newtons. Okay, 40 newtons is the weight of the body in air. Okay, so that's why this answer is 40 newtons. Clear? So this is in 40 newtons. So B and C are correct answers. 50 is wrong. So B and C are the correct answers in this case. Clear? So please type in the chat box. Is this clear to all of you? 40 newtons is correct answer. Okay. So 40 newtons is actually the weight of the body inside air. Okay. Fine. So let's go for the next question. Yeah, 40 newtons. Okay. So let us solve this question. A dough in a tank is in the form of a quadrant of a circle of a cylinder of radius 3 meters and width 4 meters. Okay. So width means into the plane of the figure, it is 4 meters. Then the horizontal force acting on the dough is dash. Okay. They're just focused on the horizontal force. Good. So horizontal force. Okay. So this is free water surface. So how do you calculate the hydrostatic force or the horizontal force acting? So if you project this, so if you project this, then you will get a rectangle actually here, correct? Because if you want horizontal force, this is a curved surface. Okay. So forces acting on curved surfaces. How you do this? So for example, if there is some curved surface, then how do you calculate? For example, if these are the forces in X, if these are the standard X, Y and Z directions, for example, or maybe Y generally you take in this direction, X, so Y and Z directions. Okay. Then how do you calculate the hydrostatic forces? So force acting in the X direction is equal to, look, Fx is equal to rho fluid G into Ax into Zx bar. Similarly, Fy is rho F into G into Ay into Zy bar. Similarly, Fz is weight of fluid supported by the surface. Weight of fluid supported by the surface. Supported by the surface. Okay. Now, if you see carefully here, try to understand this. What does these terms tell you? Look, what is Ax? Okay, 588.6. Okay, fine. I'll solve the answer, but try to understand these things. Okay. So how to calculate this Ax? Okay. So see carefully here. Ax is nothing but the area projected onto a plane perpendicular to x-axis. Okay. Means, for example, look, here this is a curved surface. Okay. So whenever you see this is x-axis, for example. Okay. So let us suppose if this is your x-axis in this x direction, then the plane which will be perpendicular to this x-axis is nothing but this plane which is perpendicular to the board, correct? Means if this is the x direction, then this plane in this direction is perpendicular to x-axis. Now you have to project this complete solid or complete surface onto a perpendicular plane. Now how do you know the projection? If you see the side view of this. Okay, so that's how you have the side view or the surface projection onto a perpendicular plane is seen on the side view actually. Okay, similarly if you want in the y direction, you have to take a plane perpendicular to y axis. Similarly in the z direction, you have to take a plane perpendicular to z axis. Clear? Okay, so please type in the chat box, is this clear to you? Did you understand how to take this ax and ay, projected areas basically, okay, onto planes perpendicular to x and y axis? Clear? Now this zx is nothing but depth of center of pressure, this zx is nothing but depth of centroid of that projected area from the free surface. Okay, so the depth of projected area from the free surface is this zx bar. Similarly zy bar, and this is directly the weight calculation. Okay, so now if you see this, now this is 3 meters, this is 3 meters, this is 3 meters actually, and this width is 4 meters. Of course I didn't dot the scale, so this is 4 meters. Now free surface is at this location, so the depth of centroid, for example if centroid is here, then if you see, this centroid is at a depth of this h from the free surface. Okay, so from the free surface, this is h. You should always take this depth of centroid from the free surface. Okay, so this is h, small h. Okay, so this is small h. Now if you see fh, hydrostatic force, fx or fh in x direction, fh in x direction is rho f g into ax into zx bar, depth of centroid. So here the fluid is water, for example. Okay, so a dough in the tank is in the form of quadrant of a circle as shown in the figure. This is water surface. Okay, so it is water, 10 cube is the density, g 9.81 into what is projected area, this 4 into 3, which is 12. Okay, so 12 is the projected area, and zx bar is how much? Depth of centroid, this depth of centroid from free surface. Okay, so if you see carefully, this rectangle, so this height is 1.5 and this is 3.5, so total 1.5. This height is 1.5 meters, 1.5 meters, and this is 3.5 meters, so total 5 meters. Okay, so we have a 5 meters totally here. So this is, what are the units? They have asked in kilonewton. Okay, so this is in kilonewton. Fine. Okay, so if you want in kilonewton, then you can delete this 10 cube. So 60 into 9.81, 60 times of 9.81. Okay, so 588.6 kilonewtons, 588.6 kilonewtons here. Okay, so that's the hydrostatic force acting on the x direction. Yes, correct, 588.6. Now please calculate what is y direction force, fy, or basically in the z direction, vertical force. Okay, so please calculate what is vertical force, fz, f vertical you can say. Okay, so vertical force, so please calculate what is vertical force acting. Yes, 588.6 is the correct answer, one with. Then calculate what is the vertical force here. So please calculate what could be the vertical force in this direction. So what is the weight of the fluid which is supported by this circular arc? So please calculate that. Please calculate what is the hydrostatic force acting in the vertical direction. Okay, so y direction force, y basically vertical. Okay, whatever that direction, vertical force acting on that particular cylindrical surface. Yeah, so please calculate what is the vertical force that's acting. Any idea? So see, how do you calculate weight of the fluid? So basically this, if you see, this portion of fluid is actually supported by this surface, correct? Okay, so this shaded portion is actually supported by the surface. Okay, so how do you calculate this? Fv is equal to weight of the fluid supported by the surface, weight of the fluid supported by the surface. Okay, the weight of the fluid supported by the surface. So this implies, or this is equal to density of the fluid into g into area shaded, whatever the area I have shaded, into width of the gate. Okay, so width of the gate. So how do you calculate the, okay, 487.8 around. Okay, so 487 point something. So let us calculate. So density of the fluid into g into, now how do you calculate this shaded part? Look, whenever you are solving questions of hydrostatic forces, geometry and trigonometry should be very sharp in your mind. Okay, so that comes out with practice easily. So if you see, this total area can be calculated as this rectangle area minus this circular this quadrant area. Okay, so rectangle is nothing but this dimension is how much. Okay, they have given this is a circular arc, quadrant of a circle. So if this is 3, then this dimension is also 3 units. Okay, 3 meters, and this total is how much? This is 3 meters plus this is 3.5, so total 6.5. This is 6.5 and this is 3, so 6.5 into 3, 6.5 into 3 minus, you take out this part of the quadrant. Okay, so this is 1/4 of a circle actually. So pi r square by 4. Okay, so this is what you have into width. What is the width of the gate actually? So width of the gate is 4 meters. Okay, so they have told, so this is 4 meters. So if you perform this calculation, if you want in kilonewtons, then delete this and write it in kilonewtons. So calculate this value, 9 pi by 4, 9 pi by 4. Okay, so this is 9 pi by 4. So subtract this from 6.5 into 3. Okay, so subtract this from 6.5 into 3. So this multiplied with 4, multiply this value with 4 and multiply this with 9.81. Okay, so 487.80, 487.80 kilonewtons. Okay, so this is 487.80 kilonewtons is the correct answer. Yes, so please type in the chat box, is this clear to you? 487.80 kilonewtons is the correct answer. Fv can be calculated as weight of the fluid displaced, F buoyancy. In case of bodies, you can do that. Okay, you can do that only in case of bodies. Okay, not in case of surfaces. Okay, in case of 3D bodies. Look, you should know the difference between surfaces and bodies. Okay, bodies are 3-dimensional in nature generally. Okay, fine. So 487.8 kilonewtons is the correct answer. Yes, all of you are very correct. Okay, one with Midun, Roshan, Nitin, Sukumar, Rishikesh, Rohit, Vijay. Great. Okay, so let's go for the next question. So let us see. There is some small question of thermodynamics kind of thing, because fluid mechanics is of both liquids and gases also. So I have taken some small question. Actually, Amit Moya sir has taken this question, but unfortunately there is some technical issue with his thing. Fine. Okay, so let us solve this question. A gas is contained in a vertical frictionless piston cylinder device. The piston has a mass of 15 kgs and a cross-sectional area of 35 centimeters square. A compressed spring above the piston exerts a force of 75 newtons on the piston. Okay, so what happens? Normally this is a polytropic process. So if you see, look guys, I'll tell you. Okay, we'll see this question. I'll tell you one thing that happened in my BARC interview also actually. Okay, so firstly they've asked what is Boyle's law. I told, sir, for a finite amount of mass of any gas at constant temperature, pressure is inversely proportional to volume. Okay, so I have told this. So pressure is inversely proportional to volume, correct? Now they've asked me, let us suppose you take a balloon, and if you are blowing, for example, okay, so when you blow a balloon, normally if you blow a balloon, then volume increases and pressure inside the balloon also increases, correct? Now how come both are same? Temperature is constant there also. Okay, so temperature is constant, but if you are blowing a balloon, then definitely pressure inside the balloon will increase. Okay, because obviously the shape, the bulging increases. Okay, and volume also increases. Okay, when pressure is high inside, then definitely volume it tries to expand. Then I told that yes sir, pressure and volume both are increasing, but here in this case amount of matter is not finite, correct? Because you are blowing air into the system, into the control volume actually. Okay, if you take balloon as your control volume, then you keep on blowing air into the control volume, so mass is not constant. Exactly. Okay, now then they gave me this example. Okay, let us suppose if there is a piston cylinder, if you are heating, okay, so if you are heating this, then if you are heating this system, then how come you justify your Boyle's law? Then I told, so in this, because here it's a fixed amount of gas, correct? Because mass is fixed, but if you start heating this, then what happen? Pressure increases, volume also increases. Okay, how pressure increases? Because this in this case of heating, what happens is when you heat this gas, then both pressure and volume increases actually. Okay, I'll show you with a small simple mathematical equation. I'll show you how pressure and volume both increases. Then they have asked how pressure and volume both increases in this case. Then I told them, so in this case mass is fixed, but when you heat it, temperature won't be constant. Okay, so temperature changes, so pressure and volume both changes. Okay, so that's why Boyle's law cannot be applied here. Okay, so strain energy was stored in the spring, yes of course, and also temperature of the system will increase actually. Okay, so when temperature increases, pressure and volume both can increase. Okay, Boyle's law talks about only constant temperature. So these are the things they played with Boyle's law, and but in one case mass is not constant, in one case temperature is not constant. Okay, So these are the things they have asked a little about this spring mass. Okay, when I find some time, I'll discuss some more questions, what happened in that interview and all. Okay, and normally, BARC is the generally known toughest interviews of all the technical interviews. But yeah, fortunately I have cleared that and I have some good information to give you. Okay, so we'll find some time again and at some different context, and I'll give you some more details about that. Okay, so now coming back to this question, a gas is contained in a vertical. Okay, fine, I hope it's clear, right, all of you? Okay, are you all liking the questions? Till now, what are the questions we have solved? We have revised many of the concepts actually. Okay, fluid and its properties, manometers, then hydrostatic forces, buoyancy and flotation, meta center, acceleration calculation, Bernoulli's equations. Okay, all these things clear. Then head loss, in one question we have discussed about the head loss. Okay, and we have some more questions to do. Okay, we'll see. Clear. So we are revising some good things actually. Okay, so let's get back. Okay, someone is ready with the answer. Midun, I don't know, I have to solve. Okay, so see here. A gas is contained in a vertical frictionless piston cylinder device. The piston has a mass of 15 kg and a cross-sectional area of 35 centimeter square. A compressed spring above the piston exerts a force of 75 Newton on the piston. If the atmospheric pressure is 105 kilopascals, then the pressure inside the cylinder is dash kilopascals. Okay, so if you draw the free body diagram of piston, actually here, then on the top there is some pressure, atmospheric pressure, which is acting, and similarly on the bottom there is some gas pressure which is acting. Okay, so there is some gas pressure. Okay, so see here, and we have air pressure from the top. Okay, so atmospheric air also acts. Okay, so we have some atmospheric air acting here. Okay, so atmospheric air, and you have some spring force that's acting on the top. Okay, so spring force is also there. Okay, so there is some spring force, F spring. Then pressure due to atmosphere, so force due to atmosphere, and this is force on the piston due to gas, F gas. Okay, so these are the things, and also you have weight of the piston because piston mass is also given here. So you have some mass for the piston, so weight of the piston. Okay, so we have weight of the piston, W piston. Okay, so this is weight of the piston. Sorry, is General Electric was coming into IITM? Sorry, I didn't get. GE. Okay, General Electric, just GE turbines and all. I think it equated few electrical last year, not last year, at my time, long back. Okay, but yeah, General Electric is very good company. Okay, previously in my industry we used to take a lot of devices from GE, pumps, turbines and all. Even I was doing maintenance of this one captive power plant actually. So we were doing actually combustion inspection CI of one turbine. Okay, so then they played a very important role. That's a very good company. Okay, even if it's not equating, you can apply to the KVS portal and you can get it. Okay, General Electric. Okay, fine. So let us solve this question now. At equilibrium, sigma Fy is equal to 0. Sigma Fy is equal to 0. Let us take upward force as positive, for example. Okay, so this gives you pressure of the gas into area of the piston is then all the things are on the negative side, minus force acting by the spring minus atmospheric pressure into area minus weight of the piston is equal to 0. Okay, so this is 0. So what about pressure of the gas inside? So this is weight of the piston plus force acted on the spring by area, this area of the piston, this is also divided by area of the piston plus we have pressure of atmosphere, right? So these are the things. Now how volume and pressure both increases is, okay, so how volume and pressure both increases is, look, let us suppose if the spring is moving up, okay, so let us suppose if the piston is moving up, then the spring gets more compressed, yes or no, correct? Because if this piston is moving up, then the spring gets compressed actually, okay. So whenever the spring gets compressed, then force acting on the spring is equal to, or force exerted by the spring is equal to K into delta, where K is stiffness of the spring, okay. So F spring is equal to, this force acted by the spring is equal to K times of compression. Now try to understand one thing, as this volume of the gas is increasing, then this piston moves up, so this delta, the compression in the spring also increases, so the force exerted on the spring also increases here, correct? So that's how whenever volume increases, force exerted by the spring increases, okay. So whenever force exerted by the spring increases, this F spring increases, PATM is constant, weight of the piston, area of the piston are constants, that's how. But this force acted by the spring actually increases, so that's how when volume increases, pressure also increases in this case, okay. So that's how both pressure and volume will increase, okay. Now this implies P gas is equal to, what is weight of the piston, okay. So weight of piston, so what is weight of the piston? Mass of the piston is 15 kgs, okay. So they have given you mass of the piston is 15 kgs, so 15 times 9.81 by area of the piston. What about area of the piston? 35 centimeter square, so 35 into 10 to the power minus 4 meter square, plus force exerted by the spring. So what is force exerted by the spring? 75 newtons on the piston, okay. So this is 75 newtons by area of the piston is 35 into 10 power minus 4 plus PATM. So what about the atmospheric pressure? They have given you 105 kilopascals, but these are in pascals, okay. So 105 kilopascals means 10 cube actually here, okay. So this is 10 cube. Now the final answer should also be in kilopascals, okay. So if you want the final answer in kilopascals, you divide with 10 cube, okay. So normally this answer is in pascals, but if you want kilopascals, then divide a 10 cube in the denominator to all these values, divide a 10 cube, okay. Now if you cancel out some things, so 10 cube and 10 cube gets cancelled, this 10 cube 10 power minus 1 gives a 750 here, similarly this gives a multiplication of 10 here. So if you do this calculation, 105 plus 750 by 35, let us do 105 plus 750 by 35, 750 by 35 plus, okay, 750 by 35 plus this 15 into 98.1, 15 into 98.1 divided by 35, okay. So you have 35 here, fine. So 168.47 kilopascals, 168.47 kilopascals, correct? So we have 168.47 kilopascals. So I have a doubt in FM and TD in type of questions, when to consider atmospheric pressure and when not. Normally have to consider, why to neglect atmospheric pressure, okay, fine. So this is a simple question, okay. So 168.47, because we have solved some good questions on meta center and also I have thought of Amit sir has kept off this question, fine. So let us see. Now someone asked me about the Reynolds transport theorem in the beginning, okay. So now there came a question, okay. So we will see how to apply the Reynolds transport theorem, what is Reynolds transport theorem, and how to use this for linear momentum and angular momentum, okay. So how many of you want me to discuss a bit on this Reynolds transport theorem actually? Of course I don't do the derivation, that I have done in a detailed course many times, but right now I'll give you some results, but again I'll talk on the important aspects of Reynolds transport theorem. How many of you want this? How many of you want me to talk on this Reynolds transport theorem? Pesha, yeah, one doubt. Yeah, please go ahead. Sir, this impact of jets. We skipped one question or what in between? Okay. The force exerted, yes, jet. Fine. Today test question. Okay, doubt. Yeah, if you have doubts, please ask, no issue. Okay, comprehensive. Okay, all of you want? Fine. Okay, then I'll talk about it. Okay, so see here. First of all, if you say Reynolds transport theorem, what Reynolds transport theorem actually tells you is, for example, look, if you see, we analyze the systems in two ways actually. Okay, system analysis means differential analysis and control volume analysis. Okay, now if you see system, as you know, generally the basic difference between system and control volume, system is quantity of matter what actually exists, and control volume is some region in space which is under study basically, okay, which we focus on. Now if you see, for example, if you take a plate, okay, so if you take a plate, I'm going with a simple example I'll give you. So let us suppose if this is a plate. Now what happens is, let us suppose there is some fluid jet which is coming and hitting and transversing. So let us suppose some fluid is coming, hitting and moving in this direction, for example. Fine. Okay, now whenever you take a bit of control volume which is enclosed, so this plate, for example, okay, so let us suppose this is a control volume that you have taken. So for example, let us suppose we simple case to make you understand, this plate is fixed. Okay, this plate is fixed plate. Now actual system is this fluid which is inside the control volume. Okay, so the fluid which is inside this volume is system, and this is space whichever you are studying is actually your control volume. This is your control volume. Now inside this control volume you have some system, and now this system undergoes some change either in linear momentum or angular momentum depending upon the time. Okay, so as time progresses, then definitely what happens is this fluid will change certain things actually. Basically it can change its linear momentum or angular momentum, things like that. Okay, now if this is situation at time t, for example, now after some small time what happens, some new mass will actually enter this control volume and some existing mass will actually leave this control volume. Yes or no? Means if this is the system inside the control volume at some time t, now after some small time dt, what happens, some new mass will actually enter this control volume and some mass will actually move. Correct? Now whatever is the new mass that's available, we don't take that as control volume. Okay, I mean we don't take that as system, because system is some fixed matter, and whenever we are fixing the matter at this time t, if this is the amount of fluid which is under importance, if this is the amount of fluid which is under importance, for example, okay, if I call this fluid which is inside this as my system, now after some time my system will be looking something different actually. Okay, means if you see, this system will go something like this. This system will go like this. Okay, so system has changed some velocity or maybe its shape, something like that. Okay, but control volume is as it is. Now whatever the fluid that entered at this section, meanwhile because of this outflow, whatever is the fluid entered, this is not your system. Okay, because system has certain name, we have fixed the particles and we called only this particles as my system. So that's why system is that quantity of matter what you have selected. So whenever new mass is coming into the control volume, you don't call that as a system. Okay, now if you see the Reynolds transport theorem, of course I'm not doing the derivation now, in a detailed course we have done this. For any quantity b, actually here beta, if you say this is b by m, which is quantity per unit mass, intensive property. Okay, for any intensive property of the system, quantity per unit mass, we write the equation as dB by dt of the system. Change of the quantity of that particular system is equal to over the complete control volume, or we can write dou by dou t initially outside or inside the integration, doesn't matter. So dou by dou t of integral over the control volume, this rho times of beta into dv. So the meaning of this is beta is nothing but quantity for unit mass. Okay, so when you multiply that with volume basically, so here we have mass actually, so beta is nothing but b by mass. So when you multiply with the density, this density by mass gives volume here actually. Okay, so that's why this is quantity per unit volume multiplied with the dv and you are integrating. So this gives the change of that quantity in the control volume plus integral over the control surface beta times of rho into v bar dot n cap dA, which is the mass flow rate. This is a scalar quantity actually. Okay, so this quantity which is here is actually the m dot, okay, mass flow rate, which is the scalar quantity. So the main thing that RTD tells you is in control volume, whatever is the changes that's happening, this Reynolds transport theorem relate the changes in control volume to the changes in system inside the control volume actually. Okay, so that's how we have these equations. Okay, now anyhow, this is Reynolds transport theorem. Now when you apply it for the linear momentum equation, here actually if you see, this is relative velocity. Okay, this is relative velocity. Sometimes this control volume can also move. For example, if you take the case of turbo machines and all, what happens, the plate actually moves here. Okay, so the rho a v square for fixed plate. Okay, forget about the formulas. Okay, we'll see what are the formulas. But now if you see, this is how we get the Reynolds transport theorem. So this quantity tells you the change net quantity which is leaving the control surface. Okay, means if you have a control volume, then you have a control surface here, correct? Because every volume is bounded by some surface. So that's why this amount is nothing but whatever is the quantity, net quantity leaving the control surface actually. Okay, so this quantity is nothing but net quantity that is leaving the control surface. That is leaving the control surface. Okay, so that's leaving the control surface, and this is nothing but net quantity change in control volume. In control volume. Okay, so this is net quantity change in control volume. So this is control volume, sorry, conservation in the control volume. Yes, basically. Okay, so same thing. So now if you see, in case of steady state, this term which is basically the quantity change inside the control volume, that quantity will go to 0 actually here. Okay, so in case of in steady state or at steady state, we observe one thing, that at steady state dou by dou t of change of this property in the control volume, this quantity will be 0 actually here. Okay, because rate of change of the total quantity inside the control volume doesn't change with time, so that's why this is 0. So therefore dB by dt is this. Now if you take for example, so let us say here, now therefore if you take quantity as momentum for example, okay, so let us take, if you take this as momentum is nothing but mass into velocity vector. So that's why mass into velocity, if you take momentum as per RTT, this gives you d by dt of momentum, which is nothing but force, correct? This is nothing but d by dt of momentum is equal to, of course at steady state, if you see, integral over the control surface beta times rho b relative dot n cap ds, or dA, sometimes you write dA or ds, dA, let us write dA, no issue. Okay, S is surface basically. Okay, so control surface, or we write elemental area dA. So this is what you have. Okay, now here if you observe carefully, this term which is here is the mass flow rate term, and here if you observe one thing, this beta is nothing but b by m is what I told you. So mv bar by m. So this gives you velocity. Okay, so this gives you velocity, or here generally you see relative velocity, because if we see control volume can move sometimes, so therefore we write this as integral over the control surface v r bar times of this dot product actually. Okay, so this rate of change of momentum is nothing but net force acting on fluid. Net force acting on fluid is equal to over the control surface whatever is the momentum rates that are changing. Okay, so this is how we get the linear momentum equation. Now the meaning of this integration is sum at all the quantities, but generally in our applications what we do, we keep some finite number of inputs and means basically some inlets and finite number of outlets actually. Okay, so whenever you have only one inlet and one outlet, these kind of situations, what we do, we will write the integration as discrete terms. Okay, so this gives you m dot vr out in the vector direction minus m dot v relative at the inlet basically. Okay, so outlet minus inlet gives you the net quantity which is leaving the control surface. Okay, so that's how we have the sigma f acting on fluid, because fluid is the system actually, the mass which you are taking, which is the fluid, that is the system. So net force acting on the system is equal to this quantity. Similarly, if b is angular momentum vector, mvr bar or angular momentum r bar cos mvr bar for example. Okay, so when this is your angular momentum, then rate of change of angular momentum, rate of change of angular momentum of the fluid is equal to, at steady state of course, integral over the control surface, then if you divide this with mass, r bar cos v r bar times m dot. Okay, so this is m dot for example. If you take this, this is mvr is nothing but the angular momentum rate change. Okay, so mvr bar, or generally you can write this as cos v r bar at outlet minus m dot into r bar cos v r bar at inlet. Now when you have this sprinklers and all, we take this angular momentum which is leaving out of the control volume minus which is coming into the control volume. Okay, so now if you want to apply this linear momentum equation, you should know two things. One is Reynolds transport theorem, second is Newton's third law of motion correctly. Okay, so what is Newton's third law of motion? If I ask you this, many people will say that every action has equal and opposite reaction, and the example they tell you is when you hit a ball onto a wall, the ball will come back. Okay, but actually the traveling of the ball is not the Newton's law of motion. Okay, Newton's law of motion is valid only when the bodies are in physical contact with each other. Okay, so try to understand this. Many people have this misconception that, let us suppose if this is a wall and if you throw a ball for example. Okay, so let us suppose if you throw a ball, then the ball slowly travels and finally it touches this and then it actually bounces back, or generally let us suppose if it bounces back in the same direction, for example in the same direction, so that you got the ball back onto the hand. Now Newton's third law is not this traveling of the ball and coming back of the ball. Okay, Newton's third law tells you that for every action equal and opposite reaction, correct? Now for example, if I take my mobile, and if I throw it onto the wall, then I won't get it back obviously, correct? Yes or no? If I take a mobile and if I throw it onto the wall, then definitely I won't get it back, because the reason is Newton's third law is not about this traveling of the objects. Okay, whenever two bodies are in physical contact, then if body A is exerting a force F on body B, then body B also exerts the same force on this. That's why if you want to apply the linear momentum equations, if you want to see what is the force exerted by the jet on the vane, that's equal to minus of the force exerted by the jet, the force exerted by the vane on the jet actually here. Okay, so anyhow, let us solve this question to understand this. Look, a 15 centimeter diameter jet of oil, relative density 0.8, strikes a stationary flat plate at an angle of 35 degrees to the normal. The force exerted on the plate when the velocity of the jet is 16 meters per second is dash. Okay, so let us take one empty slide and let me tell you how to apply the Reynolds transport theorem to this question. Okay, so see carefully here. So see carefully here. First of all, I'll draw a sketch. So see here, there is one plate. There is one plate, okay, a stationary flat plate at an angle of 35 degrees to the normal. Okay, so strikes a stationary flat plate. So let us suppose there is a stationary flat plate, for example. Okay, there is a stationary flat plate. Stationary flat plate. Now, a fluid jet is going and hitting this at some angle. Okay, so to the normal to this is at some angle like this. Okay, so normal to this is something like this. Then a fluid jet is coming and hitting this plate, for example. Okay, so fluid jet is coming and hitting this plate at some angle 35 degrees to the normal. Okay, so 35 degrees to the normal, for example. Okay, 35 degrees to the normal. So this is coming and hitting at 35 degrees to the normal. 35 degrees to the normal. Okay, so there is discharges also. Can you show, sir? Sorry, I didn't get this. So there are some comments. Just a minute. No, sir. It can be a bullet fired from the gun. Yeah, basically, if you see, whenever the bullet is leaving, the moment the bullet leaves, not traveling to the barrel, okay, you get the reaction when the bullet actually gets out of that spring, actually. Okay, so whenever the bodies are in contact, only the reaction force is applied. Look, whenever two bodies are not in physical contact, how can they apply reaction on each other? Correct? Understood? Clear? Did you understand this? Even gravitational force has a reaction only when you are touching the feet. Okay, otherwise reaction won't be there. If you are floating in air, then you have only some buoyancy. You don't have any reaction force, normal reaction. Understood? Is this clear to you? Did you understand this? Is this clear to you? Normally, if two bodies are not in physical contact, they cannot exert forces on each other, correct? Unless there is some magnetic effects or something. But normally, in case of mechanical forces, you cannot actually apply forces on them. Okay. Now, let us see. Let us slightly change this diagram anyhow. So if you see, let us slightly change this diagram actually. Instead of taking this, let us take this a bit inclined, okay, so that it will be easy for you to understand. So let us suppose if this is inclined. So this is the normal direction to the plate. So let us suppose this is normal direction to the plate. Okay, so this is normal direction to the plate. Now let us say fluid is coming and hitting this at some angle. So there is some fluid which is coming here. Okay, so some fluid which is coming here. So this plate is fixed. The angle made with the horizontal is 35 degrees. Okay, so 35 degrees to the normal. So let us say this is 35 degrees. For example, okay, so this is 35 degrees. Now the fluid is coming like this, and let us say some part of the fluid is moving in this direction and some part is coming in this direction. Okay, so it got splitted. So some part of the fluid got in this direction. Okay, now Q1 and Q2 when plate was inclined. We'll see what about Q1 and Q2. Okay, so see here. Let us try to understand this first. Now, see here. In this case, because I have taken this intentionally, so that one particular force will be 0. Okay, so tangential force. So I have taken this because intentionally we can show one force to be 0 in this case. Okay, so let us suppose because of this motion there is no tangential force actually. Okay, so there is no tangential force. The fluid is coming and smoothly sliding. Okay, so no tangential force. Tangential force. Okay, so no tangential force. Fluid smoothly slides over the plate. Fluid smoothly slides over the plate. Slides over the plate, because sometimes choosing the coordinate system correctly can actually simplify your question. Okay, so let us suppose if we take xy coordinate system, then it will be little lengthy in calculation. But if I do it in the normal and tangential components, we know since the plate is fixed, the tangential component is actually 0 along the length of the plate. Okay, so that's why ft is 0. So let us calculate only fn, normal reactions. Okay, so if you know fn, then this fn is directly one of these options. Okay, so how to do this? See carefully here. How to choose the things? Now see carefully. Let us suppose if you take n, normal direction and tangential direction, for example. Okay, so we have normal and tangential directions like this. So whenever you have normal and tangential directions like this, when you have the plate like this, okay, so let us suppose if you take the plate, it is some inclined. Okay, so plate is along this inclined, and you have some to this plate, and the fluid is coming, approaching along this path. Okay, so this angle is 35 degrees. Clear? So this is 35 degrees. This is 35 degrees. Okay, so whenever this is 35 degrees, the fluid is sliding like this. So if you take the control volume, if you take this control volume, if you take this control volume actually here, now one thing is fine, try to understand this. This fluid will not split to equal halves, correct? So some part of the discharge goes in this direction and some part of the discharge go in this direction. This is Q2. Okay, and let us say this angle is theta for the time being. Let us do the general terms and then let us see the things. Okay, so this angle is theta, and here there is some discharge of Q1 and discharge of Q2. So here you have a Q. Okay, so now my system is the fluid, control volume is this orange shaded line. Okay, so let us suppose I'm doing the analysis over two coordinates, n and t coordinates. Okay, now if you see, then in this case, if you see, no tangential force. Okay, so fluid smoothly slides over the plate. Okay, now in this case, if you see, sigma ft is 0. Okay, so what about sigma ft being 0? Actually, first of all, discharge, total discharge is equal to q1 plus q2. Okay, so q1 plus q2. Now total tangential force is equal to 0. This means momentum leaving out in tangential direction minus momentum leaving or momentum entering in tangential direction is equal to 0 here, correct? Why I have written 0 here is, look, sigma f acting on plate in tangential direction is equal to minus of sigma f on fluid in tangential direction. Yes or no? Because the fluid and plate are in contact with each other actually. Okay, so whenever these two things are in contact with each other, this sigma f on plate by t is equal to minus sigma f on fluid at t. Okay, clear? So a lot of comments actually. What about gravitational force? Bodies do have physical contact there. Look, for one force to exist, you need not have physical contact. Okay, but actually for the reaction to exist, look, whenever if you take an aeroplane for example, gravitational force acts on the aeroplane, but aeroplane doesn't exert any reaction in the universe. Okay, so whatever is the fluid that is in contact, only that shows some resistance to that. Okay, when gravitational force is acted on the airplane do not show any reaction force in return. Okay, so that's why action reaction force pair will always exist only in case of physical contact. Clear? Understood? It experiences gravitational force, but flight do not produce any reaction force on that. Okay, so for action reaction pair to exist, you should have contact always. Understood? Like normally the case when you have two bodies in contact. Gravity is a conservative field. Okay, gravity acts on any body, but the reaction force exists only when you come in contact. If reaction force can make the airplanes fly, then obviously no need of aerodynamics. Okay, no need of any lift generation. Flight gravity will be pulling the flight down, then flight will produce some reaction force and will fly, but that won't happen. Okay, clear? So anyhow, let us see here. So sigma F on plate is by fluid. If you want, we can write one more thing, by fluid is equal to minus sigma F on fluid by plate in tangential direction. So since this quantity is 0, this quantity is also 0. So if we apply Reynolds transport theorem, this rate of change of momentum of the fluid in tangential direction is equal to sigma F of fluid in tangential direction. Okay, so this is what I've been telling you here at this case. Okay, in one direction if you apply, then sigma F on fluid in one particular direction is equal to velocities in that particular direction. Okay, so that's how you have this tangential direction, sigma F acting on fluid in tangential direction on fluid in tangential direction is equal to momentum changes in tangential directions. Okay, so now when you make this quantity equal to 0, so this, if you see, now what is fluid momentum leaving out? Q1 fluid is leaving at, let us suppose if this velocity is v, then there is no friction, smoothly sliding, then Q1 is moving at the velocity of v, so rho times Q1 into velocity in the tangential direction is v, plus then this part is coming in the negative tangential direction, so rho Q2 into, but that is going out, so this plus is because the fluid is coming out, but this minus is because the velocity is in the negative direction of the tangential direction. Understood? Did you all understand why this plus and this minus here? Because plus is because the fluid is moving out, so it's a positive quantity, but the velocity is in the negative direction, so that's why we have taken a minus v here. Okay, can you understand this? Why we have taken a minus sign here? Is this clear to all of you? So type in the chat box, is this clear to all of you? Did you all understand why we have taken a minus v here? Because at this location, this Q2 discharge is coming down in the negative direction. We have taken T in the positive direction, so that's why we have replaced it with a minus actually here. Okay, this plus and minus signs play very important role in applying the Reynolds transport theorem. When you take certain directions, the flows which are happening in the, or the velocities or the quantities which are in the reverse directions should be kept with minus signs. Okay, so this is minus. Now this complete mass is coming into the control volume, so rho Q, which is Q1 plus Q2, into what is the velocity in the tangential direction? Look, in the horizontal, for example, let us say in this direction, the velocity is v. So if you resolve this into tangential and normal components, if you resolve this v into tangential and normal components, for example, then we know the angle between this normal and horizontal, this velocity is theta, so this is theta, so this is v sin theta actually here. Okay, and this is v cos theta. Understood? So basically here, if you see carefully, the angle between the normal and this flow is theta, so with normal and flow the angle is theta, so this is v cos theta and this is v sin theta actually here. Okay, so this is in the positive direction, because if you resolve, the component will be in the positive upward direction, so v sin theta is equal to 0 in this case. Okay, so this v sin theta is 0 anyhow. Okay, so that's how by simple resolution you will come to know that what are the discharges. Now if you cancel some common terms, density gets cancelled. Okay, so v also gets cancelled all over, so when v gets cancelled, Q1 minus Q2 is equal to Q sin theta, and Q1 plus Q2 is total discharge. So if you simplify this, then 2Q1 or Q1 is equal to Q by 2 times of 1 plus sin theta, and Q2 is Q by 2 times of 1 minus sin theta actually here. Okay, many people mug up these expressions as 1 plus cos theta by 2 and 1 minus cos theta by 2, but which is theta, basically what angle is theta has to be observed carefully. Okay, so many times what they do is they take this angle as theta and then they write cos theta expressions here. Okay, but whenever theta is with normal, your discharges will be of this form. Okay, so that's why you have to be little careful. Okay, so anyhow, tangential force is 0. Now how to calculate the normal force? Let us see. Okay, so tangential force is 0. How to calculate the normal force? Sigma Fn acting on fluid, sigma Fn acting on fluid or what we want actually, the force exerted on the plate when the jet is moving. Okay, so on the plate, sigma F on plate is equal to minus sigma F n on fluid. Correct? So this is equal to minus of sigma F on fluid is m into V out in the normal direction minus m into m dot times V in the normal direction. Okay, so if you see at the outlet the flow is completely tangential. Okay, so at the outlet that flow is completely tangential, so you don't have any normal velocity component. So that's why this quantity is 0 actually. Okay, because at the outlet the flow is completely tangential, you don't have any normal component, so that's why this term is actually 0. Then minus of minus gives plus m dot times V inlet in normal direction. Okay, so m dot times V inlet in normal direction. So let us see what is m dot, rho times of q, total q, into velocity in the normal direction. So what is velocity in the normal direction? Your velocity is something like this. Okay, your velocity is something like this and the normal direction is this. So this is theta. So we have V cos theta as the answer here. Okay, so V cos theta is the normal direction. So V cos theta is what you have here. Okay, so the normal direction force on plate, sigma Fn on plate is equal to rho qv cos theta. And what about q? Rho into q is nothing but area into velocity. So rho a v square cos theta is what you have here in this case. Okay, so theta we have taken with normal actually. Okay, so that's why rho a v square times cos theta. So if you do this calculation, rho, which is 10 cube, it is water, correct? No, it is given some fluid of L2 density. How much is this? 0.8. So 800 is the density. Units are in newtons. Okay, fine. So 800 into, what about area of the jet? Jet is having some diameter, a 15 centimeter diameter jet. Okay, so pi by 4 times of 0.15 square. 0.15 square. So rho a v square. What is the velocity of the jet? 16 meters per second. So 16 square into theta. We have taken theta with the normal. So theta is given something around 35 degrees. Okay, so cos 35. This is cos 35 degrees. Okay, so did you all understand how did we get this? How V out is 0. Okay, sorry, u into 800 pi by 4 d square. Yes, pi by 4 d square, right? So how V out is 0? Because we are writing normal direction force components. Okay, so the velocity at the outlet in normal direction. So if you see, the flow is moving out tangentially along this. Okay, so the flow is moving out tangentially, so there is no flow which is leaving this control volume normally. Okay, so that's why V out in the normal direction is 0. Clear? Did you understand how did we get this V out in the normal direction 0? Yes or no? So please type in the chat box. Did you understand how we have written this quantity is 0? Because there is no velocity in the normal direction at the outlet. Clear? Did you understand, Joyshi? At the outlet, fluid is not moving in the normal direction at the outlet. Okay, so that's why there is no velocity at the outlet. Clear? So that's why it is 0. So if you perform this calculation, okay, so I think just a minute. Let us perform this calculation. So 800 into pi by 4, 800 into pi by 4 into 0.15 square into 0.15 square. Okay, so 0.15 square into 16 square, 256 into cos 35 degrees. Okay, so this is in degrees. So 35 cos. Okay, so cos 35 degrees. 2964.6. 2964.6 newtons. Okay, so 2964.6 newtons is what you have. 2964.6. Okay, so if you check the answers, 2964. So 2958. Okay, so some small difference could be there here because this whenever you are calculating area and all, some decimals could be changing here. Okay, so if you normally calculate that area separately and all, 0.15 square into pi by 4. So people may take only till 0.17 and all. So that's why in this calculation. Last this some 5-6 difference could be there out of 3000. Okay, so 296 around 2960 newtons force is applied on the plate in the normal direction, which is nothing but the total force actually. Clear? Did you understand how to apply the Reynolds transport theorem basically? So here we have changed the plane along tangential and normal to the plane, then applying the force concept. Yes, correct. We have actually taken the coordinate system. We have chosen the coordinate system along the normal and the tangential directions. Okay. Otherwise, what we have to do? We have to take x direction and y direction, then take square root of fx square plus fy square, all these things. Okay. I hope some of you might have done that and got the same answer. But here, when you do this calculation, it will be little easy. How many of you have done this in x and y coordinates and then done the answer? Actually, to be frank, I need not do this. Okay, but I have done this just to show you the resolution. Okay, because otherwise what happens? You can directly, anyhow v out is 0. So directly you might have written this equation. Fine. Clear? So do you understand? I think Negisa is here. Hi, sir. So yeah, so basically this I have just shown you to show that both the parts will be not same and there is certain ratio between them. Okay, and never mug up this as 1 plus cos theta, 1 minus cos theta, these things. Okay, because if they change the angle, then you will be at risk. But doing these 2-3 steps in exam could save you from putting wrong answers. Okay, clear? Because that cos theta formula, whatever you are telling, is when this inclination is given theta, but here the inclination of the fluid jet is with normal to the plate. Okay, not with horizontal. Fine. Okay, so is that clear to all of you? So shall we go ahead? Okay, fine. So let's continue with the next question. Okay, this is some Reynolds transport theorem what I've given you. Then there is some simple question, 1 mark question again. Okay, so we have spent a lot of time on analyzing certain crucial things. Now let us try to solve this. If velocity potential phi is 10xy, then the magnitude of velocity vector at point 1 comma 1. So same like the stream function value. So whenever stream function is given, then yes. Okay, next question. So whenever the stream function is given, we have calculated certain things. Okay, now directly potential function is given, so they're asking you magnitude of velocity, which is one very frequent type of questions in GATE examination. Okay, so is there any ESC batch was there from GW today? You have launched for AE and SSC. Okay, ESC is in discussions. Okay, very soon you will come to know of it, but right now it's in the plan. Okay, and discussions are going on. That's it. That's all I can tell you. 14.142. Okay, so let us see. So phi is given to you. Okay, so phi is 10 times of xy. So if you have a velocity profile ui plus vj, then u is basically dou phi by dou x and v is dou phi by dou y actually here. Okay, so these are the two equations. So basically partial derivative with respect to x is u and partial derivative with respect to y is v. So u is equal to 10 times of y and v is just 10 times of x. So if you calculate magnitude, then this is 10 times of square root of x square plus y square. So this gives you 10 into what is the point? 1 comma 1. So square root of root 2. So this is 14.14, correct? Meters per second. What are the units? Meters per second. So 14.14, correct? We don't need a calculator because yes, 14.14 is correct because square root of 2 is 1.414 and 10 times of that square root is 14.14. Clear? 14.14 meters per second. Fine. Okay, so next question. It's a simple question again, 1 mark question. For the given velocity fields, which one or more of the following flows are steady and incompressible? Okay, so basically if it's incompressible, then this quantity doesn't matter. If it's steady or unsteady, things look same. Okay, so how do we check whether these are possible fluids? So how do you check these are incompressible cases? For incompressible flow, just now we have in today's session we have seen for incompressible flow. For incompressible flow, okay, so for incompressible flow, we know divergence of velocity is 0. So this implies dou u by dou x plus dou v by dou y is equally 0 for a two-dimensional flow. Okay, so here they have given you two-dimensional flow. Yeah, without calci. Okay, we can solve sometimes. So see here. So yeah, we have to check whether these velocity profiles are satisfying the continuity equation or not. Okay, so how do you check this? First of all, let us verify the options first one by one. First case, u, v. So let us see what are the functions u and v. So u is 4xy plus y square, 4xy plus y square, and v is how much? What about v? V is, what about v here? 6xy plus 3x. 6xy plus 3x actually here. Okay, so dou u by dou x plus dou v by dou y is equal to dou u by dou x of this quantity is 4y plus dou v by dou y of this quantity is 6 x actually here. Okay, so this is not equal to 0 by default. Okay, so this quantity is not equal to 0 by default. This equation gets satisfied only at some particular points. Okay, so that's why this equation, it doesn't satisfy the continuity equation, so it need not be an incompressible flow. Okay, next, second, u is equal to 2x square plus y square, 2x square plus y square, and v is equal to minus 4xy, minus 4xy. So this implies dou u by dou x plus dou v by dou y is equal to dou u by dou x of this quantity is 4x plus minus 4y. So this is okay. So dou u by dou x of this quantity is 4x, and this is with respect to y is minus 4x. Okay, because if you differentiate this, then the answer is 0. Okay, so therefore this is a steady incompressible flow. So basically it's an incompressible flow. Clear? So this is B is correct answer, A is not the correct answer. Then coming to option C. See, this is a bit slightly calculative option. U is minus x by x square plus y square, and V is how much? What about V? V is minus y by x square plus y square. So let us check what is dou u by dou x plus dou v by dou y. Dou u by dou x plus dou v by dou y is equal to, if we differentiate this partially with respect to x, let us see what we come. X square plus y square into minus 1 plus minus x into 2x by x square plus y square whole square, correct? Then plus differentiation of this quantity with respect to y actually. Okay, so if you do with respect to y, x square plus y square into derivative of minus y is minus 1 plus minus y into this partial derivative is 2y by x square plus y square whole square. Okay, so this is a simple differentiation of u by v rule. If you apply, then this implies dou u by dou x plus dou v by dou y is equal to minus x square minus y square minus 2x square. Okay, so okay, this is minus sign, right? UV rule. Sorry, just a minute. Here it should be minus sign, correct? If I'm not wrong. Right? Just a minute here. Okay, fine. Here also it is minus sign. Okay, because v into u dash minus u into v dash. Okay, so we have a minus sign. So if you see, this is x square plus y square. So this is total x square minus y square, and this is y square minus x square actually here. Okay, so total value is 0 in this case. So this is also some incompressible flow. So C is also correct answer. And D, if you check, this is 4y plus 2x. Okay, and this is some other quantity. I think it is not incompressible. Maybe u is equal to, what is the options? Okay, 4xy plus x square. 4xy plus x square, and v is 3x plus y cube by 3. 3x plus y cube by 3. Okay. So what about this calculation? Dou u by dou x plus dou v by dou y. Okay. So dou u by dou x is 4y plus 2x plus y square. Okay. So which is not 0 by default. Okay. So that's why only B and C are incompressible flows, but A and D need not be incompressible. Clear? So that's how only first option and option C basically here. These two are the options of incompressible flows. Clear? So please type in the chat box. Is this clear to all of you? Okay. So is this clear to all of you? Fine. So let us take one small break for 5 minutes because it's 11:30. 4 of us we have completed already. Okay. So 5 to us. Let us spend some time for 5 minutes. If you have any doubts, you can ask me. Did you all understand how to take the velocities and all in Reynolds transport theorem? Okay. Definitely we'll try to solve some XCPYQs. Okay. So at that time you'll be much more look at some really nice questions and really some little complicated questions of angular momentum like lawn sprinklers, all these things. Okay. No issue, but we'll come up with that. Don't worry. Fine. Okay. I hope all of you are liking this session actually, correct? We have covered some lot of different things actually from different domains actually, and from different chapters, from different concepts. Okay, so all these things. Reynolds transport theorem is again one very good concept that we could talk of. Okay, fine. So anything that you want to know about GATE examination or anything that anything basically, like anything about GATE, all these things. Okay, am I audible now? Fine. So anything that you would like to know? No voice. So in tank case, if there are two different fluid for force calculation, we cannot take projection area. This question एक test में था. Okay, so basically you're talking about this what do you say, mixed fluids, means basically not mixed, basically this multi-layered fluids. Okay, so we'll see. Okay, you're asking about multi-layered fluid class. Okay, I understood. Means basically there's a tank. So in that tank some part is filled with one fluid, and above that there is another fluid. Then what is the hydrostatic force acting on the plate? Okay, this is what you want to know. Okay, I'll tell you that. No issue. Okay, I'll tell you. No issue for that. Then, so one thing that I would like to tell you here, because GATE examination is near, and I think maybe there are very few chances that we meet again, or maybe for one more session we can meet XCPYQs or something. I'll tell you one thing, guys. Look, in GATE examination, how many of you have already given GATE previously? How many of you have already given GATE examination? How can we expect this GATE 2023 ME paper? Because very less members have applied. To be honest, for IITs, it doesn't matter that how many of them have applied. Okay, paper level will be same. And more importantly, I'll tell you one thing. Paper is never set by a single IIT. Okay. For example, if IIT Kanpur is organizing GATE 2023, that means IIT Kanpur takes responsibility of website, examination centers, and forming a team for forming a team for setting the question paper. IIT Kanpur doesn't. IIT Kanpur don't set the question paper by itself. Okay. Always question paper is set from a faculty team from all the IITs and IISc. Okay, but you can predict something. Like for example, I'll give you an example. In 2019, okay, 3 years down the lane, GATE organizing institute was IIT Madras. Okay, when I was at that time in the campus, fortunately. So I'll tell you, normally for mechanical, if you see thermal sciences, okay, thermal fluids, these kind of branches, IIT Madras has a very good history in the past and also doing very well. So when if you observe carefully at GATE 2019 paper, nice questions or generally some little out of the box questions will be from thermodynamics, fluid mechanics, these kind of papers. Okay, so when a particular IIT is organizing GATE examination, it tries to send the team of that strong subjects in that particular IIT. Okay, means for example, if IIT Madras is strong in thermodynamics, fluid mechanics, these kind of things, actually it's not like others are weak, but comparatively it is much more robust. Okay, so if you see the team for setting questions from thermal or this kind of groups, there's a high possibility that it goes from IIT Madras. Okay, there's a high possibility. I don't say it went, but it might have gone actually. So similarly, if you analyze papers, actually manufacturing or design, these two are generally very good at IIT Kanpur. Okay, and the most important thing is initially when IIT Kanpur got established, the feeding to IIT Kanpur was from IISc Bangalore actually. Okay, so that's why normally the toughest institute to get a PhD in India, people believe, is IISc Bangalore followed by IIT Kanpur. Okay, so it happens always. But yeah, generally you can expect the question paper of same level like every year, maybe a little complicated, but things will be fine. Actually, the main advantage is when less number of candidates write the examination, even if you score little good, your score increases. Okay, basically means for example, let us suppose if only 3-4 thousand people are writing XE or hardly 4,800 something, then even for the less marks your score actually increases. This is one advantage. When similarly in mechanical, if you get almost 65 marks, 70 marks, your score may go to 758, 770, which could gain you some good jobs or maybe MTech admissions. These kind of things can happen. Okay, paper level will increase and it will increase day by day because the quality of teaching is also increasing day by day, because they are not full, so they will twist to any limit and they will maybe let them. Okay, obviously, because it's again GATE examination is one benchmark for all the technical evaluations. Okay, many PSUs take it. Okay, in MTech for MTech admissions in IITs and IIST also, Indian Institute of Space Science and Technology, you will get that, all these things. Okay, so we have a lot of things. And many of you who might have written GATE examination, there is one common feedback that student tells that, sir, I was not able to see few questions at the end. Time got finished. I was supposed to solve some more questions, but because of finishing of time, I didn't see the questions and all. So as soon as your exam starts, the first thing you should do is look at the question paper. Means physically they don't give you a question paper with a printed question paper, but you can actually see all the questions in the question paper. Okay, how come that happens is, look, for example, if you see GATE not GATE calculator, GATE 2023 official website. For example, there are some mock tests here. I want to show one future here, for example, to you. So mock tests link might be there. So mock tests be there here. So here, if you see, click here to take a mock test. Okay, so for example, if you take mock test, anything, for example, you take, for example, civil engineering. Okay, anything. Okay, when you take civil engineering, paper gets loaded. So this is how you start your exam. Basically, this is a mock test. So you have all the rules and all. You'll have enough time to go through all these things. Then after, once you click ready to begin, so as soon as you click ready to begin, your examination starts loading. Okay, so your examination starts. And many times what happens is, now people will try to solve this first question. If they don't know the answer, then they'll go for the next question. Okay, then if they know the answer, they'll mark it. So they'll go in a random way. But this is not very suggestible actually in gate examination exclusively, because in gate examination the kind of questions you have some numerical answer type questions, you have some MCQs. Okay, so let us suppose for example you have two MCQs in the beginning. Okay, now let us suppose you solved an MCQ and you got an answer which is not in the four options, for example. Okay, then in that case what happens is you will start feeling stress and all. Okay, so in the first 30-40 minutes your mindset will completely go out of the box, and you cannot do anything better. So once you start the exam, first thing that you should do is, if you go a bit up, actually here there is one button which is called question paper. Okay, so you should click that question paper. So what happens when you click that question paper is, all the 65 questions come in a PDF. Okay, so you can see all the 65 questions comes as a single PDF. Now the thing that you should do is, what I have done exclusively when I have written exams in the past is, definitely there will be few subjects which you are good at, or you have prepared well in that subjects, and some few subjects which you are not maybe done enough preparation on that. Okay, so in that what you will do is, for example, if I initially what I have done in on Scribble pad is, they'll give you a Scribble pad. So on Scribble pad I used to write the subjects names. Okay, for example, fluid mechanics, thermodynamics, heat transfer, okay, some other machine design, theory of machines, like this. So what I used to do is, when I look at this paper, for example 15th question, thermodynamics. Okay, so at near thermodynamics I used to write 15 comma, then 16th question, theory of machines. At theory of machines I used to write 16. Like this I used to split the question paper into subjects. Now I know what are the subjects, I know it, so I used to go to that particular question numbers. Okay, so then this is how I have solved initially. And sometimes it's possible that from the subjects what you have prepared very well, some tough questions might come out. Okay, so don't get discouraged, but if paper is tough for you, then it is tough for all over India. Okay, not only for you. So prepare well. For example, in 2021. Okay, fine. Own method, I don't know what is own method, but normally this is the approach I have followed, and it went fine actually. Okay, so this going through these questions should be very going through all the questions, at least visiting all the questions should be done before the time. Okay, so once the time in the last 30 minutes it should not be the case like you haven't seen few questions yet. Okay, you might have seen all the questions by that time, and then that will boost your confidence, because once you start writing first 20-25 questions in the first 1 hour, that means you're already gate qualified in the first 1 hour, and then it will definitely help you out for further marks actually. Okay, because that creates some positive mindset to you. Okay, so that's why my suggestion is basically you can go through this question paper tab and you can go for all these questions first. Okay, so once you visit all these questions, then you can decide on how to solve the questions or which questions to solve, all these things. Clear? So anyhow, this is a simple thing that I thought of giving you. Okay, clear? So shall we continue the discussion? Okay, many of the students, they don't know about this question paper tab. Okay, yeah, so many students, they don't know about this question paper tab, and they just start answering the questions randomly. Okay, that won't be much helpful to you. So how to revise maths? Just follow your technical subjects thoroughly, all your maths gets covered. Okay, seriously, I'm telling this. If you want probability and all, go for some operations research. Okay, then PET and CPM, queuing theory, all these things, you will understand what is probability. Okay, similarly, if you want matrices, then you can go for strength of materials. Okay, or maybe theory of machines, vibrations, you will easily understand. Again, in practical, eigenvalues, what are you calculating are the principal stresses of a stress tensor. These kind of things if you know, then actually you should never study maths as a separate subject. Okay, maths should always be studied as a supporting tool for your core subjects. Okay, so if you do that, then definitely it will give you very good nice marks. So in GW exit essays, marks is not coming good. What to do? Maybe check with your application. Okay, so because when you solve some questions, there could be some common mistakes that you do generally. Okay, and some repetitive kind of mistakes can also happen. Okay, so please make sure these kind of things don't happen. Okay, and these kind of things don't happen, then things will go fine at the end of the day. Okay, fine then. Last question, sorry. this time in XC, what would be a good score as students are very less? I'm telling you, focus on 65, 70 to 75 marks. Okay, that will definitely give you a good score. Okay, focus on marks 70 to 75, somewhere in between. Okay, fine. So let's go for the next question. Oh, sorry. Yeah, this question. A 25 centimeter diameter jet exerts a force of 950 newtons in the direction of flow against a flat plate, which is held inclined at an angle of 30 degrees with the axis of the stream. The rate of flow will be dash liters per second. Okay, so basically they have given you this impact of jets. Okay, so if you see, there is one plate. This plate is inclined at 30 degrees, at an angle of 30 degrees with the axis of the stream actually. Okay, so means the axis of the stream is something like this. Okay, so this is inclined at 30 degrees. This is inclined at 30 degrees. Okay, so this angle is 30 degrees. 30 degrees. Okay, so a 2.5 centimeter diameter jet exerts a force of 950 newtons in the direction of flow. Okay, so this is exerting in the direction of flow against a flat plate which is held inclined at an angle of 30 degrees with the axis of the stream. So this angle is 30 degrees. Okay, of course. Now in this direction, x direction, fx, in the stream direction, the force exerted is how much? 950 newtons. Okay, so this is 950 newtons. Then they are asking you what is the discharge. Okay, velocity is given. Okay, it is coming at some velocity. Okay, velocity is not given. Fine. Anyhow, jet diameter is given. Okay, so it is given that the jet exerts a force of 950 newtons in the direction of flow against a flat plate. Okay, so what is Fx on plate? Fx on plate is equal to minus sigma Fx. Sigma Fx on plate is equal to minus sigma Fx on fluid. Okay, so on fluid, which is minus m dot v out in the x direction minus m dot v in the x direction. Okay, so now if you see the fluid after coming like this, some part of the fluid will go in this direction and some part of the fluid will come in this direction. Okay, now here if you see, this angle is 30. Okay, now this angle is 30. Now we are 1 plus cos theta by 2 and 1 minus cos theta by 2. These things will work out. Okay, so if this is q1 and if this is q2, then and this is some velocity. Okay, this plate is inclined at some 30 degrees. So in that case, this q1 is equal to q by 2 times of 1 plus cos theta, and q2 is equal to q by 2 times of 1 minus cos theta. Okay, so this is 1 minus cos theta. Clear? So q by 2 times of 1 minus cos theta. So this implies, so because of this minus sign, you can swap these two terms. Sigma Fx on plate, sigma Fx on plate is equal to m dot v in the inlet minus m dot v in the outlet directions. Okay, in x direction, of course. This is also in x direction. Okay, now if you see carefully here, now m dot v, so what is this q1 and q2? We know basically from these ratios, because this angle is theta. So therefore this sigma Fx on plate is rho q. At the inlet, complete flow is in x direction and it is coming at velocity v, minus at outlet, if you see, this q1 is moving at same velocity again. Okay, so it comes at velocity v, assuming no friction, so it moves at same velocity. So this is velocity v, and here also this is velocity v actually here. Okay, so now at the outlet, rho q1 into, so for this flow, if velocity is in this direction, then this angle is 30. So v cos theta is in the positive direction actually. Okay, so if this is positive x, this is positive, so v cos theta, v cos theta is what we have here, plus rho q2 into, now what about the velocity here? The flow is coming in this direction, so if you resolve, the x component will be in negative direction. Okay, so this angle between these two is theta, which is 30. So minus v cos theta, minus v cos theta. So is this clear to all of you? Did you understand why there is a minus sign here? Yes or no? So please type in the chat box. Did you get why there is a minus sign here? Minus v cos theta. So did you understand here why there is a minus v cos theta here? Yes or no? So type in the chat box. Please type in the chat box. Did you understand why there is a minus v cos theta? Because at the second part of the outlet, means the Q2 is having a velocity in the x direction in the negative sense. Okay. So because here if you see, whenever velocity is coming like this, if you resolve this fx and fy, then fx is in the negative direction. That's why. Okay. So this is in the negative direction. So that's why we have taken a minus sign. Okay. Now if you see, then this quantity, so rho q into v minus rho q1 is q by 2 times of 1 plus cos theta into cos theta minus rho q by 2 into 1 minus cos theta into cos theta into v, of course. Okay, so we have v. So this is the term. So what they want actually, discharge, correct? They are asking you what is the value of discharge actually. Okay, now this velocity can be written as discharge by area. So sigma fx on plate is equal to rho qv. If you take out rho qv, v can be written as q by area of the jet into 1 minus, then this is 1 plus cos theta into cos theta by 2. So cos theta times of 1 plus cos theta by 2 is what we have. Then minus of minus plus, we have plus cos theta into 1 minus cos theta by 2. Okay, so this is the equation. So theta value is known to us, which is 30 degrees. Okay, so theta value is 30. Now if you simplify this expression, then minus cos theta plus cos theta by 2. Okay, so minus cos theta by 2 and plus cos theta by 2, then minus cos square theta by 2 minus cos square theta by 2. So total cos square theta actually. Okay, so sigma fx on plate is equal to rho q square by a into 1 minus, this is cos square theta by 2 and minus cos square theta by 2. So total 1 minus cos square theta. Okay, so what you need from this, you need discharge value. So discharge is force acting in the x direction. So what is force acting in the x direction? Sigma fx on plate into area by density times of 1 minus cos square theta. Correct? So this is what you have here. So correct, calculations are fine, right? So 1 minus cos theta by 2 plus cos theta by 2, these two gets cancelled. So cos square theta by 2 minus cos square theta by 2. So total cos square theta. Okay, so a by 1 minus cos, a is multiplied here, and rho and 1 minus cos square theta is calculated and a square root here. Okay, so we need a square root. Now what about area of the jet? They have given 2.5 centimeter diameter. Okay, so let us see square root of force F value. So what is F value here? F is, this is exerting a force of 950 newtons. Okay, so 950 newtons into pi by 4 times of diameter square. So what about diameter square? This is 2.5 centimeters. So 0.025. Okay, so 2.5 by 100. So 0.025 whole square by density of the fluid. Okay, so what is the density of the fluid? It's a water, correct? So it's a flat plate actually of the steam. So nothing, fluid is nothing mentioned, right? Diameter jet exerts a force of 950 newtons in the direction of flow against a flat plate which is held inclined. So let us take the fluid is water. Okay, so fluid is water. So 1000 into 1 minus cos square theta. So cos 30 is root 3 by 2. So cos square theta is 3 by 4. So 1 minus 3 by 4 is 1 by 4. Okay, so this is 1 by 4. Clear? So this value is 1 by 4. Okay, so now if you simplify this, 4 and 4 gets cancelled. So if you multiply this value, 950 into that 0.025 square, 0.025 square. Okay, so 0.025 square into pi is also there. Okay, so into pi by 1000 by 1000. Okay, so this is by 1000. So this is the value. So take a square root of this. Okay, so when you take a square root of this, 0.0431. Correct? So 0.0431 meter cube per second. So 43.1 liters per second. Correct? Yes or no? What is the answer that you are getting? I'm getting 43.1 liters per second. So please check this calculation. Okay, so 43.1 liters per second is what I'm getting here. Okay, sigma fx on plate into area divided by density into 1 minus cos square theta. Okay, so theta is 30 degrees, so cos square theta is 43.189, correct? Yes, I think 43.189. Yes. Okay, so 43.2 almost 18 meter cube per second. So 43.2 liters per second is what you have here. Okay, so 43.2 liters per second is what we get here. What we are getting here. Yes, 43.189 basically, correct. 43.189 liters per second, which is 43.2 liters per second. Okay, but did you all understand how we are taking the direction of velocities of the jets? Okay, how we are splitting the discharges, all these things that should be taken with care. If you keep any plus or minus difference here, that's it, answer will change. Okay, so 43.2 liters per second is the correct answer. Okay, so is that clear? So please type in the chat box. I got 43.189. Are you all getting 43.189 by performing this calculation? Simple calculation, right? 0.025 into 950 into pi by 4. That's it. Okay. How many of you got the same answer? So please type in the chat box 43.189. All of you. Everyone should type in the chat box. Whoever got this answer should type in the chat box 43.189 liters per second. Correct? Sukumar, Ismail, Roshan, sorry. But Jyoti, Punab. Okay, fine. Great. So let us solve the next question. Oh, sorry. I think this is the question. So air at density 1.1 kg per meter cube, dynamic viscosity 1.7 into 10 power minus 5 Pascal second, flows with a velocity of 20 meters per second in a 12 centimeter diameter pipe. If the friction factor is 0.02, then the shear stress at the wall is dash. Okay, so how do we calculate the shear stress at the wall in a pipeline? Internal flows. Okay, flows through pipe actually. So how do we calculate this? How do we calculate this? Okay, so density A is flowing. Okay, so density is 1.1 kg per meter cube. Dynamic viscosity is how much? 1.7 into 10 to the power minus 5 Pascal second. Okay, flows with a velocity of 20 meters per second. So when they give a uniform velocity, that means they are talking about the average velocity. Okay, so V average is 20 meters per second. 20 meters per second. Okay, and the friction factor F is 0.02. 0.02. Then the shear stress at the wall, so tau wall is how much? Okay, in pascals. They are asking in pascals. Okay, and they have given you some options also, kind people. So tell me how we can do this. We need the shear stress at this wall, pipe wall actually. Okay, so how do we calculate this? So what is the relation between wall shear stress and these things, pressure gradient and all these things? So type in the chat box. How do you calculate? You have the friction factor actually. Okay, so friction factor is also known to you. So wall shear stress, how do you calculate the wall shear stress? Tell me. dp by dx into r by 2. Correct. Now who will tell you the dp by dx value, pressure gradient value? Yes, correct. Pressure gradient into r by 2. Correct. Yes, I agree. But how you will get the pressure gradient value? Okay, B is the correct answer, of course. Okay, fine. But let us go in a sequence. Who tells you the pressure gradient value from this equation? How do you calculate the pressure gradient value? HF say. Okay, HF. There is no expression for HF. Okay, fine. So see here. Normally how I do is I generally keep this velocity profile in mind. So in a pipe, velocity at any radius is given by r square by 4 mu into minus dp by dx into r square minus r square. Okay, so this is what you have here. Okay, so this is the quantity that we have. Now if you want this maximum, if you want this V max, then this quantity is 0, smaller is 0 here. Okay, and V max is nothing but 2 times of V average. Okay, because in case of pipe flow, 2 times V average by V max is actually 2, so that's why 2 times of V average is equal to radius square by 4 mu into minus dp by dx actually here. Okay, so r square by 4 mu into minus dp by dx is what you have here. Okay, so minus dp by dx. Okay, so 1 minus, when you take r square here, this is 1 minus small r square by capital R square. Correct, so this is what you have. Okay, now when you equate this to 0, because at maximum velocity is at center line, so when I will calculate dp by dx. Acha, I'll calculate dp by dx. Kahan se okay, I asked you from where will you get dp by dx. You're telling I'll calculate. Fine. Anyhow, I'll calculate. So see here, this is r square times of r square by 4 mu times minus dp by dx actually here. Okay, so here they have given you 2 times of v average. So average velocity is given to you. So what is average velocity? 20. Okay, so this is 20. Just a minute guys, they have given dynamic viscosity as Pascal second, right? Okay, fine. So 20 is equal to radius square. So what is radius square? This is a 12 centimeter diameter pipe, so 6 centimeters is the radius. So 36 into 10 power minus 4 divided by 4 into dynamic viscosity. Okay, so Pascal second. So dynamic viscosity value is 1.7 into 10 power minus 5. 1.7 into 10 power minus 5 into minus dp by dx. Minus dp by dx. Okay, so from here you can calculate the pressure gradient. Correct? So please calculate pressure gradient value. What is the pressure gradient value from this equation? So please tell me, what is the pressure gradient value from this equation? So type in the chat box. What is the pressure gradient value from this equation? So pressure gradient value. So tell me here. Anyhow, this is 10 power minus 1. So this gives you 10. 4 cancels out this 9 times. Then 10 cancels out this 2 times. So total 4 is equal to 9 by 1.7 into minus dp by dx. Okay, so dp by dx. So minus dp by dx is equal to 4 into 1.7, which is 6.8 by 9 Pascal per meter. Okay, so this is the pressure gradient value, 6.8 by 9. What is the value here? Correct, 6.8 by 9. Yes or no? Because we have a 4 here, so 4 is equal to 9 by 1.7 is left over here. So 4 into 1.7 gives you 6.8. So 6.8 is this 6.8 by 9. So what about wall shear stress? So wall shear stress is minus dp by dx into r by 2. So which is 6.8 by 9 into 6 by 6 centimeters. Correct? So this is 10 power minus 2 by 2 actually here. Okay, so this is in pascals. So what are the units they're asking? This is in pascals. Okay, so here we have substituted everything in. Correct, right? V meters is in this. dp by dx is not known to you. R square by 4 mu. Okay, so I think everything is fine here. 0.755. Yes. So when you get this 0.755, yes, 0.7. Sorry, you're typing something. 0.755. Yes, 0.755 basically here. So this is 0.755. Now when you calculate this value whichever is here, dp by this value is in SI units, right? 2 into V average. Average velocity is 20 meters per second. Okay, so average velocity is 20 meters per second. So 20 is equal to this quantity. So 4 is equal to 9 by 1.7 into minus dp by dx. Okay, so the minus dp by dx is 6.8 by 9 Pascal per minute. So tau w, wall shear stress, is minus dp by dx into capital R by 2. So if you do this calculation, then let us see. So 3 table 2 times and 3 table 3 times. 2 gets cancelled. So 6.8 by 3 into 10 power minus 2. 6.8 by 3 into 10 power minus 2. So 10 power minus 2, 0.01. Okay, so 0.022 is what we are getting. is this equation v of z at any location r square by 4 mu into minus dp by dz of course partial gradient into 1 minus small r square by capital R square, correct? Yes or no? So once please type in the chat box this equation, because normally I write it from the Navier-Stokes equation every time. So capital R square by 4 mu into minus dp by dx. But normally for a this dynamic viscosity value, I think this is the units are actually, you know, I think this is kinematic viscosity value because value is much smaller actually. Okay, I think we have to multiply density to this and then we have to go. So once check the calculation. Wall shear stress is what they're asking in pascals. Okay, minus dp by dx into r by 2. Yes, this is fine. So we have radius. It's a 12 centimeter diameter pipe, correct? It's a 12 centimeter diameter pipe. Okay, so this is 12 centimeter. So 12 by 2 is 6. Then 6 into 10 power minus 2 meters by 2. Okay, so 6.8. But this equation V max is equal to, so r square by 4 mu times minus dp by dx into 1 minus small r square by capital R square, correct? Let us check the units. First of all, r square meter square by 4 mu. So Pascal per meter. So Pascal second. We have Pascal second into Pascal per meter. Okay, so Pascal per meter into this is dimensionless quantity. So meters gets cancelled and Pascal get cancelled. So meters per second is velocity, correct? I think it is correct. Dimensions wise it is correct. Yes. So dimensions wise it is correct. Okay. So then definitely this is the correct answer because at maximum location this radial location is 0. Maximum velocity occurs at r equal to 0. So when you put r equal to 0, this equation turns out to be r square by 4 mu times minus dp by dx. At this is V max. So maximum velocity is 2 times of the average velocity in this case. So 2 into 20 is equal to r square 6 centimeters. So 6 into 10 power minus 4, correct? Yeah, 6 centimeters is 6 into 10 power minus 2. So square 36 into 10 power minus 4 by 4 into dynamic viscosity 1.7 in 10 power minus 5. Then this cancels out a 10 on the top. 4 9s are 36. Then this 0 cancels out this 0. 4 equal to 9 by 1.7 into pressure gradient. So pressure gradient is 6.8 by 9 Pascal per meter. Then tau W 6.8 by 9 into 6 into 10 power minus 2 by 2. I think this calculation is correct. Okay. We check first flow is laminar or turbulent generally. Okay, but friction factor 0.02 is generally for a high, 0.02, correct? So friction factor is 0.02. So friction factor 0.02 generally this range. For a pipe flow normally if you see F is 64 by Reynolds number. So Reynolds number in this case is 64 by 0.02. So this value will be how much? 64 by 0.02. Okay, so 3200. So this is in transitional range. This is in transitional range. Okay, so okay, fine. Then this is in transitional range. Okay, fine. So this is transitional in range. Okay, so yeah, we didn't use friction factor. So basically what happens, whatever the analysis that we have done, this is for the laminar analysis. Okay, but here if you see, this is beyond 2300 for internal flows. Okay, so this value is greater than 2300. So we can say the flow is transitional in this case. So we can basically laminar results couldn't give you correct answers. So here if you see, flow is transitional. Flow is transitional. Okay, so whenever flow is transitional, so we'll go for turbulent analysis. So in turbulent flows, what is the relation between shear stress, wall shear stress and friction factor and density of the fluid? So please tell me, in case of turbulent flows, what is the correct relation between F, tau W and density? So type in the chat box. So type in the chat box, what is the relation between wall shear stress, density and friction factor? Any idea? So all of you type in the chat box. So type in the chat box. Look, here head loss is not given to you. Understood? FLV square by OGD can be applied, but here head loss is not actually given to you. Okay? Clear? So since head loss is not given to you, you cannot apply this HL is equal to FLV square by 2GD, all these things. Okay, fine. This Reynolds number here in this case is 3200, so it is in the transitional range. Okay, so we cannot apply the lambda results here, of course. So this velocity profile, whatever we have done, this is correct only when this Reynolds number is actually less than 2300. Clear? So but normally this is the procedure that how you do whenever things comes out in lambda case, and this answer is to be in pascals. Okay, so 6.8 by 3 into 10 power minus 2 here in the case of lambda regime. Okay, and in case of turbulent flows we have this relation as some empirical relation actually here. Okay, yeah, fp square into O by 2d. Clear? So dou p by dou x is f over v square by 2d is what you have here in case of turbulent flows. So here if you see dp by dx is f rho v square, or rho f v square is what generally write, rho f v square by 2d is what you write generally here. Okay, v is average velocity is what you write. So from this equation we'll get dp by dx. So from this dp by dx we'll get this wall shear stress. Okay, and this is a negative quantity actually. Minus dp by dx is this quantity, rho f v square by 2d is what you have. Okay, so from this you calculate the pressure gradient and you actually substitute this pressure gradient here, then you'll get the answer which is matching with one of these results. Okay, so density is given to you and diameter, pipe diameter is also known to you, 12 centimeters is what you have. Okay, so kindly do this calculation, then you will end up with the correct answer. Okay, so let's go for the next question. So let us see this. A horizontal venturimeter of size 0.5 meters by 0.25 meters is used to measure the flow of oil of specific gravity 0.9. Okay, then the discharge of oil through the venturimeter is 100 liters per second. Then the reading in mercury manometer should be dash. Coefficient of discharge is 0.98. Okay, so coefficient of discharge is given. So first of all, when they give you the dimensions like this, 0.5 meters by 0.25 meters actually, then in that case, so see here, when you have a venturimeter, like this, so if you have a venturimeter like this, okay, so venturimeter, okay, so when you have a venturimeter like this, then in that case, let us suppose if you have some diverging section, normal diverging sections will be very narrower here. So fine. Okay, so compared to cone angles at inlet, at the outlet the cone angles will be low. Okay, here this happens because the flow actually accelerates in this kind of configuration. Okay, so and this is basically here if you see, if you maintain a higher cone angle at the downstream location, then there could be some concept of flow reversal, because of which flow actually cannot happen effectively. Okay, so that's why we actually keep this cone angle very less and this cone angle very high, and the flow will happen in this particular direction. Okay, so the flow will happen in this direction, and of course you have some pipeline here. Okay, so the pipeline is somewhere connected like this, and here also the pipeline is connected. Okay, so basically here also the pipeline is connected. Normally these two diameters will be same. Okay, so the diameters will be same here because it's the same pipeline. Venturimeter is connected between the same pipeline actually. So if you see a diverging section, fine, then let us see, we construct a venturimeter like this. Okay, fine. Okay, so now when this is a venturimeter, obviously at the downstream you have a lesser cone angle to avoid the system. Sorry, I didn't get this. Minu Bajaj. Okay, fine. So now if you see, we have some discharge here. Then when you connect a mercury manometer here, oil mercury manometer, one section is at the throat, which is at the minimum cross section, and one limb is connected at the uniform location of the pipe. Okay, so we connect one location at the uniform location of the pipe here. Okay, So now this is connected with the help of a manometer. Okay, fine. This is a manometer. Okay, now here you have some oil, and here normally if you see pressure P1 is slightly higher than this pressure at this P2. So obviously the flow or the manometric deflections will be something like this. Okay, and here you have some mercury which is filled over. Here you have some mercury which is filled. Okay, and here you have oil. Here you have some oil actually. Okay, so here you have some oil. Then this deflection is how much is what you want to tell. Okay, so this is the deflection shown by the manometer here. Okay, so they're asking you then the reading in the oil HC manometer should be dash. CD coefficient of discharge is 0.98. Okay, and here they are told you the flow through the discharge of oil through the venturimeter is 100 liters per second. Okay, so there is some flow, actual flow, which is maintained at some 100 liters per second Q. So let us solve this. Q actual is 100 liters per second. And what about CD? CD is 0.98. 0.98. So this means if you try to calculate the theoretical discharge, so Q theoretical is 100 by 0.98 is what you get. Okay, so 100 by 0.98, these many liters per second. Okay, so 100 by 0.98, 100 by 0.98 liters per second. So 102.04, 102.04 liters per second is what you have here. Okay, so 102.04 liters per second. Now whenever it is 102.04 liters per second, now how do you calculate this deflection H? Okay, now they have given you the venturimeter sizes. This is 0.5 by 0.25, and oil is of specific gravity 0.9. Okay, so density of oil is 900. Density of oil is 900 kg per meter cube, and also we have one thing that density of oil is 900 kg per meter cube, and here what they have given you diameters. D1 is 50 0.5 meters. Okay, so 0.5, 0.5, half meter, and D2 is how much actually here? So D2 is like 1 by 4 meters. Okay, so this is 1 by 4 meter. So basically D1 is 2 times of D2. So the pressure difference will be 15 by 2 times of rho V1 square. Okay, so let us see. So P1 minus P2 is equal to 15 by 2 times of rho V1 square. Okay, rho oil times V1 square. Okay, so because we know that whenever the flow is happening in this particular case, then whenever D2 is half of D1, then definitely V2 square minus V1 square gives you this particular result. Correct? We have seen this. So P2 minus P1 in this case is equal to, so here if you see P2 minus P1 case in this case is this diameter. Okay, so for example here if you see this oil column height. Okay, so this oil column height from here to this location, and here from this location, of course, so the same horizontal level to this location is nothing but this diameter value. Okay, so this radius value, whatever is the radius of the pipe, that is generally this part, and here this is due to this deflection H. Okay, so this value will take as the half of D1. D1 by 2 is what you take generally. Okay, because if you see this is D1 by 2, and here if you see this, if you neglect this small difference, then this D1 by 2 height is maintained because of this limb actually. Okay, so from manometry what we write is from manometry if you equate pressures at these two locations. Okay, so if you equate pressures at these two locations, location 1 and basically same location here at location 2, then how can we get this A and B? For example, if you make these points A and B, then pressure at location A is P1 plus this quantity. Okay, and here if you see the same amount of quantity, if you see, then this amount of oil, if I take X, this X gets neglected actually. Okay, so if you neglect this X, then P1 by rho Z plus from manometer, if you write directly from manometers, then P1 plus density of oil into G into X plus h, this manometric height. Okay, so this manometric deflection height is also given by h. So this is equal to P2 plus. Now this column of this column of what do you say? This column of oil is given by this value, which is d1 by 2 actually. So oil into G into d1 by 2 approximately plus this x plus density of mercury into G into h. Okay, so this h is the deflection. Now you cancel this part x corresponding to the oil. Then in that case, P1 minus P2 difference. Okay, so from this equation, P1 minus P2 difference is going to be density of oil into G into d1 by 2, density of oil into G into d1 by 2 plus density of mercury minus density of oil into G into density of mercury minus density of oil into G into h. Okay, so this is how we calculate h, and for calculating the pressure difference we know V1 square by 2. So discharge is known to you and d1 is also known to you, so you can get V1 square value actually here. Clear? So once you get V1 square value, then okay, so once you get V1 square value, because obviously here the limb pressure should be taken here, because what happens normally these two are not connected on the same level actually. Okay, so the pressure at this location and the pressure at this location are not same, and this oil column is generally this oil column is generally present here. Clear? So if you do this calculation, 14.66 mm is what you're getting, 14.66. okay, so maybe this answer. So if you multiply with the 14.66, if you divide with 1000, yes, you will get 0.0146. okay, so fine, let us check the answer. So if you check this calculation, okay, so yeah, so if you check this calculation, then you can get the correct answer. So P1 minus P2 and equated these two. Okay, Roshan, clear? Have you equated these two things? So please type in the chat box, have you equated these two things? Okay, so please confirm. So equating these two things could give you the answer, correct? You have done the calculation already? Yes, in meters it is 0.0146 and in mm it is, yes, 14.66, correct? Okay, so if you equate these two quantities, then you'll get the correct answer, of course. So 15 by 2 oil V square. Okay, so 15 by 2 rho oil into V1 square. V1 square can be written as 16 q square. Okay, so 16 q square by pi square d1 power 4. Okay, so this is V1 square. So this is equal to then P1 minus P2 value, which is equal to this, which is rho oil times G into d1 by 2, rho oil into G into d1 by 2 plus this quantity, which is density of mercury minus density of oil into G into G into h is what you have here. Okay, so this is h. So from this equation you have to calculate what is h value. Okay, so for that we'll do one thing. Density of oil, if you cancel density of oil, then this density of oil by density of oil here. Okay, so you'll get one density of oil in the denominator. So fine, so if you do this calculation, 15 by 2, this is 8 anyhow, so 15 into 8, 120 into q square. So what about q square? Discharge. So discharge is 102.04 liters per second, so 0.102 0.10204 whole square divided by pi square into d1 power 4. So what is d1 power 4? 0.5 meters, correct? So 0.5 meters, so 0.5 power 4, 0.5 power 4 minus G 9.81 into 0.25 is equal to density of mercury. Did they give you any value? Density of mercury value? So okay, nothing is mentioned. So take 13,600. So 13,600 by 900 minus 1 into 9.81 into h. Okay, so this is the value of h. So let us calculate this value. So if you calculate this value of h in meters, okay, because this is in meters, perform this calculation. 120 into 120 into 0.10204, 0.10204. Okay, so 10204 square actually. Okay, so square of this value divided by 0.5 power 4. Okay, so divided by 0.5 power 4, so this gives you around 20 divided by pi square. Okay, so divided by pi square gives you this value 2.02 minus 9.81 into 0.25. Okay, so I think this calculation should be done again. So 15 into 8 into q square by pi square into d1 power 4 actually here. Okay, so is this correct? I hope things are clear. Okay, so if you perform this calculation, so this quantity, if you take negative, okay, so basically if you have equated these two and if you simplify, you will end up with the final answer as 0 point, okay, 0 point in meters. Option C is the correct answer, basically 0146 meters. Okay, so 0.0146 meters is what you are getting. Okay, so if you equate those two and if you simplify, you will get 0.0146 meters. Clear? Okay, so type in the chat box, is this clear to all of you? Fine. 0.0146 meters. Okay, I hope all of you are getting this. So type in the chat box. Okay, just please do the calculation, then you can easily get that. Okay, I think I've made one decimal mistake somewhere, but definitely this will be the answer as all of you have got. Okay, yeah, 14.63 mm. Now let us see this question. Hydrostatic forces. A solid cylinder is placed inside an interface of two fluids as shown in the figure. Then the resultant hydrostatic pressure force on the cylinder should be dash kilonewtons. Width of the cylinder in the plane is 1 meter. Okay, so basically width into the plane is basically 1 meter. It's a 1 meter long cylinder. Okay, so how do you calculate the hydrostatic forces acting on them? First of all, so FH is equal to first of all, hydrostatic force acted because of this water. Okay, so when you see hydrostatic force acting on acted upon by water actually, then in the x direction, if you see rho f into density of water into g into what could be the projected area in this case. Okay, you will get a rectangle of diameter and length 1, correct? So d into 1 meter width into from the free surface it is at a distance of 1/2 minus to this water force, you have a contradiction from this specific gravity of 1.2. So 1.2 into density of water into, now this projected area perpendicular to this plate will be half of the diameter because this is 2 meters. So half of the diameter into 1. So d by 2 into 1 into from the free surface it is at a height of d by 4 actually. Okay, so it is at a height of d by 4. Okay, so this is I think we have written area into this depth of center of pressure, which is 2 meters from the top. Okay, so this is 2 meters, not 1/2. This is 2 meters minus this quantity, which is d by 4, which is only 1 meter in this case from the free surface. Okay, so if you perform this calculation, then rho w into g is also there here. Okay, so into g should be there, so g times of, okay, so density of water into g into d into 2. So what is d into 2? 4 into 2, 8 meters. 8 minus this is 1.2 into this, d is 4 actually here and d is 4 here. So this is 1 and this is 2 actually. So 2 into 1 is 2. 2 into 1 is again 2. Okay, so we have 2. So rho double 1.2 into 2. So this is the total hydrostatic force which is acting on the fluid, correct? So in kilonewtons. Okay, so let us suppose if they're asking in kilonewtons, then by taking this density of water we can write answer in kilonewtons. Okay, so 8 minus 2.4, 8 minus 2.4 times z, 8 minus 2.4 times 5.6 g is what you have here. Okay, so 5.6 g. And what about the vertical force? Vertical force is equal to, they haven't given any density for this body, correct? So they are just asking hydrostatic pressure force. Okay, so when they, if you see now this left half of the cylinder is completely in this water. Okay, so pi by 4 d square volume or density of water into g, density of water into g into volume of fluid which is inside the water, which is pi by 8 d square, because pi by 4 d square is for complete cycle, but only left half is in the fluid. So pi by 8 d square into pi by 8 times of d square, which is the volume, into 1. Okay, into 1, width is 1 unit, minus this plus, then you have one more thing. Okay, this half of the solid is in this fluid, so 1.2 times of density of water into g into pi by 16 d square into 1. Okay, so this is the volume of the cylinder. So density of water into g into, then we have pi by 8 d square, or if you take d square out, for example, g d square times of pi by 8 plus 1.2 into pi by 16 is what you have here. Okay, so if you simplify this, then we'll get the answer. If you delete this density of water, then we'll get the answer in kilonewtons. Okay, so we'll get the answer in kilonewtons, 112.88 kilonewtons. Okay, let us calculate. So g is anyhow here, so d square is actually how much? 16. Okay, so d square is 16, so this gives you 2 pi plus 1.2 pi, so 3.2 pi totally. Okay, so 3.2 pi times g kilonewtons. Okay, so this is what you have, because d square is actually 16, so 16 pi by 8 is 2 pi, plus this 16 gets cancelled, so 2 plus 1.2, total 3.2 pi. Therefore magnitude of the total hydrostatic force that's acting is equal to square root of hydrostatic force in the horizontal direction plus vertical square. Okay, so this gives you g into square root of 5.6 square plus 3.2 pi square. Okay, so this is what you have here. Okay, so then this is g, the answer is going to be in kilonewtons. Okay, so let us check this. 5.6 square plus 3.2 into pi, 3.2 into pi square. Okay, so square of this value, so 132 point something, so take a square root of this. So when you take a square root of this, then take a square root of this, 11.50 into 9.81 into 9.81, so 112.889. correct? Yeah, all of you are getting 112.889 version. Fine, so 112.9 kilonewtons is the correct answer in this case. Okay, so horizontal force is due to the projections. From projections we can take this, and vertical force is basically the buoyancies which are acting on the elements. Clear? Okay, yeah, 112.889 kilonewtons. Yes, correct, 112.889 kilonewtons is the correct answer here. Okay, yes, 112.889 kilonewtons is the correct answer. Great. So now let us go for the next question. This is by knowledge question. Energy loss in the pipe is 2 meters. The vacuum pressure at point B should be dash kilopascals. Okay, so they're asking pressure at this point. It's a simple question actually, by applying Bernoulli's equation. So if you apply Bernoulli's at these 2 points, then you can easily get the answer. So will you solve this question? They have given you different diameters, and definitely you can easily calculate this question. Okay, so datum difference is also given, 100 and 107. So please type in the chat box, can you do this question? Okay, so type in the chat box, will you be able to solve this question? Simple, discharge is given directly, and area of means the diameters are also given, so definitely you can just apply the Bernoulli's equation. You can just solve this directly. Okay, so we'll go for the next question. Okay, so let us see. So the velocity along the center line of a nozzle length L is given by V is equal to T into 1 minus x by 2L whole square, where V is velocity in meters per second, T is time in seconds, x is distance from inlet to the nozzle. The local acceleration at T is equal to 4 seconds is at T equal to 4 and x is equal to 0.5 meters is dash meters per second square. Correct up to 2 decimal places, given that L, this constant L, is 0.8 meters. Okay, so correct up to 2 decimal. Fine, of course we have to correct up to 2 decimal places. So what is local acceleration basically? So please tell me. Normally if you take accelerations, there are 2 types in that. Okay, so one is the change in velocity with respect to time, and the other is change in velocity with respect to position. Correct? Like for example, if you have a converging passage, okay, then even in case of steady flow, what happens basically? Even in case of a steady flow, because of the convergence of the passage, the fluid actually accelerates in between. Okay, so that's how when fluid is accelerating, then in that case the acceleration is not because of the increase in time, increase in velocity due to time, but here the increase in velocity due to position actually. Okay, so that's called convective acceleration. Okay, but sometimes normally velocity increases with time whenever there is some unsteadiness, so that is due to time actually. Okay, so here they're asking you temporal acceleration. Okay, so how do you calculate the temporal acceleration? Velocity is given, so what is velocity? It's a one dimensional case, so t into 1 minus x by 2l whole square, t into 1 minus x by 2l whole square. Okay, so this is whole square. Now in that case, local acceleration at t equal to 4 seconds. So local acceleration, which is also called temporal acceleration with respect to time. So temporal acceleration, which is equal to dou v by dou t. Okay, so this is the temporal acceleration. Okay, we have to calculate dou v by dou t. Okay, so partial differentiation. So if you do this, this is nothing but 1 minus x by 2l whole square. Okay, because if you differentiate this quantity, we will get this expression as this 1 minus x by 2l whole square. Okay, so this value is equal to, we want this value at x is equal to, from the inlet of the nozzle at a distance of x is equal to at x is equal to 0.5 meters. Okay, so at x is equal to 0.5 meters, x is equal to 0.5 meters. So temporal acceleration is equal to dou v by dou t at x is equal to 0.5 meters is equal to 1 minus x by 2 times of L. So what is 2 times of L actually? So 2 times of L is 1.6. So 1.6 whole square. Okay, so this is 1.6 whole square meters per second square actually. Okay, so this is a temporal acceleration. So point useful होगा. So yes, ये class 12th के लिए useful होगा. Maybe few questions, not the other questions. Okay, not the hydrostatic forces and all these things, but very few questions. Okay, hardly 1 or 2 questions. So now if you see this 0.5 by 1.6, 0.5 by 1.6. Okay, so 0.5 by 1.6. So subtract this from 1. So subtract this from 1 actually. Okay, so square of this. So 0.4726 meters per second square is what we have here. Okay, so this is 0.4726 meters per second square is what we have here. In clear? Yeah, 0.473 almost. So 0.473 meters per second square is what you do generally. Okay, fine. So let us see the next question. A 1:10 scale model of submarine moving far below the surface of water is tested in a water tunnel. If the speed of the prototype is 8 meters per second, then the ratio of the drag for the model and the prototype is dash. Okay, so they are asking you what is the ratio of drag force acting on the model to that of drag force acting on the prototype. Okay, so dimensional analysis basically. So kinematic viscosity of sea water is 1.121 into 10 power minus 6 meters square per second. Kinematic viscosity of water is 10 power minus 6. Density of sea water and density of water. Okay, so whenever they give you questions of dimensional analysis or model and prototype analysis, try to plot or try to make the data for model and for prototype actually. Okay, so when you make this, then let us see model and prototype. Okay, so tell me one thing first of all. Code number. Okay, submarine. Try to understand this. Submarine moves inside the fluid or on the top. In case of submarine, will you have free surface flow? So tell me, in case of submarine, will you have any free surface flow? In case of submarines, will you have any free surface flow? Type in the chat box. Will you have any free surface flow in case of submarines? No. Submarine is actually completely submerged. Okay, so drag acting on this. So what could be the dimensionless number? That should be same. Whenever things are completely submerged, then inertia of the body tries to move it, and obviously viscous force will try to stop it. So if inertia and viscous are the dominating forces, then what could be the important dimensionless number in that case? Which number? Which dimensionless number should be important in that case? Type in the chat box which dimensionless number should be important in that case. Actually, Reynolds number. Okay, so that number should be, yes, Reynolds number. Clear? So Reynolds number should be same between the model and the prototype actually. Clear? So now let us see. First of all, let us try to add the model. Okay, now one more question I would like to ask you. First thing, out of model and prototype, which size will be large and which size will be small actually? I mean, out of model and prototype, whose size will be larger and whose will be small? What do you think? So type in the chat box. What do you think? Out of model and prototype, size of what will be large? Model chota. Photo big, model small. Photo larger. Fine. Let me ask you this question. Normally in our mechanical applications, what you told is the thing that happens. Prototype will be large and model will be small. But sometimes if you go to advanced applications, like for example, model is replica. Yeah, model is smaller. Fine. Look, model always need not be small. Okay. For example, I'll tell you. Let us suppose if you are studying heat transfer on small electronic chips, for example. Okay, you have taken some Arduino board, and let us suppose, yeah, let me tell you. So let us suppose model need not be small always. Okay, I'll tell you why. Let us suppose if you are talking about heat transfer on some small chips, electronic chips. Okay, then if you want to understand that heat transfer, it is very difficult for you to conduct experimentation on the small electronic gadgets. Okay, like for example, conductors, semiconductors of that level. So what you actually do is you will generate some larger models. Okay, so it's not always like model is small and prototype is large. Okay, model is just a replica. It can be a chota or bada, anything. Okay, so model can be large or model can be small than the actual prototype. Okay, it depends completely on the application, but of course in the classical applications like airplanes or ships, submarines, all these cases, or in pipe flows, we actually make the model small. But when you go for advanced applications like heat transfer in chips, electronic chips, or cooling of electronic chips, okay, which is one very important domain nowadays. So if you see in all these cases, we make the model large actually. Okay, so that's why it's not mandatory that always model should be small. Clear? Fine. Yeah, prototype is actual thing, what actually exists in the field. Yeah, that's why you said replica. Good. Okay, but actually models can be larger than the prototype sometimes. Okay, now let us see the conditions here. So if you see what we have, a 1:10 scale model of submarine. So obviously in case of submarine, submarines will be large and model will be small. Okay, yeah, model can be small or large. Okay, so in case of submarines, model will be small, of course. Okay, so length of model by length of prototype is 1/10 in this case. Why? Because general actual submarines will be larger than models. Okay, is moving far below the surface of water. See, they have given you one hint also here. You should not apply Ford number. They have given it is far below the surface of water. Okay, means from the surface of water it is moving at much depth. Is tested in a water tunnel. Okay, if the speed of the prototype is 8 meters per second, so what is velocity of the prototype? 8 meters per second, and this actually moves in sea water. Okay, now this is tested in water tunnel, means fresh water. Normally what you test in labs and all, that is fresh water, and this is sea water. Okay, submarines actually move in sea. So the ratio of drag force for the model and the prototype is dash. Okay, so F drag on the model by F drag on the prototype. Okay, so this is what you need actually. So F drag for the model to the prototype. Okay, so first of all, so here, yeah, first of all, if you see, Reynolds number of the model should be equal to Reynolds number of the prototype here, correct? So which means we know velocity of the model into length of the model by kinematic viscosity of the model. So because Reynolds number is V dimension by kinematic viscosity is equal to velocity of the prototype, length of the prototype by kinematic viscosity of the prototype here. Okay, so these two things should be same first of all. Then coming to the drag force, we know drag force is equal to, so whenever Reynolds numbers are same, then definitely, okay, fine, I think there is no issue. Okay, chat box is fine. So now if you see, whenever you are trying to calculate the drag force, so coefficient of drag completely depends upon Reynolds number. So that's why, since Reynolds numbers are same for model and prototype, coefficient of drag is also same. Okay, so normally what is the expression for drag force? F drag is equal to half CD density A into V square, velocity square, correct? So basically if you see, half is constant, CD between the model and prototype is also constant. So this ratio is equal to density of model by density of prototype into this area. Area is nothing but length square. So length of the model by length of the prototype square into velocity square. So velocity of the model by velocity of the prototype square actually. Okay, so if you see, this implies drag force acting on model by drag force acting on prototype is equal to density of model by density of prototype into length of model by length of prototype square into velocity of model by velocity of prototype. So from this equation, we know velocity of model by velocity of prototype is equal to kinematic viscosity of model by kinematic viscosity of prototype into length of prototype by length of model. Okay, now if you substitute this there in that equation, we'll get kinematic viscosity of model by kinematic viscosity of prototype whole square into length of prototype by length of model whole square. Okay, so this is what you get basically. Okay, so now if you can, can we expect single question from this session? Yeah, definitely, why not? Okay, if things go like every year, you'll get easily some good number of questions actually. Okay, so see here, this LM by LP and LP by LM gets cancelled. So this is density of model by density of prototype. Okay, so what is density of model by density of prototype? Model is moved in freshwater tunnel, so this is 1000 and this is 1027 actually. Okay, so 1000 by 1027 into kinematic viscosity of the model. Okay, so model is freshwater, so kinematic viscosity of model is 1 into 10 power minus 6, 1 into 10 power minus 6 by kinematic viscosity of prototype actual sea water is 1.121 into 10 power minus 6. So square of this quantity. Okay, so 10 power minus 6 gets cancelled. Now if you do this value, you will get the ratio. So 1000 by, first of all, 1.121 square, 1.121 square. So reciprocate this multiplied with 1027. Okay, so now multiply this with 1000. Okay, so when you multiply with this 1000, okay, is everything fine? No, I think there is some issue. Just a minute. 1000 divided by this calculation should be very important. Okay, 1027. So this value multiplied with 1 by 1.121 square, 1 by 1.121 square. Okay, so square of this value, fine. So 0.775, 0.7748, which is 0.775 is what if you round off to 3 decimal places. Yes, 0.9737 is what you got. Check the calculation once again. I hope this is correct. Okay, because O L V square. Okay, fine, this is fine. Then from this equation, V L by nu is equal to VP LP by nu. So V model by V prototype is kinematic viscosity of model by prototype into length of prototype by length of model. So in that square, if you replace this quantity LP by LM whole square, then these two quantities gets cancelled. Okay, then 1000 by 1027 into 1 into 10 power minus 6 by 1.121 into 10 power minus 6. Correct. Okay, so I think this calculation should be correct. 0.775 is correct. Okay, so 0.775 could be the correct answer. Yes or no? Clear? Okay, so please type in the chat box, is this clear to you? 0.775. Yeah, 0.7748. Yes, even I got 0.7748. I have rounded it, rounded off. That's it. Okay, 0.7748. I have just rounded it off to 3 decimal places. Clear? So 0.775 is the correct answer. So let us see this. An impulse turbine of 3-meter diameter is rated at 1000 kilowatt at 300 rpm. Okay, under a head of 500 meters. So there is one impulse turbine of 3 meters diameters and it is rated at 1000 kilowatt at 300 rpm under a head of 500 meters. The turbine is operated under a head of 400 meters. What is the speed at which it would run actually? Okay, so the turbine is actually operated at some different speed. What should be the speed if it should be operated if the head is actually 400 meters actually? Okay, so now if you see, normally in case of hydraulic machines, this is an impulse turbine. Normally for any turbine, if you see, normally these kind of questions based on the scaling, okay, so they change the head or they change the powers, all these things, they the dimensionless numbers, three set of dimensionless numbers are actually very important actually here. Okay, so one thing is gh by n square d square and q by nd cube and p by rho n cube d power 5. These numbers, these dimensionless numbers are actually very important for hydraulic machines. Okay, until and unless you consider compressibility effects and viscous effects, 90% of the hydraulic machines questions what comes in gate exam depends on these three numbers actually. Okay, qh or gh by n square d square and q by nd cube and p by rho n cube d power 5. Okay, normally these numbers we can easily get from the dimensional analysis using Buckingham's pi theorem, which I have shown in my detailed course, actually comprehensive course of fluid mechanics. But normally if you see, these are the dimensionless numbers that are important. Okay, now here to maintain the same power we need this n cube and d power 5 actually here. Okay, but here the things are connected with head also. Okay, this is one dimensionless number. So if you want to work out different things, the terms which are connecting the head and of course the rotational speed actually. Okay, impeller diameter is same. Okay, so the impulse turbine has the same diameter which is of 3 meters in diameter. So in that case, this head is 500 meters and the turbine is operated under a head of 400 meters. So what is the speed at which it would run? Okay, so now if you see, this dimensionless number involves head and this dimensionless number involves rotation speed and power. Okay, so now if you see, for example, if we divide these two dimensionless numbers, p by rho n cube d power 5 by gh by n square d square. So this is also a dimensionless number, correct? Because this is a ratio of two dimensionless numbers. Okay, now if you see, n square can cancel this n times, okay, and d square can cancel this d cube times. Okay, so if you see this equation, we get p by rho n cube or rho n d cube into gh is what you have here. Okay, so this is the dimensionless combination. Okay, because this is the ratio of two dimensionless quantities, so if you can cancel some terms of this, then again it turns out to be a dimensionless quantity. Okay, now if you see, p by rho n cube gh is what you have here. So rho and g are constants here because the fluid doesn't change, and that impeller diameter is also constant here. Okay, so the impeller diameter is also constant. So nh, okay, so p by nh is what you have to make equal for things here. Okay, so therefore from these equations you can see g power should be same, so n1 cube d1 power 5 should be same. Similarly h by n square d square. So from this relation we can get this particular understanding. So p by nh, this value should be same. So if for the same power, this product of n and h should be same actually here. Okay, so if you see at 300 rpm, this is 500, so 3 into 5 is 15, so 4 into some other value, so something more than 300 should be there here. Okay, so it's almost like 1.25 times of 300 is what you should get actually here. Okay, so 1.25 times of 300, this gives you around 375 rpm. So here 364 is there. Okay, so instead of doing this, we will do separately also because some decimals I think they have changed. So if you do this, gh by n square d square. Okay, so first of all, gh by n square d square of first case is equal to gh by n square d square of second case. Okay, so power is actually present here, so G gets cancelled. Okay, and diameter of the impeller also gets cancelled. Okay, then in that case h1 by n1 square is equal to h2 by n2 square. Okay, so this is n is in rpm. Okay, now n2, the rotational speed in this case is n1 into square root of h1 n2 is equal to n1 into square root of h2 by h1. Okay, so h2 by h1 actually here. So h2 by h1 gives you h2 is around 400 meters and h1 is around 500 meters. Okay, and take a square root of that, and this is n1 actually here. Okay, so when you do this calculation we can get the answer. So h2 by h1, so 400 by 500, 0.8, so 0.8. Okay, and square root of this, so 0.89, so 300 into this, 300 divided by this value, correct? So 300 divided by this 0.89 around. Okay, so 337 point something, so 336 rpm could be the correct answer. Okay, so that's how we do the calculations here. Okay, similarly for any impulse turbine or for any turbine in general, those are the dimensionless quantities that are available. Okay, so see, similarly here a hydro turbine is required to give 25 megawatt at 50 meters head and 90 rpm runner speed. The laboratory facilities available permit testing of 20 kilowatt model at 5 meters head. The model runner speed is dash. Okay, so they have given you, again if you see the model gh by n square d square, because here also they have talked about head n square d square, so this of the first should be equal to gh by n square d square of second. Okay, so gh by n square d square actually, yeah, 336 rpm around. Okay, so we'll get 336 rpm around in previous case, and here the power is also given, so p by rho n cube d power 5 is equal to, in the first case is equal to p by rho n cube d power 5 in the second case. Okay, so this is in the second case, but here if you see impeller diameter is not changed. The laboratory facilities permit testing of 20 kilowatt models at 5 meters head. The model runner speed is what they're asking. Okay, so let us suppose if the density is same. Now what about the diameters ratio? G is anyhow same here in this case, so heads is changing and diameters, this n ratio, n into d ratio is also there here. Okay, so h1 by h2 is equal to n1 by n2 square into d1 by d2 square actually here. Okay, so now if you want impeller speed, okay, the model runner speed, you can take the ratio of d1 by d2 from this equation. Okay, so from this equation d1 by d2 is equal to n2 by n1 into square root of h1 by h2. Okay, so this is the relation for the impeller diameter ratios from this. Okay, yeah, we can do this, right? So basically you can do this question, right? So simple again, using dimensional analysis we can simply do this. So d1 by d2 is equal to n2 by n1 into root of h1 by h2. So if you replace here, then we need, what do we need? Model runner speed. So we need n2. For example, if you take model and prototype for example. Okay, so if you test with model, then we want model runner speed. Okay, so n cube is equal to np cube into dp by d model, dp by d model whole square, sorry, whole power 5 into, okay, into, and this is nm, right? So pm by p, so pm by p of the prototype. Okay, and now how do you define this n1 and n2? So let us suppose if this is of model by prototype, so prototype by model into model by prototype. Okay, so now if you keep this dp by dm as the value here, so nm cube is how much? Nm cube is equal to np cube into then dp by dm whole power 5. So dp by dm whole power 5 is nm by np whole power 5, nm by np whole power 5. Okay, so this is nm by np whole power 5 into this hp by hm whole power 5 by 2, correct? So hp by hm whole power 5 by 2 whole power 5 by 2 multiplied with, then the last term is power in the prototype by model by prototype. Okay, so this is what you have. Then if you take if you can calculate you know, we need one speed anyhow, so this is 1 5 by 3 5 by 6 and whole power 1 by 3. Okay, so we have this 1 by 3 in this case. Okay, so this implies model is equal to prototype. So what is the speed of the prototype actually here? N of the prototype actually. So type in the chat box. So type in the chat box N of the prototype. They have given you, correct? So the prototype is running at 90 rpm. Okay, so it is running at 90 rpm. So 90 into nm by np. So what about nm by np? This is okay, nm is what we need. Okay, so nm by np, but we don't have this ratio of nm by np, correct? So what can we do? Basically we can actually take this 1 minus 5 by 3 here. Okay, so minus 2 by 3 is what we have. Okay, so basically from this equation you have to calculate the nm value. Okay, so will you calculate this? So type in the chat box, from this equation you have to calculate what is the value of nm. Okay, np is given to you, all quantities are given to you, you just have to substitute and calculate the correct answer. Okay, clear? So please type in the chat box. So type in the chat box. Can you do this calculation? We have only one variable in this equation. nm is not known to you. That's it. Apart from nm, we know all other values. Okay. Basically, equate any two combinations of dimensionless numbers, and that can simplify your answer. Okay. Fine. So please try to solve that question. Okay. So single equation and single unknown. Then okay, fine. Super 30 questions. Fine then. So fine. Actually, today this session is supposed to be taken by myself and Amit Moya sir, but unfortunately some technical issue got developed in his system, and that's why the session started half an hour late actually. Okay, and so basically these are the questions, some good questions that we have solved today. In hydraulic machines, we have solved only the questions of dimensional analysis. Okay, so hopefully in tomorrow's session we'll try to whatever is there, we will try to put one two question some questions on Pelton wheel and couple and turbine, this Francis turbine actually. Okay, because sometimes 3-4 times what they have done individual questions on Francis and turbine depending on the velocity triangles and all. Okay, so the velocity triangles and all, if you see, I would like to give you some basic analogy here. So normally if you see energy supplied to the rotor, okay, whatever is the rotor that's there, to the blades, the energy supplied is basically in two parts. Okay, so total energy supplied will be in two parts actually. So first thing is the static head that you have plus half into this particular part is due to the static head, and due to the pressure head we again have this term u1 minus u2 square plus v relative at inlet minus relative at outlet square. Okay, so these are individual squares actually. So u1 square minus u2 square and vr1 square minus vr2 square actually here. Okay, but in case of impulse turbines like Pelton wheel and all, we have the question something like these two terms, the pressure difference is actually zero, because in case of Pelton wheel and all, we have whatever the total energy available, that energy is available only in terms of kinetic energy. Okay, there's no pressure energy. But in case of Francis turbines and all, what we do generally, we'll create a casing in such a way that the fluid enters with certain pressure energy also. Okay, so the main difference between impulse turbines and the reaction turbines, Francis and Kaplan turbines, is basically this. Okay, so normally if you see impulse turbine, if you see Pelton wheel is actually impulse and tangential wheel actually. Okay, so fluid comes and hit the location tangentially. But in case of Francis turbines, what happens, there is certain pressure energy that's available, and those are radial flow reaction turbines. Okay, so in case of Francis turbine, fluid tries to enter radially from the blades and then it tries to impel on the rotor. Okay, and this head is actually obtained from this relation 1 by 2g times of vw1 u1 minus vw2 u2, where these are the wheel components. Okay, so vw1 and vw2 are the wheel components of the rotation. Okay, so basically in any case of turbine, it can be Pelton wheel, Francis turbine or reaction turbine, basically these things should be there. And obviously if you can understand one thing, this U2 in this case of reaction turbines. In case of reaction turbines, what they do is they will try to maintain the outlet radial completely. Okay, so whenever they try to maintain the outlet radial completely, this VW2 will tend to 0. That's why in Francis turbine and all, what happens, just in front of the draft tube, what happens, whenever the impeller is rotating, just below the impeller, the flow is actually converted completely radial. You might have seen this. Okay, so if you see, the flow completely gets converted to radial at the exit of the Francis wheel actually. Okay, or the Francis turbine. Okay, so in case of reaction turbines, it is tried to made that the outlet is at generally radial location, so that this part of energy which is getting lost from this energy is made minimum actually. Okay, so this some questions on velocity triangles and all will try to put in the tomorrow session, or if not, when I'm taking XC series, I'll try to put that questions. Okay, because Amit Maya sir has to be dealing this part today, but unfortunately at the last moment we have deleted some questions actually. Okay, but just giving the fundamentals, I'll try to take some questions on this. Okay, because today I think questions are finished actually. Yeah, questions are finished, fine. So these are the questions that we have. Okay, so if you have any doubts, you can ask me in meanwhile. Okay, so boundary layer theory, yes, boundary layer theory, basically whatever the there should be some questions on boundary layer theory actually, but we haven't seen, right? What? Okay. Fine, don't worry. Again, I'll come back with you to you with some XC questions or something like that. So then we'll spend some time. Okay, when you are going to take XC series. Okay, so very soon, maybe tomorrow or in couple of days, we are going to talk about it, and definitely before get examination, we'll try to take some sessions on XC series. Okay. Boundary layer questions are actually very easy. Actually, if you see complete boundary layer equations, whatever we do, at least for mechanical and XC, if you see, they move only about two equations. One is the Prandtl equations, or the basically the what do you say, viscous flows for boundary layers, and second is the one convex momentum integral equation. Okay, which gives you the relation between wall shear stress and the this momentum thickness dou theta by dou x. Okay, so these two things are the only two equations about which the complete boundary layer theory moves on, at least for undergraduate level. So that again will put some questions in. So don't worry because when we are dealing this XC series, definitely we'll try to take majority of the questions from boundary layer theory, then Reynolds transport theorem, and this of course turbo machines is not in syllabus of XC, but again, yeah, since today I think definitely some turbo machines questions would have been done, so I'll try to give that questions there, and yeah, basically these are the things. Okay, so how are the questions you felt? How did you feel about the questions? Oh, some good number of likes also today. Okay. Then I think session went fine. So did you all enjoy this session? Actually, we have taken some good questions. Okay, in between some of the questions you might not have seen before. Actually, some set of models at least, and using gate calculator simultaneously could help you in doing the calculations. Okay, fine then. Okay, so anyhow, just some question practice kind of session. Okay, of course, it's not a detailed course. Again, if it is a detailed course, I would have done some lot of other things, but it's a short session actually. Okay, Nikhil, so please explain that QS in which another pipe is inserted in half and asked to calculate increase in Q. Which question? I didn't get this. Okay, so tomorrow we have only one class left basically here. The last class at 9 a.m. tomorrow. So basically industrial engineering and over and heat transfer. So Amit Dikshit sir and Sandeep sir will take this session. Okay, so both of them will again try to finish off the things. So within some 5-6 quick lectures, we have done some good number of questions in practice. Okay, so today also some 30 questions again we have solved. Okay, and that will definitely, so almost some 150 questions will definitely help you out, and we set these questions in such a way that majority of these are repetitive in models. Okay, so that you will enjoy the session, and obviously some 25 to 20 extra marks, whatever you can get in the exam. That could be from this series, obviously. Okay, and of course this is our mechanical team that you know for past quite some time. Okay, Amit Moya sir, Vatan sir for aptitude, of course, and Ramanand Bansal sir for machine design, then Vishal Soni sir and myself partly for mathematics, and then this is me and Kuldeep sir, of course, dealing some crucial background work at the moment, and Aditya Paul sir and Swadesh Kumar Singh sir, they are dealing the production and manufacturing sciences. I hope you might have attended some lectures from there, and that would definitely help you out. Then Vinod Datsul sir, Negi sir, myself for thermal, and Sandeep sir for heat transfer. Then Apup sir and Amit Dikshit sir, Vishwajit sir, basically for theory of machines and industrial engineering part. So Amit Dikshit sir is really one of the finest faculties for IE and OI again. So tomorrow his session, so do not miss the session. Okay, so almost some 80% of the team has some industrial experience here, and 20% is restricted themselves to academics, but again they have some plenty of good academic experience then. Okay, and finally I have one slide to display. Thank you all. That's it. Okay, so we'll meet again soon on this channel or maybe on English channel, and we will again discuss some questions. Okay, maybe some concepts also, maybe sometime later. Okay, fine. So thank you all. Then good night. We'll meet soon again for XC or something like that, and then we will set all the things ready for GATE 2023. Okay. Anyhow, if some of you might not attend that, I'm telling you now, all the best for your GATE exam, all the best for your GATE 2023, and I wish definitely you'll get good score and end up at some good place finally. Okay. So thank you all. Thank you all for your patience, and thank you. Thank you all. Good night. Take care. Bye all of you. Yeah. Take care. Okay. So thank you all. Okay. Good night, all of you. All the best, and yeah, take care. Bye. So shall I end the stream? Shall I end the stream actually? Okay. So some motivational words. Good. What motivation shall I give you? Okay. Whenever you feel relaxed or when you feel like not studying, think about what happens if you don't get a job for next 2 3 years. Okay. Then immediately you'll start reading. I'll tell you because I generally don't give this motivation sessions, but yeah, because situations themselves should actually motivate you. That's what I personally feel. Okay. Because yeah, situations should actually motivate you rather than words of people. Okay, so if that can happen, then obviously you'll be at good place and doing good work. Okay, just focus on the GATE examination, give your 100% effort. That's it. Okay, that's the maximum thing I can tell you. Okay. Yeah, fine. Take care all of you. Okay, good night. Bye. Take care. Okay, we'll meet soon again on some channel. Take care. Bye all of you. Bye. Take care. Good night.